So here's my whole life story. I learned to code, felt like an absolute wizard, then tried to actually ship something real. What happened to me?
Ha! You bought a ticket, my friend. And that's the whole first chapter. Right there. Learning to program isn't arriving anywhere, okay? It's just the admission ticket. Now it's a real ticket. It genuinely gets you in the door. But the road from there to a good result is long. And here's the thing, it's packed with a whole crowd of other activities that have nothing to do with typing code.
Hold on. I paid good money for that ticket, and you're telling me the show costs extra?
The show is everything. And why does everybody trip over this exact same step? Because of a thing the book calls ad hoc software. Look, tons of programs get written with no plan at all. One off, throw away, solve today's little problem, and move on. And in that tiny world, softwares and program mean the exact same thing. And writing it needs no special technique, no discipline, nothing. Like a quick script you bang out to rename a folder of photos.
Right. Okay, that's basically all my code. Guilty as charged.
You're in excellent company, but watch what happens the moment you need not one program but several, all of them clear, logical, consistent with each other. Suddenly, you have stepped into a completely different problem space. And here's the rule. I want you to tattoo on your arm. The more complex the software gets, the more distinct factors it takes to build it, to use it, and to keep it alive.
All right, so name me the first factor. What's number one?
Documentation. And don't you dare yawn on me, okay? Because it is not the boring afterthought everybody thinks it is. It's really a communication tool. It tells the users how to actually use the thing, and it tells the developers how it's structured and how it's built. And from a programmer's angle, it's way more than a manual. It's the formal specs, the designs, the plans, the interface definitions, the whole skeleton of the project.
Huh. So it's the wiring between all the people, not some PDF nobody opens.
That's exactly it. And get this, it's so central, it gets its own chapter at the very end of the book. Remember that, because we're going to close this whole story right back there. So programming turns out to be just one item on a long, long list of activities. And here's the kicker. Even the coding gets harder inside a big process, because now you follow rules, you honor principles, you don't just make it run and walk away.
So what's actually on that list?
Oh, it's a whole parade. Gathering the goals, analyzing the problem, shaping the requirements, designing, building the interface, implementing, testing, maintaining, planning the resources, guarding the quality. On and on and on. And here's the sneaky part, the part I love. Programming itself isn't even on the list.
Wait. You just spent 5 minutes selling me on programming, and now it's not even on the list?
On purpose. They tuck it quietly inside, implementing the software. And they do that precisely to make the point that coding is one ingredient in the stew, not the whole meal. And to really drive it home, and this one stopped me cold the first time I read it. There are entire projects with not a single line of new code written.
Come on. Software with zero code? That's a cake with no flour.
And yet, you bundle up ready-made programs, some configuration instructions, and a pile of extra content. Images, text, audio, video, and boom, a brand new product without one new program written. The book admits those exist, then says, we're going to focus on the kind where making the program parts is the main event.
Okay, so if the job is this giant pile of activities with a whole crowd of specialists, who's the ringmaster holding it all together?
You reach for engineering. Capital E. Engineering is the practical application of scientific knowledge and mathematics to solve real problems and make real products. And it leans hard, on prior experience. All that experience baked into rules and standards that guarantee you a certain level of quality.
So, software engineering is just that, pointed at software?
That's it. And the IEEE says it beautifully, okay? The application of a systematic, disciplined, and measurable approach to the development, operation, and maintenance of software. And there are 3 words in there I want you to underline: systematic, disciplined, and measurable.
Measurable? That's a weird one to stick in a definition.
Great ear. And it pays off, by the way, because there's a whole chapter later on, software metrics, which is literally the art of making quality measurable instead of just a vibe. And notice how comprehensive that definition is. Development, operation, and maintenance. All the activities of production, not just the fun ones up front.
That's a lot to hold in your head at once. How do you break it down?
You look at three aspects. Some books call them layers. One is process. That's managing and tracking how the work actually unfolds, answering the questions, what do we do and when do we do it? Two is methods, choosing your methods, your techniques, your tools, answering, how do we do it? And three is guarding the quality, process, methods, quality. Hold on to those three. We'll keep coming back to them.
Let me guess, which one's secretly the boss? It's quality, isn't it?
You nailed it. Quality is arguably the most important of the three, and the other two, process and methods. They basically exist to make it happen. Think about it. On a hobby project, it's enough that the thing just runs, okay? But in real production, it has to meet defined quality criteria, or everything else you did loses its value.
Back up a second. You said methods, techniques, and tools like those are three different things. Are they?
They are, and it's a lovely little distinction. A technique is a concrete procedure, one specific way of doing one specific thing. A method is broader. It's a specific way of applying one or more techniques across some part of your work. So take unit testing, the technique of testing little isolated pieces of code. Now wrap a whole disciplined way of working around that technique. And what do you get? Test-driven development. That's a method. And yes, it earns its own chapter later on.
Nice. And I bet there are 100 ways to slice up all those activities.
The book gives you two, and comparing them is where the real lesson hides. The first slice is by the basic job. Planning, then design and implementation, then quality, then maintenance. The second one, this is from Pressman, is the framework activities, communication, planning, modeling, construction, and preparing for the launch. And those run in loops, iterating, not just once straight through.
Two maps of the same country. Why would I bother learning both?
Because holding them side by side teaches you the logic underneath. Watch. The first map hides communication inside planning. The second one pulls it out on its own. The second splits design and implementation into modeling and construction. The first keeps it as one lump. The first names quality as its own separate thing. The second folds quality into everything. And the first calls out maintenance by name, while the second just sees it as one more full cycle around the loop. Same country, different borders.
So what's the actual difference between software engineering and software development? People throw those around like they're the same word.
They overlap a ton. They really do. But development is the fuzzier of the two. It's a slippery word, okay? It shows up in different contexts, meaning different things, sliding back and forth between two extremes. Let me give you both ends.
Please. Both ends.
At the widest end, on an actual project, development means literally everything. All of production, even the process itself. And as a discipline, in that widest sense, it's just another name for software engineering, full stop. Now the narrow end, only design and implementation, nothing else, that fit the old classical methodologies where jobs got split into neat phases by time and specialty. Today, that causes more trouble than it's worth, so the narrow meaning barely gets used anymore.
So, which one does this book actually run with?
A middle path, tuned for Agile. On a project, development means the widest thing, everything, but the discipline points mainly at the work in and around design and implementation. And I love that the book is honest that these lines blur, okay? Defining a component interface. That's planning and design at the same time. Unit testing. That's programming and quality at the same time. And design keeps showing up even inside maintenance.
Okay, and what about the people? Who gets called what?
Here the practice is a bit of a mess. The terms get treated as equals, with a dozen different interpretations floating around. But here's the logic underneath it. Since modern methods lean on everyone being highly skilled and pretty independent, The engineer's title basically goes to anyone working on the program parts.
As opposed to the folks doing the interface, the docs, the artwork.
Right. Those are the other roles. So the book just plants a flag and hands you a clean definition. A software developer is anyone who does design and implementation, plus the jobs that touch them. Simple. And that's exactly how we're going to use the word for the rest of the ride. Now, the big organizing idea, methodologies. Here's the situation. Our techniques aren't perfect and they aren't complete, so people keep refining them and inventing new ones. And that flood makes choosing genuinely hard. Worse, your choice for one problem has to line up with your choices for all the others, inputs, matching outputs all the way down the line.
So, how do you not drown in options every single morning?
You make the calls once, right at the very start. You fix your working principles, your sets of methods and processes, and you stick to them. Good news, every later decision gets faster, and the pieces just fit. Bad news, and there's always bad news, okay? You're choosing early, before you really know the details, and one big global choice is a lot harder than a bunch of little local ones.
So can I reuse those big decisions across a whole bunch of projects?
And right there, that question gives birth to a methodology. Formally, a recommended set of methods and processes, all aligned with each other, that lets you pull off a development project successfully. Think of it as a house style. Do it this way, use these tools, walk this path. It's a framework for every activity, from planning the process all the way to launch, narrowing your choices and recommending the routes and the tools.
A house style. Yeah, I like that.
And it comes in two strengths. It can be very strict, pin down every single step and every tool, or it can be looser, what they call a framework methodology, an Akvirna one, that sets only the broad principles and leaves the specific tools wide open. And here's a little controversy for you. Some people argue the loose ones aren't even proper methodologies at all, that they're incomplete. The book teases exactly that fight.
Huh. Okay, and I heard there are a few headline types. How many are we talking?
4 big ones, and you should note each one by its center of attention. Process methodologies focus on the life cycle and the domain's processes. Model the process, get algorithms, then get programs. And the famous face of that family is the waterfall model. Structural ones focus on getting a good internal structure. Object-oriented ones center on the objects and classes in the problem domain. And agile ones focus on one thing above all, adapting to change.
Waterfall. That's straight down the stages, and you never look back, right?
Water down a waterfall, one direction only, okay? Research, analyze, plan, design, implement, test, prepare, each one sealed in its own phase. And Agile? Agile was born precisely because development drags on and on while the world keeps shifting underneath you, and so do the requirements. So Agile just takes change as its starting assumption from day one, and it's very often blended with the object-oriented methodologies.
But here's what actually bugs me. Software doesn't rust. So why does old software somehow feel worse over time?
Gorgeous question, and the book has a little warning box on exactly this. You're right. Software doesn't wear out. Time does nothing to the code itself. Nothing. But the computers around it change. The inputs change, the outputs change. Users start expecting more, so its value slowly, quietly drops. That's the real reason you maintain it. And here's the neat part. Every maintenance cycle looks like a tiny development process of its own. Plan, design, implement, check. So the software doesn't age, the world just ages around it.
So it doesn't age. The world ages around it. That's kind of poetic, actually.
It really is. And one more trap before we move on, because this one snags absolutely everybody. You will keep hearing the phrase object-oriented methodology, okay? Do not equate that with object-oriented programming. The book is downright emphatic about it. A methodology sets principles across the whole process, a programming paradigm, functional, test-driven, event-driven, only ever touches the implementation, the code itself.
So the methodology is the whole building, and the paradigm's just the coding going on inside it?
Perfectly put. Object-oriented methodology uses object models everywhere. Requirements, domain, architecture, delivery. Object-oriented programming is only the code. And get this, using the methodology doesn't even force your code to be all objects. In practice, you happily mix paradigms for different parts of the job. Oh, and object orientation is so foundational, it gets its whole own chapter early on, with Agile coming later. This chapter is just the map.
All right, land the plane for me. What's this book actually going to spend its time on?
Most of its attention goes to designing and implementing software, with real room left for the broader methodology stuff we just walked through. And it insists on one thing: everyone should solidly know structural design. Not enough to make you a professional designer, okay? But enough to be a springboard into writing genuinely better programs.
Better programs. Please tell me this isn't memorize the rules and obey.
The exact opposite, actually. Every project is its own story, so the goal is never to learn the rules by heart and apply them blindly. It's to understand why and how each rule got shaped, and then how to bend it to fit your project.
So before we go, give me the whole road. Where does all of this actually lead?
The map in one breath. Here we go. Next up, the problems that make software hard in the first place. Then object orientation, that foundation. Then designing software, and the language for drawing those designs, UML. Then the design principles and the patterns, which are really just those same principles worked all the way out into concrete examples.
Patterns. That's the greatest hits chapter. I already want to skip ahead.
Ha! It is a good one. Hold your horses. Then Agile Development and Test-Driven Development. Remember that method we defined earlier? Then Refactoring, Polymorphism, Debugging, Optimization, Concurrency, Event-Driven Architectures, Metrics, Version Control, and finally, Documentation. The very first extra factor from way back at the top of the hour.
The top. So the whole book opens and closes on the same idea.
That's the whole thesis. Right there, it's all about the stuff around the code. And what does it deliberately skip? The big picture quality control, the deployment, the resource and project management, and it hands you off to pressmen and friends for all of that. Because Chapter 1's point is dead simple. The ticket gets you in the door, but the show is everything else.
Learn to code, then learn everything the code needs to survive. I'm in. Thanks, folks. So, last time you taught me how to build software well. Today, we do the fun part. Everything that goes horribly, spectacularly wrong. And I mean that with love, okay? The whole chapter is built on 3 questions in order: what can go wrong, why does it go wrong, and how do we shrink the risk? That's the spine of the whole. Hold on. The fun part is the disasters. I'm learning a lot about you today.
Ha! Look, I'm an optimist about it, and here's why. The epigraph is literally 2 words from Douglas Adams. Don't panic. Because here's the reassuring truth. Right up top, you can almost never wipe out problems completely. Nobody can. But with enough good prevention work, you make the consequences basically negligible. So we're not doomed. We're just careful.
Okay, so before we go further, what even is a problem? Is that the same thing as a failure?
Great instinct, and no, they're 2 different animals. A problem is anything that hurts the process or the result. It makes the work slower, pricier, it drains the team, sours relationships, drops the quality, any of that. A failure is what a problem grows into when you ignore it. You let it sit, you don't babysit it, and it matures into a failure.
So, a failure's just a problem I didn't babysit.
That's exactly it. And formally, the book pins it right down. A failure is any unfavorable deviation from the plan, and the basic yardstick, the way you measure one, is lost material value. which usually means one of two things: blown budget or blown time.
And how many ways can it go sideways?
Four flavors, okay? Cost overrun, deadline overrun, an unusable result, and outright abandonment. But here's what everybody gets wrong. They picture those as four separate boxes. They're not boxes. They're a chain. They're dominoes. Watch them fall. Almost any problem means redoing or extending work. More hours? More money? There's your cost overrun. So you throw more people at it. And maybe you dodge the delay. But usually those extra hours don't fit the schedule, so now you're late too. And lost time breeds more cost, the business gets shaky, and when there's finally no point going on?
One little bug and suddenly the whole company's on fire. Run the four back for me?
One breath. Cost overrun, deadline overrun, unusable result, abandonment, each one nudging the next one over. Tuck that ladder away, because we lean on it all episode. Now zoom in on the strangest one of the four, unusability. And this one really messes with people. The software gets finished, on plan, no serious bugs, and it still can't be put to use at all. All that work, just...
Wait? No bugs and it's still garbage? That doesn't even sound possible.
I know, right? But it happens. And here's how. Maybe some key requirement isn't met. Maybe the interface is unusable. Maybe you literally can't get the thing into production. And underneath all of those, 9 times out of 10, sits poor project oversight. And get this, the paradox is it hits the biggest projects hardest.
The big ones? I'd have bet the big, expensive projects were the safe ones.
Everybody bets that. And it's exactly backwards. Think about it. You build a system for 3 years against a frozen spec, and by the time you finally ship, the business has moved on. The world changed underneath you. The spec doesn't match reality anymore. You built a perfect answer, a flawless answer, to a question nobody's asking.
Oof. And this is real. This isn't just a theory you're spinning.
Oh, the numbers are brutal. There's a famous 1994 study. The U.S. was spending over $250 billion a year on IT projects. A year! And roughly 31% got canceled before they even finished. And only about 16% came in on time and on.
16? So 5 out of 6 were late, over budget, or just dead.
5 out of 6, pretty much. And in the big companies, it collapsed to 9%. Then a 2015 analysis nailed the law, hiding behind all of it. Success is inversely proportional to project size. The smaller you go, the better you do. Small, agile projects, about 58% success. Large classical ones, around 3%. And that's still...
3% is a rounding error. That's not a project.
It's a rounding error, so flip it around and you get the winning conditions. Small projects, experienced teams, modern methods. And the losing conditions are the mirror image. Huge projects, green teams, outdated methods. And by the way, when they studied 52 healthcare IT projects, the number one cause of failure? 44%. Undefined project scope. Nobody drew the boundaries.
And let me guess, nobody saw the risks coming is right behind it.
30%. Right behind it, unrecognized risks, plus unrecognized stakeholders and bad communication. Oh, quick term, because it matters, stakeholders. That's everyone with a stake in the result. The clients who paid, obviously, but also every potential user, and even the people the software only touches indirectly. Everybody in the blast radius, okay?
Okay, but... over budget is still kind of abstract. Did anybody actually get destroyed by this?
The extremes get dark. Foxmeyer, drug, a $5 billion company, went bankrupt in '96 over a botched resource planning system. And the U.S. Aviation Authority poured $2.6 billion into an air traffic control system and then abandoned it. 3 times over budget.
They bet the entire company on software. That is genuinely terrifying. All right, we know what goes wrong. Now the juicy question, whose fault is it?
So the chapter splits the causes into 3 groups, and it's really careful to say this is for understanding, Not for pointing fingers, okay? Causes on the client's side, causes on the developer's side, and causes that sit on both. 3 buckets.
Okay, fair enough. So if it's the client's fault, the client fixes it, right?
And that's the trap. That's exactly the trap. The responsibility to spot the problem and solve it is basically always on the developers, especially the leads. And the logic is sneaky simple. Listen, the problems the client catches themselves, the team never even sees those. Gone. So the only ones left, the ones that land on the teams?
Back. The ones nobody noticed, so you inherit exactly the invisible ones.
That's the job. So, the client side has 5 unrealistic or fuzzy goals. Goals that clash with the company's own strategy. Stakeholder politics, commercial pressure, and users who flat out resist the new software. Take fuzzy goals first, it's a beauty. IT feels so all-powerful these days that people launch a project thinking anything's buildable, with 0 real groundwork. And then the goal keeps shifting under them. And every time it moves, the requirements move right along with it. And that burns money you've already spent.
And user resistance. That's just people being stubborn, no?
See, that's what I'd have thought too. And it's not. It's not just stubbornness. New IT quietly brings 2 things employees genuinely hate. 1, more oversight of what they do all day. And 2, a forced change in how they work. Nobody wants the boss watching closer and the rulebook rewritten in the same week. But here's the clever fix. The smart shops pull the employees right into the planning. Now it feels like better working conditions instead of surveillance. Same change, totally different feeling.
And commercial pressure? That's the boss screaming ship it yesterday?
Basically, yeah. Every project exists for profit, so the pressure builds to cash in fast. And then the bad calls fall, like dominoes, again with the dominoes, reshuffling what gets built, slashing deadlines, skipping quality control. Ideally, you resist all that. But when you can't, the move is damage control, build the critical parts faithfully, only cut corners on the low-stake stuff.
Okay, so what about the team's own sins?
Almost every one of them is a management failure, honestly. Weak leadership, sloppy resource estimates, poor status reporting, risks nobody's managing, betting the farm on immature tech, failing to even grasp how complex the project really is. Developing with no firm principles. It's leadership all the way down.
And the causes that belong to both sides?
Bad communication, mutual distrust, and badly defined requirements. And guess what? The lead can usually catch those too. So every single road, every one of them, leads right back to the leadership. Which tells you...
So it's never really one villain, is it?
Never one villain. Behind every real failure sits a whole stack of causes. One alone almost never sinks a project. It's the nasty combination that does it. And that's exactly why you watch and reassess the risk the entire time. Because every hour you're late to notice, it costs you. Now the single most common cause deserves its own spotlight. Bad planning. And everybody assumes bad planning means too little planning. And that, right there, is a serious blind.
Hold on, you can plan too much? That sounds like something a lazy person made up.
It's very real, I promise. But let's do too little first. It's the obvious one. It comes from weak analysis or from vague requirements. The analysis has to be wide enough and deep enough to answer every question the domain actually needs. Otherwise, you miss whole concepts, whole components. And the special case is vague requirements, which happened because somebody assumed the trivial stuff was, too trivial to bother writing down.
But writing down the totally obvious stuff feels like a waste of everyone's time.
Right? Except, and this is the trap, trivial is wildly subjective. What's trivial to you, with all your experience, is a total mystery to a junior who literally cannot understand what isn't written down. And remember from the intro chapter, documentation is the team's communication tool. So every gap in it is a future misunderstanding, sitting there quietly waiting to detonate.
Okay, now sell me the flip side, the too much.
Over-planning. It looks like going too broad, too unfocused, analyzing too deep, too early, what they call premature detailed design. And my absolute favorite word in this whole chapter? Gilding. Being overambitious. Building fancy, gold-plated stuff, way out of proportion to what anybody actually.
Gilding. That's gold trim on a car that's got no engine.
Ah, exactly the picture. And it backfires hard, a few ways at once. You generate documentation thousands of pages long, and the important information just drowns in it. So you catch the real conceptual mistakes way too late at final testing, when it's too late to fix them inside the budget. And all that gold plating burns extra time when you finally try to deploy. So too little hurts you, and too much hurts you. Bad planning cuts both ways.
All right, doctor. How do we not do all this? What's the actual cure?
So the umbrella over everything is risk management. Recognizing, assessing, and controlling whatever could go wrong before it ever grows into a real threat. And here's the elegant little bit, the part I love. A risk is just a problem you spotted in advance, while you can still do something about.
So, a risk is basically a problem with a time machine.
A problem with a time machine? I'm stealing that! And that's exactly why the classic risk sources all look so familiar. You've met them already. Staff shortages, unrealistic deadlines and budget, building the wrong features. Gilding, again, it never leaves. An endless stream of requirement changes. Weak external components, same monsters as before, just spotted earlier while they're small, and three big concepts carry the modern prevention. The first, cranked up communication.
Meaning more meetings? That's everybody's least favorite word.
Ha! But aimed meetings. Here's the difference. The old methods talked intensely right at the start, then went dead silent for the whole long build, so what shipped had drifted way off from what the client actually wanted. Now you insist on regular, intense contact, mainly the client and the team. And the payoff is you catch the deviations early. A client who reviews the progress doesn't just find bugs, okay? They help you shape a better solution.
But hang on, can't too much client input actually slow you down?
Sharp. And the chapter warns about exactly that. Too much information can bury the client instead of helping. And an unprepared client firing off endless suggestions inflates every single step. Especially those endless requirement chains, new demands landing before the old ones are even built. So it's a balance, always a balance.
And a prototype that fits in here somewhere?
Right in the middle of it. A prototype is a skeleton, a primitive interface, work that's just simulated, and it gives the client the feel of the finished thing. Pure illusion, total smoke and mirrors, but enough to feel it under their fingers, way more directly than a spec document they only half understand.
Sounds great. So what's the catch? There's always a catch.
There's always a catch. 3 of them, actually. 1. The client fixates on the pretty interface and ignores the guts. 2. A too narrow prototype hides all the flaws in whatever it doesn't happen to show. And 3. Build it too fancy, and it eats up the very time it was supposed to save. Second big concept, iterative development. The old methods treated software as one whole product, designing every last thing in full, up front. Iterative flips that. You split the work into small chunks and only analyze and build each chunk when its turn actually comes.
So instead of designing one giant building all at once, you build it piece by piece?
You build a whole village. That's the picture. There's a rough big picture plan, sure, but you finish the houses one at a time, so any single piece can absorb big changes cheaply. It shortens the time from plan to done and shrinks the risk of a massive spec change blowing up on you mid-build.
And I'm guessing there's more than one flavor of iteration.
3 of them. Incremental, you add a brand new piece, like stacking blocks. Evolutionary, you improve a piece that's already sitting there. And combined, you do both at once. Oh, and there's a slick variant, by the way. You plan the iterations by deadline instead of by task. You fetch how long it'll take and how many people you've got, then pick the work by capacity. Time-boxed.
And the danger there? You ignore the future chunks and end up redoing stuff later?
That's one edge of it, yeah? But the opposite edge hurts just as much. If you try to account for every future iteration up front, your very first iteration gets as complex as the entire system. They call that inflating the step. And the whole approach just loses its...
Wait! Planning by deadline, fixed time boxes. That's an Agile thing, isn't it?
A lot of Agile methods push exactly that, and Agile gets its own chapter down the line, so this is the seed of it. Now, third concept, object orientation. The modern methods put objects up front, not processes, and the payoff is a much more stable model because business change swaps processes in and out way more often than it ever changes the objects.
And the thing that actually makes the object stable. What's that?
Encapsulation. You hide the implementation behind an interface, and most changes just stay local. Picture university enrollment. The process approach shatters it into a bunch of procedures all sharing data everywhere. So you kill the entrance exam, and the ripple is huge and totally unpredictable. The object approach localizes the data inside the objects, so that same change stays small and stays...
Hold on, those tangled dependencies everywhere. Isn't that the coupling idea?
Exactly, and the chapter literally says it'll define coupling properly over in the design chapter. So hold that thought. Lower coupling means one change drags fewer other things along with it, instead of setting off an avalanche. And that's exactly why object orientation fits iterative so well. More iterations mean more changes. So you want the method that breeds the fewest dependencies.
So next up is object orientation itself, then design, then Agile. It all threads through.
It all threads through. And here's the one idea to carry out the door with you. Practically every modern technique exists to beat down some specific risk. So, as we learn each one, the sharpest question you can possibly ask is, which problem does this protect me from?
What can go wrong, why it goes wrong, and how to dodge it. And step one, don't panic. Thanks, folks. Today's the big one. Object-oriented programming. The thing every intro course swears is the natural way to think about code.
And here's what I love. The chapter opens by trolling exactly that. The very first line is Dijkstra, okay? One of the giants of the whole field. And he says object-oriented programming is a terrible idea that could only have come out of...
Whoa, a giant said that.
On purpose. It's a provocation, not a joke. Because look at where OOP actually sits. It's the dominant paradigm today. It works in every single phase of development, front to back. And yet, it's the only great paradigm with no strict mathematical foundation under it. None. He's poking a real bruise, and we press on it all hour.
Okay, so before we dive, where does this sit in the course? What did we just leave?
Great question, because this doesn't come from nowhere. Right before this, we spent a whole chapter on why software projects fail, and this chapter is the industry's first real answer to that. And it all starts with the software crisis. Mid-60s, computers are suddenly everywhere, spreading like crazy, and the world needs way more programs than the old handcrafted artisan techniques could ever deliver.
So demand just outran our methods.
Demand outran the methods? Exactly. And the first fix was structured programming, a small, tidy set of clean control structures, expressive enough to write any algorithm you want, but simple enough that you could actually prove the code correct. And hold on to that phrase, okay? Prove it correct. Tuck it in your back pocket, because it's going to come back and bite us.
Why does it come back?
It bites us at the very end of the chapter, but I'm getting ahead of myself. So then people structured the data too, and somebody had the bright idea to fuse code and data into one single unit. And that fusion, that's the seed of OOP right there. Funny thing, by the way, early on, nobody even said class. They said main objects, modules, definitions. And C++ to this day says member function, not method.
Fuse what? It knows with what it does. So what actually is an object?
So, an object models some entity from your problem, a student, an order, a shape, whatever. And the chapter pins down 4 things every object should have, okay? An identity, a state, a behavior, and a lifetime. 4.
Unpack those for me.
Sure. Identity is what sets it apart from every other object. State is the values it's carrying right this second. Behavior is what it knows how to do. And lifetime, it's born, it lives, it dies. And here's the part I love. One old definition frames the whole thing as 3 little questions. Who am I? What can I do? And what do I know? That's an object.
Who am I? What can I do? What do I know? That's clean.
Right? Now, describing every single object by hand would be brutal, so you climb up 1 level to the class, which is just an abstraction over objects that are similar enough. And here's the subtle part that matters. They're similar by behavior, not by structure. Behavior, not structure.
Cookie cutter and cookies. But why behavior over structure?
Because, and this is the whole trap, 2 things can hold identical fields and behave nothing alike. You'll watch that blow up in a few minutes with a square and a rectangle. Now, the official definition from the Object Management Group is gorgeously circular. A class is defined through its objects, and an object is defined as an instance of its class.
Hold on, that's a circle. That's cheating.
It totally is, and the chapter flags it on purpose, because it's a preview of the entire OO world, where very little is nailed down to the last strict detail. Everything's a little loose. Tuck that away too, because the ending of this chapter is the bill coming due for exactly that looseness.
Structure lives in attributes. Behavior lives in methods. That's the split.
That's the split. And usually, it's rigid. An object's class is fixed the moment it's created and never changes. So it belongs to exactly 1 class, which ties classes straight to types, nice and tidy. But, and there's always a but, there are rebels out there.
Rebels? Name one.
JavaScript, for one. You can reshape a live object's methods on the fly, and the purists will tell you only those languages are truly object-oriented, and the rest of us are merely class-oriented. And get this, there's a data language, D, by Date and Darwin, where an object literally changes class in the middle of its life. Shrink a rectangle's sides till they're all equal, and it just stops being a
rectangle. It just switched teams. Wild! So what's the piece that protects me from myself?
encapsulation. And to feel why you need it, look at the old sin of the classic techniques. Every piece of data, every algorithm, wide open to every programmer. Anyone can reach in and touch anything. So it's trivial. Trivial. To break the rules and shove the whole software into an invalid state. And who's going to do that? Everybody. Eventually, everybody does.
So encapsulation is putting the fragile stuff behind glass.
Behind glass. Perfect. It hides the implementation, and the interface is the carefully chosen set of methods that lets you use the object without knowing any of those guts. And there's an iron rule: you never touch attributes directly. Ever. Every access goes through a method, so even a plain readable field gets wrapped in a little doorman.
A doorman? Even the simple fields? Isn't that overkill?
Depends on the culture, honestly. Java and C# hand nearly every attribute, a getter and a setter, the full ceremony. C++ pushes right back, keep them minimal. But here's the payoff, and it's huge. The author can rip out and rewrite the entire internals, and the users never feel a thing. The only thing that ever touches them is a change to the interface itself.
Give me the picture I can hold in my head.
A TV remote, okay? You care about the channel and the volume. You do not care, not even a little, how the electronics pull it off. A good interface gives nothing away. Nothing. And it scales way up past classes, whole components, whole services, each one hiding its own guts. And that's what lowers coupling and keeps the parts from tangling.
Coupling. That's a quality word, right? Feels like it's coming back.
Oh, it's coming back in a big way. Coupling and cohesion get their proper treatment in the design chapters coming right up. And here's a bonus. Encapsulation doubles as an architecture smell test. If a class's interface is a grab bag of unrelated jobs, split the class. And if one little task forces you to poke a dozen different classes' interfaces, you make a brand new class, a facade that hides all that mess behind one clean face.
A facade. Bet that's a pattern later.
Good ear. Facade is one of the design patterns just 2 chapters from now. And that's the thing about this whole chapter. It's quietly planting seeds for that entire catalog. You'll keep going. Oh, we met that already. Okay, so there are 4 core concepts in OO. Encapsulation, interface, inheritance, and the star of the show, polymorphism. And polymorphism's point is dead simple. I mean genuinely simple. Code you write once should work with different kinds of objects. Write it once, runs on many. That's the dream.
One piece of code, many shapes of thing. But there's flavors.
3 flavors. Hierarchical. Code for one class also works on all its subclasses. Parametric. You write it with no fixed type at all, and the type gets handed in later as a parameter. And implicit. No shared hierarchy, no parameter. The objects just happen to satisfy the behavior you expect, and that's enough.
And one of those is the everyday one, I bet.
The hierarchical one, the default in most OO languages, riding on inheritance, so that's the one we dig into here. The parametric flavor, by the way, is such a big deal, it gets its own whole chapter. Later, chapter 11, mark it down. But all 3 buy you the exact same prize, more abstract, more reusable code. One solution instead of one per type.
So how's inheritance actually defined?
Through the is-a relation, and it's precise. It's one-way and partially ordered class A is a class B if and only if every object of A has all the properties B's objects have. Then A is derived from B, A is the subclass, B is the base class, and the 2 directions have names. Going down to the special case, that's specialization. Going up to the general, that's generalization. Going up to the generalization.
Give me an example that sticks.
Students. A bachelor student and a master student each have every single property of a plane. Student plus some extras of their own. So each one is a student, clean as can be. They're the specializations. Student is their generalization. Now, remember that behavior. Not structure warning. It comes back with a vengeance right here.
Okay, how does it bite this time?
So, a square should inherit from a rectangle, right? Every square is a rectangle. That's just true. But watch what happens when somebody eyeballs the fields instead of the behavior. A square stores one side, a rectangle stores 2, so the rectangle suddenly looks like the special, richer one. So let's make the rectangle inherit from the square.
No. That's upside down.
Completely upside down. Because a square's behavior rules just don't hold for a rectangle. A rectangle's perimeter isn't 4 times one side, is it? The structure fooled you. The fields lied. And keep this square and rectangle pair front of mind, because at the very end of the chapter, it comes back as one of OOP's deepest, ugliest cracks.
Concepts are one thing. How do teams actually build with this?
Methodologies. And they really took off in the early 80s. Because the old structured design just couldn't carry the bigger projects anymore, it buckled. And here's the thing. A whole bunch of pressures shoved everyone toward objects at the same time, modeling entities with their state and behavior together, wanting more abstraction and modularity, these new visual user interfaces, machines starting to talk over networks, and everybody demanding shorter development cycles. All at once.
And it settles into a tidy story, or into chaos?
Chaos first, always chaos first. 3 overlapping eras. Era 1. The early steps, up to about 97. A swarm of rival methodologies, each one with its own private notation, most of them way too narrow to survive. But, and this is the beautiful part, nearly every technique we still use today was born somewhere in that swarm.
Okay, and Era 2?
Era 2 is the shaping of UML, roughly 95 to 2005.
UML, the diagram language we just did a chapter on.
The very same one. Good, you're connecting it. So, over at Rational, Booch and Rumbaugh merge their two methods. Jacobson jumps in 95, and out comes the RUP process plus one unified notation, UML. The first official UML in 97 closes out Era 1. Version 2.0 lands in 2005, and then comes Era 3.
Which is?
Post-UML. From 2000 on, people finally stop reinventing the notation, thank goodness, and the new methodologies, mostly Agile now, get built assuming UML is just there underneath.
Agile. That's a whole chapter down the road, too.
It is. And here's the fun part. It still leans on pieces of RUP even now. But the real, lasting win from UML is this. Developers finally understand each other with no notation mix-ups. Same picture means the same thing to everybody. So useful that even some non-object methodologies reach over and grab it.
Is there a shared shape to all these modern methods?
Two instincts, and every modern method has them. First, model everything with objects, watching four basic sets. Entities, that's your data. Subjects, the kinds of users, services, what the system actually offers, and interfaces, the doorways users reach the services through. And second, shorten the cycle. Everybody pushes iterative development, and Agile just goes further, pacing by deadlines and cranking the communication way up.
Entities, subjects, services, interfaces, data, users, offerings, doorways, locked in. The chapter's been pretty pro-OOP so far. When does it get honest about the downsides?
Right now, buckle up. So the old complaints were size, speed, and how much sheer programmer effort the thing ate. But those aged right out. Take Smalltalk, one of the first true OO languages. It struggled partly because it was big and slow. Then Java shows up in 95 with its virtual machine, literally the same architecture, and it succeeds. And the only real difference is 15 years of faster hardware.
15 years of Moore's Law did the work.
Moore's Law did the work. Pretty much all of it. And compilers got so good that C++ can actually be plain C on some things now. So slowness today is mostly misuse. Too many pointless abstractions. Not the paradigm's fault. Same story with databases. Relational engines chew on whole sets at once, but an OO program handles one object at a time, so you bolt on an ORM to hide the relational nature underneath.
And that ORM layer costs you?
If you're too strict with it, yeah. Every single access has to crawl from object to ORM to database and back. But those are all performance gripes, small stuff. The real problem is conceptual, and it's the root of everything. Every genuine weakness in OOP traces back to one thing. There is no mathematically precise definition of the concepts the whole paradigm is built on. None.
And the other paradigms have that?
They do. Structured programming, functional programming, relational databases, all sitting on firm, solid math. OOP just isn't, and in certain cases that leads to flat-out contradictions, real ones. And that is the actual Dijkstra critique, stripped of the joke. No formalization means you basically cannot prove your code correct.
And there it is. Prove it correct. The callback from the top of the show.
Full circle. Right where I told you it'd bite. OOP quietly gave that up. And it shows up as three classic problems. Count them with me. Problem 1, object identity is fuzzy. Can two objects hold the exact same contents and still not be the same object? If all their attributes match, are they secretly one instance? There's no clean answer, and it really hurts once you get into object databases.
Okay, that's 1. And 2, I'm guessing an old friend?
The square and the rectangle, back to collect their debt. Watch this. Give a rectangle a set width and a set length, fine. Now call set width on a square. Run the inherited method and only the width changes. So it just stopped being a square. So you override it to change both sides at once. Now it stays a square, but doubling the width quadruples the area so it's not behaving like a rectangle. Every door is locked.
So every escape route is a contradiction. Any fix?
No good one in ordinary OO languages. We only partly patch it over in the principles chapter, and even then, only partly. Now, Problem 3, and this one's sneaky hidden global state. Structured programming begged you to avoid global state, and OOP was supposedly built for that. Objects don't reach into each other. They politely trade messages instead.
But to send a message, you have to know the other guy exists.
And that's the whole catch right there. So all your objects quietly become one big connected graph. And that graph, that's the program's global state, sitting in plain sight, just wearing a disguise. Encapsulation hands each object clean state directly and a hidden tangle underneath indirectly. And here's the kicker. Structured code has the exact same tangle. It's just visible instead of tucked out of sight.
So is there any way at all to make OOP airtight?
One way, exactly one, make your objects immutable and treat identity as all attributes, being equal. Do that and it's consistent, it's provable, gorgeous. Except, here's the punchline. That's basically just how functional programming already works, with real-type theory holding it up. So the only true fix for OOP is to stop being
OOP, ha. Okay, bring it home.
in one breath. OOP was born from the software crisis. It fused code with data, and it gave us objects, encapsulation, polymorphism, and inheritance. Behavior over structure, always, every time. No formal proof, 3 honest cracks, and Dijkstra's jab was real, not just cranky. And yet, get this. Decades of practice show it's still the best, most reliable approach we've got. Which is exactly why the quote gets told as a joke instead of a eulogy.
Loose foundations, unbeatable in the field. And next, the design side, where these ideas become real principles and patterns. I'm in. Thanks, folks. Okay, big one today. We just spent a whole chapter on objects. So now what?
Now we design. And here's the thing. The whole chapter balances on one sentence. A software project is the plan the software gets built from. That's it. And Grady Booch opens with a line. I love the entire history of software engineering is the history of raising the level of abstraction. Okay, that's the melody, and it plays under everything we're going to say.
Wait, a plan? Like blueprints for a house?
Exactly the right instinct. But here's what's sneaky. The idea of a plan never changed. What changed is what goes in it and how you make it. Way back, you designed algorithms. That was the plan. Then came strict, separated phases. And now Agile blends the designing right into the coding. No clean line between them anymore.
And the plan's the same size every time? One size fits all?
No. It scales, and that matters. The scope of the project decides the number of models. A giant company's information system needs a rich, layered project. A tiny tool that does one clear thing? That fits on a couple of pages. Design isn't a fixed checklist. It flexes to the domain and to how complex the thing actually is.
So, where are we sitting on the course map right now?
Right past object orientation. So we've already got objects and encapsulation in our pockets. This chapter, this one, forges the raw vocabulary of design. And the next couple of chapters formalize it. First, the principles, then the patterns. We're laying the foundation everybody stands on.
So what's actually in designing? Where do you even start?
You walk 4 steps, from the domain all the way to the implementation. Step 1, explore the domain, the business, the users, what they actually need. Step 2, analyze the domain, build models of how it works, a domain class diagram, an activity diagram. Step 3, define the requirements, pin down exactly what the software must do. And step 4, design the implementation. You cross from the world of the problem into the world of code. Abstract the system, then functionally decompose it down to classes and interfaces. Explore, analyze, define, design.
4 neat steps in a row, except nobody actually works in a straight line like that, right?
Nobody. Never. Explore and analyze braid right together, and halfway through designing, you'll trip over some missing fact and jump straight back to requirements. Sometimes all the way back to exploring. Those are the dashed arrows on the diagram, the feedback loops. The steps interleave. They don't queue up politely.
Give me something concrete. What does that look like?
University enrollment. Okay? To To build software for it, your domain exploration has to map what already exists. Every step, what data comes from the candidate, what's pulled from the system, which clerk has which privilege. Because when you're automating a process that already runs, the whole game is understanding what's already there. You're not inventing new work. You're capturing work that happens today.
And those domain diagrams, that's the UML that's coming up, isn't it?
The very next chapter. UML is the notation you draw those class and activity diagrams in. Now, the results stack up in layers of abstraction. The whole system sits on top. Under it, components. The big functional parts. Under those, subcomponents, and you keep splitting until functional splitting runs out of meaning, and then you switch to a structural split into packages.
Hold on. Component, package. Aren't those two words for the same box?
Sharp. And no, genuinely different. A component is a functional unit, clear job, simple interface, a piece of functional decomposition. A package is just a logical grouping of classes used together, not functional at all. Think of every class in one syntax tree hierarchy, bundled up because they travel together. And a bonus you get for free, you start recognizing development tasks. Course design hands you a few big ones. Fine design hands you a swarm of small, trackable ones.
Does everyone walk those 4 steps the same way?
No. And here's where it gets interesting. The order and the emphasis come from your methodology. A development methodology is your whole way of seeing the project, which models matter most, in which phase you build them, which specialists make them. And they fall into 3 big groups. Classical, everything before object orientation. Strict, ordered phases, describing the business processes, structuring the project around them. Non-agile object around them. Non-agile object, oriented, the focus shifts from processes to objects.
So what's actually wrong with doing it phase by phase?
That's the waterfall. A one-way march, no going back. And that's the weakness, right there. You find an early mistake late, and now you're stuck choosing between 2 bad endings. Either you ship what the plan said, even though you know it's wrong, or you go back, which is brutally expensive. And the bigger the project, the bigger the risk you never finish it at all.
But hold on. Why are objects a safer bet? Objects change too.
They do, but 2 things save them. 1, processes come and go far more easily than objects do. And 2, changing a process cuts deeper because, remember, encapsulation from the object chapter? Encapsulation locks the consequences of a change into one place. Objects contain the blast radius. And Agile pushed this furthest. It assumes changing requirements are normal, so you delay analyzing and designing a piece until you implement it. And that, by the way, is exactly why the programmer analyst rose up. One person who both designs and codes.
One person wearing both hats. Makes sense. People throw around architecture and design like they're the same word.
And they're not. Design, it comes from the English word for project, is really the synonym for the whole software project, though today we use it narrowly for modeling the implementation. Architecture is the structure up at the high, abstract level. And here's the line that sticks. Write this one down. Every architecture is a design, but not every design is architecture. Design is the broader circle. Architecture is a smaller circle sitting inside.
So architecture is just the big picture subset.
Exactly. The load-bearing decisions. Now, you can't draw that boundary perfectly cleanly, but 2 criteria decide it: how far you've pushed the functional decomposition and how much a more detailed design would ripple across the whole system. And booch again. Architecture is the significant design decisions that shape the system, where significance is measured by the cost of change. If it's expensive to undo, it's architecture.
So cost of undoing it is the tell.
That's the tell. And there's a classic trap here, okay? People reduce architecture to just the functional decomposition, then dump everything structural into, we'll design that later. Looks clean on a whiteboard. but it ignores how much the detailed design actually shapes the whole thing, and you end up with a rigid architecture that makes you pay for it later in expensive changes.
You keep saying abstract and decompose. Are those the two big moves?
The two moves, and they alternate back and forth the whole time. Abstraction buys you generality, you generalize, you ignore the details that don't matter. Decomposition buys you structure, you introduce detail by finding the smaller pieces inside. And here's the elegant part. Abstraction comes in 4 flavors, each with an opposite that's a flavor of decomposition. Classification. You spot the class behind a set of objects. Opposite, instantiation, making one concrete instance. Generalization, you derive a base class. Opposite, specialization.
Whoa, hang on. Say those 4 back to me. Classify, generalize, shape a service, compose.
That's the 4. And the timing matters too. Early on, you're mostly composing and shaping services, spotting components, drawing interfaces. Later, carving out the insides. That's when you classify and generalize. Different tools for different moments.
And decomposing? That's just breaking things up? Or is there more to it?
There's more. And it matters. 3 ways. Functional, you split into components, each with a clear function, as self-standing as you can make it. Logical, you split into packages, things developed together or structurally tangled, not necessarily functionally related. And by variability, you hunt down the points of variability, the spots where change is likely, and the axes of variability, the directions change tends to spread. And then you split those change points apart into different components.
Points and axes of change? Okay. Give me the functional example.
Electronic ordering, beautiful example. The ordering component splits into 3 independent pieces. Warehouse reserves the product. Payment handles the money. Delivery estimates the cost and schedules the drop-off. Each with a clean interface, no overlapping responsibility. But watch the trap. Inventing functionality just to get a prettier split. And the telltale sign? You name a component, but you keep putting off its interface. No clear interface usually means no clear function.
So how do you keep yourself honest about that?
Well, Lowy goes all the way and says, skip functional decomposition entirely, just go by variability. But the real, grown-up advice is to combine them. Do the functional split first, then turn right around and grill it from the angle of, okay, what here is actually likely to change?
All right. How do you actually know a design is good?
2 ways, qualitatively, comparing traits, and quantitatively, with real numbers. The numbers are the job of software metrics, development metrics track the process, design metrics put a number on the design itself. And the good traits? They stack in 3 layers. Layer 1, everybody sees, correctness. It does exactly what the spec says, and efficiency. It stays inside the planned resources, processor, memory, storage, and lately, get this, even energy.
Right, correct, and fast. That's the stuff the user actually feels.
Exactly. That's the surface layer. Layer 2 is all about reuse, because reuse pays off huge for very little effort. Flexibility. It adapts to new circumstances with little or no change. Extensibility. You grow it by adding new pieces, barely touching the old ones. And modularity. It's built from well-decomposed modules, each with a clear function. And modularity is the prerequisite for both of the others, and for Agile work besides.
Okay, and layer 3?
Layer 3 is the subtle one. Modularity alone doesn't guarantee the pieces actually connect cleanly, so you want more. Separated responsibilities, precise interfaces, consistent encapsulation, and the 2 stars of the whole show, high cohesion and low coupling. There's even a thing called interface width, the number of connection points and parameters. And a wide interface is a red flag. The component's doing more than one job, or the responsibilities got split badly.
You've been teasing those 2 the whole episode. Time to pay up.
Time to pay up. These are the two most important traits of a software design. Practically every principle and every pattern comes down, in the end, to balancing these two. Cohesion, how tightly the elements inside one module belong together. Coupling, how tightly elements in different modules depend on each other. And the creed, in one line, good design is high cohesion plus low coupling. And you measure both at every level.
Tight inside, loose between. And this is that grasp thing that's coming up next, isn't it?
The very next chapter. There, high cohesion and low coupling literally become GRA's principles, the tiebreakers for who gets a given responsibility. Here, they're the measuring sticks. There, they get a job to do. Now, cohesion comes in 7 kinds, best to worst. Functional, everything cooperates on one function, nothing spare. The ideal, and exactly where decomposition should stop. Sequential, one piece's output feeds the next. Communicational, they all share the same data. Procedural, steps of
7 kinds. Okay, run them back at me, fast.
functional, sequential, communicational, procedural, temporal, logical, coincidental, ideal all the way down to garbage. And a nice little detail. That procedural one shows up as the controller-control pair, where a controller builds one complex operation out of a class's loosely related methods, like the string class or plain old file operations.
Now, coupling. And there the goal's obvious. 0, right? No coupling at all.
That's the trap. No. Zero coupling means a component's completely isolated, and a system with no coupling isn't a whole at all. It's just a pile of separate parts sitting next to each other. The goal is coupling with good characteristics, not none. Good. So how do you rate it? 3 kinds, worst to best. Logic coupling. One module knows and leans on another's implementation. A gross break of encapsulation through sharing information or sharing assumptions. Type coupling. You use a concrete type from another module. And specification coupling, you depend only on the abstract interface through polymorphism. And that's
Program to the interface, not the guts. That's got its own chapter later too, doesn't it?
its own whole chapter. And from C++20 on, concepts let you formally specify a template interface, specification coupling too. And there's a whole spectrum of coupling levels, graded by how heavy the shared content is. At the worst end, you're reaching straight into another module's internals. At the lightest, best end, you're passing just a single message, no data at all. The less you hand over, the cleaner the seam.
So the less you share, the better. Got it.
Exactly. And a few finishing traits. Direction, one way is best. Two-way and circular, just tangle everything up. Width, keep it narrow. And manner. This one's important. Static coupling is written into the code before it ever runs, like inheritance or a member object. Dynamic coupling gets wired up at runtime. Static is more intense, less desirable, and modern development leans hard toward dynamic. The poster child? Event-driven development. Signals and slots in Qt, wired up on the
Signals and slots. Let me guess, that's a whole chapter down the road.
way down the line. Event-driven architectures get their own chapter, and this dynamic coupling is your first taste of why. Now pull it all together, and you get intensity of coupling. It climbs higher for logic over specification, for heavier levels, for wider, for circular, for static. And yes, you can measure it. Coefficients per pair, per component, for the whole system. Design metrics bleeding back into design. And, you guessed it, metrics get their own chapter too.
And the actual shapes these couplings come in?
Topologies. 5 common ones. Client-server is closest to the ideal. One way, narrow, low. Circular is the hardest of all. Two-way, potentially wide. It blows up the complexity and blurs who's even responsible for what. And in between, sit 3 more. Hierarchy of ownership, coupling through an interface and coupling through method parameters.
So underneath all the principles and all the patterns, it really just comes down to those 2 knobs.
That's the whole chapter in one breath. A project is a plan. You build it by abstracting and decomposing. You judge it by its quality traits, and the two that rule them all are high cohesion and low coupling. Jack Reeves nailed it back in '92. Programming itself is an act of design. And next up, UML. The notation to actually draw every bit of this.
From a blurry idea to boxes and arrows. Let's go. Thanks, folks.
New explainer. And honestly, this one's the Rosetta Stone of the whole field, okay? Here's the thing. Every single person on a project, the coders, the testers, the client who's paying the bill and never wrote a line of code in their life, they all need one shared way to describe the system. And the shared language everybody landed on, the one that won,
UML. Even I know that one.
Then you already know a giant. I mean it. The chapter puts UML right up there with structured programming, object orientation, relational databases, things so universal, software is basically unthinkable without them. And here's my favorite tell of a truly mature language, okay? It's grown up enough to describe its own grammar. And the notation it uses for that grammar? Get this. It's itself. It's itself.
Wait, a language that describes its own grammar? That's a snake eating its own tail.
It kind of is, and it works. UML was born mostly between 1995 and 2000, and the standard's kept by a group with the greatest villain name in all of tech, the OMG. But here's the one thing to hold on to above everything else. UML is first and foremost a picture language. The text just annotates. Nearly everything you do is a diagram you draw.
Okay, so where does this sit in the course?
Great timing question, because it sits right in the middle of everything. Chapter 4 just handed us the raw design ideas: abstraction, decomposition, cohesion, coupling. And all UML is really is how you draw them. And the next 2 chapters, principles and patterns. You're going to sketch every single one of those as a UML diagram. So learn the alphabet now, okay? And you get to read the novels later.
Learn the alphabet now, read the novels later. I like that.
That's the deal. And here's the very first fork in the road. Every UML diagram is one of exactly 2 things, structural or behavioral. The structural ones freeze the parts in place. They've got zero notion of time, okay? It's pure anatomy. The behavioral ones are the flip side. They live in time, messages flying around, states changing, communication flowing. 2 families, structure and behavior. That, right there, is your whole map.
All right, lay out the whole family for me. Structural first.
7 structural diagrams. Count them with me. Class, that's the star, the static model of your classes and how they're all tied together. Object, a snapshot of real, live objects at one single instant. Package, that groups the logical model and shows you the dependencies between the groups. Composite structure, the guts, the innards of one single element. Component, functional pieces, each with a public interface. Deployment, the physical machines and what actually runs where. And profile, that's you bending UML itself to fit some special domain.
That's 7, and my brain's already full.
Ha! But catch the rhythm, because the rhythm is the whole point. Package splits the system logically, component splits it functionally, deployment splits it physically. Same system, okay? 3 different lenses. Now, the behavioral family, use case, activity, state machine, and then a special little club called the interaction diagrams.
Interaction diagrams? Why do those get their own club?
Because on those, time isn't just present. It's spelled out, explicitly, front and center. There are 4 of them: sequence, communication, whose older name, by the way, was collaboration, timing, and the interaction overview. So say the whole thing back with me, okay? Structural is the anatomy. Behavioral is the movie.
And the interaction diagrams are the movie with a stopwatch running. Locked in.
Locked in. You've got the map. Now let's spend some real time on the class diagram, because it's the most used one, full stop, no contest. Here's the shape of it. A class is just a rectangle, and you slice it with horizontal lines into 3 shells. Name up on top, then the attributes, your data, then the methods, your behavior. Name, data, behavior, top to bottom.
Okay, and how do I mark what's private versus public?
Little signs right on each member. A minus means private, a plus means public, a hash mark means protected. And the types? The types are optional. Oh! And if the class has to obey some special rule, you can add a fourth shelf just for constraints, written in plain words or in formulas. But honestly, most of the time, you'd rather leave things out than cram them all in.
Wait, why would I ever want to hide the types?
Because less is more, okay? When the diagram's crowded and the whole point you're making is about the relationships, the types are just noise, so you strip it right down to the names. There's one rule, though, and it matters. If you hide something, you have to say you're hiding it. Otherwise, people look at your diagram and just assume the thing doesn't exist.
Fair. Now, the lines between the boxes.
6 relationships, and each one gets its own little end mark, so you can tell them apart at a glance. Inheritance is a hollow triangle pointing at the base class. Interface implementation is that same triangle, but on a dashed line. Aggregation is a hollow diamond sitting on the container. Composition is a filled-in diamond. Association is just a plain line. And dependency is a dashed line. The weakest of the whole bunch. The weakest of the whole bunch.
That is a lot of diamonds and triangles.
It is! So let's untangle the 3 that trip absolutely everybody up. Aggregation, composition, association. I call these the confusing cousins. Let's do the diamonds first. Aggregation is the weak one. The whole holds the parts, sure, but the parts can go off and live on their own just fine. Think a car and its wheels, okay? Total the car in a wreck, and those wheels still roll away down the street.
And composition's the clingy one, then.
Composition is strong integration. You destroy the whole, and the parts die right along with it. And get this, a part can't even be brought into existence without knowing which whole it belongs to. Classic example. An order, and its line items. No order? Then there are no items. They don't exist without it.
Okay, and plain association?
The loosest of the named links. It's one-directional if only one side actually holds the reference. You draw that with a little navigation arrow, or 2, directional if both sides do, which is honestly redundant. But it's allowed. And then dependency, the featherweight, is looser still. No lasting link at all. One class just has to know another exists, because it uses it in passing. The textbook case is a list and an iterator. The list never stores the iterators, it just hands them back as results. More declarative than structural, barely a connection at all.
Hold on. Didn't composition show up back in the OOP chapter?
Sharp? Yes, it did. Composing objects. That's straight out of object orientation. Here, UML just gives it a precise symbol to draw. And here's a handy little tip, by the way. Since aggregation says a bit more than a bare association does, upgrading a one-way association into an aggregation will very often make your model that much richer. Basically for free.
Hey, so how do I say something like, a team has 5 to 11 players?
That's cardinality. You put a number by each end in this from ... form. So 10 ... 20 means anywhere from 10 to 20 objects. 1 ... star, and the star means no upper limit, means at least 1 and up. And if the 2 ends are just the same, you write a single number. Simple as that.
And those little angle bracket tags I keep seeing everywhere?
Stereotypes, a word tucked in double angle brackets right before the class name. You got abstract, interface, entity for stored data, enumeration for a value type, focus for the actual star of the diagram, auxiliary for a little helper. And look, since one single drawing can never show you everything, there are 4 flavors of class diagram, domain, that's data only, no methods, interface, public methods, but no attributes, implementation, all the methods, no attributes, umbrella, and detailed, which is the works, everything at once.
So, 4 zoom levels of the exact same class.
4 zoom levels. Exactly. And it's that same abstraction and decomposition move from Chapter 4, just aimed at a single diagram now. Like, the interface view of a list drops the element class entirely, but it keeps the iterator. And why? Because iterator is the return type of a traversal method. It earns its spot.
You keep teasing the object diagram. What's it actually for?
It's a photograph, okay? The class diagram gives you the rules, the general laws. The object diagram shows you actual objects with actual values at one single frozen instant.
Nice. Makes the abstract thing real. Okay, what about components?
So a component is a piece of software with one clear job. And notice, we design it exactly the way we design a class. Single responsibility, encapsulated, the interface pulled out front.
Single responsibility. Hold on, isn't that a headline in the principles chapter?
Good ear! Same exact principle, just at a bigger unit. Components only ever connect through their interfaces, and one component can offer up several of them. Now in the picture, a provided interface, one it offers, is drawn as a little circle on a stick, a lollipop. And using it is a socket, or an arrow reaching out for that circle. Older UML drew two puzzle piece tabs. UML2 cleaned it up into a box with a little puzzle icon over in the corner.
Provides a plug, needs a socket. And this is that functional split you mentioned earlier?
Functional decomposition, exactly right. What each piece does and how everybody else reaches it through its interface. That's the whole idea.
All right, so how's a package different from a component?
A package is a logical group, and in a modern object-oriented language, that's basically just a namespace, okay? The package diagram shows you which elements live in which group, and how the groups depend on each other. So remember, component was functional, package is logical. Same system, a different cut through it.
And what decides what actually goes into a package?
Ah, lovely criterion, this one. Things that are semantically related and that change together, right? If touching one part of it usually drags the rest along with it, then you keep them together in one place.
Wait, that's the cohesion idea from Chapter 4.
It is cohesion, straight up. And here's a little preview for you. It comes right back as a proper named principle, common closure, in the very next chapter. But for now, the drawing's simple. Draw the box, name it, show the dependency arrows, and optionally list the classes inside. Done.
Okay, and deployment. That one sounds like the server room.
It literally is the server room. So component is functional structure, right? Deployment drops all the way down to the physical architecture. And remember, architecture versus design from Chapter 4? This right here is the architecture side of that line. You draw nodes, servers, clients, devices. You drop each software component onto whichever node runs it, and then you connect up the communication lines between them.
So this is basically the picture you hand to whoever's buying the hardware.
That is exactly the audience, what runs where and how the machines talk to each other. Nothing more, nothing less. Okay, on to behavior. The use case diagram shows you how whole groups of users touch the system. Your actors are stick figures, each one with a name. Each use case is an ellipse, one complete interaction. And it's joined to its actors by plain lines. No arrows, nothing fancy.
Honestly, that sounds way too simple to be useful.
And that is exactly the trap, okay? The chapter literally calls this thing the tip of the iceberg. The diagram is just a little sketch floating on the surface. All the weight, all of it, is down in the text underneath. Every single use case needs a thorough written spec, or you've got nothing you can actually build from.
So what has to go in that write-up?
The name, The actors, a short description, preconditions, postconditions, the main flow spelled out step by step, then the special cases, and any supporting diagrams. Take a real one, applying to a competition. The candidate brings the forms. The clerk checks them and enters them, prints it out, the candidate signs. And then the alternate flows. Foreign paperwork, previous prize winners, and so on.
Wait, preconditions and postconditions? That's the Liskov thing coming up.
Same vocabulary. Really sharp catch. It's a contract, okay? What holds true before? What holds true after? Here it frames a use case. Over in the principles chapter, that same idea governs subclasses. One vocabulary, two jobs. And then there are two links you can draw between cases. Include, which is when one case swallows another that gets reused. A lot. That one always runs. And extends, which is an optional add-on that only sometimes bolts on. Both are dashed arrows with a label.
Include always runs, extends only sometimes shows up. Got it.
You got it. And the beautiful thing is, use cases scale, all the way up and down. From a giant business case like student studies at the top, right down to one tiny activity with a recognizable result. Small enough that you can build it fast. Okay, save the best for last. The sequence diagram, where a use case finally turns into something runnable. And here's what I love about it. The geometry itself carries meaning, okay? Vertical is the flow of time, top to bottom. Horizontal is one column per object, and each object drops a dashed lifeline straight down the page.
So the objects stand side by side, and time just falls down the page.
Time falls down the page, exactly. Now, on each lifeline, sit these thin little activation frames. A frame opens the moment a message arrives, and it closes once that message is handled. The messages themselves are arrows shooting between the columns. A create message spawns a brand new object, and an X at the bottom of a frame, that kills it off.
And when something answers back,
you draw a return arrow going the other way. You can skip it, honestly. But you draw it when the call is synchronous, meaning the sender's just sitting there waiting, or whenever the result actually matters. And at the very lowest level, you draw every single message. So at that point, the diagram basically is the implementation. The textbook example is walking an expression graph, constants, operator applications, library calls.
Hold on. That expression graph, isn't that the visitor example?
Same expression tree that turns into the visitor pattern later on. You caught the whole thread. And look at the pipeline here, okay? A use case flows into a sequence diagram, and the sequence diagram flows into real, actual methods. That's the whole assembly line, right there. Now, the communication diagram. Same objects, same messages. But it emphasizes the structural layout, who's talking to whom, instead of the exact timeline.
So, same conversation, different highlight.
Order versus arrangement. That's the whole difference. And the very last one, the interaction overview, that's a flavor of activity diagram where each node can itself be a whole other diagram. So a giant, sprawling process just collapses down into one bird's eye view.
Okay, bring it home for us.
One breath. Here we go. UML is the shared language, and it splits into structural, class, object, package, component, deployment, and behavioral, use case, sequence, communication, and all their kin. And here's the thought I want to leave you with. What Esperanto never quite managed to pull off for human speech, UML basically pulled off for software. One language, and everybody reads the same picture. Oh! And modern tools will even generate your class skeletons right from the diagrams and go backwards too.
Draw the picture, get the code, and next up, we start drawing real designs, the principles chapter. I'm in. Thanks, everybody.
Okay, another explainer, and I love this one. The question, how do you design software so that 6 months in, it hasn't rotted into one giant tangled mess? Because left alone, it will, okay? Code decays. It's
A mess. Yeah, that's just called my code.
Ha! You're an excellent company. And get this, the chapter opens with Dijkstra himself, one of the giants of the field, and his whole thing was, we are always fighting chaos, and the smartest move is to stop the chaos before it ever forms. You don't clean up the mess, you prevent it.
Okay, so what even is a design principle? Sounds fancy.
Honestly, nothing fancy. Think of little forks in the road while you're building. Where do I put this responsibility? What do I bundle together? Who leans on whom? A principle is just tested advice for those forks. Decades of it, handed to you for free. And here's the thing people miss. It's advice, not law. These things overlap, and sometimes they flat out contradict each other.
Wait, hold on. The rules fight each other?
On purpose. It's the collected wisdom of the best programmers who ever lived, okay? So a beginner gets to borrow experience they haven't earned yet, and it comes in 3 famous sets. Solid, for shaping your classes. Grasp, for deciding who's responsible for what. And a 3rd set for grouping everything into packages. 3 sets. Tuck that away, we'll keep circling back to it.
And some of those sound almost too obvious to bother saying out loud, no?
They do. And the chapter calls that out on purpose. Trivial doesn't mean unimportant. We name the obvious ones precisely because obvious is exactly the thing we all overlook.
Okay, let me lock it in before we move. Solid, grasp, packages, 3 sets.
That's the whole map. Solid shapes classes, grasp hands out responsibility, the package set groups it all up. Tuck it away. We live here for the next hour.
And where are we sitting in the course right now?
Right in the thick of it. The design chapter just before this handed us the raw materials, abstraction, cohesion, coupling. This chapter forges those into named principles. And the very next chapter, design patterns? That's basically these same principles worked out as ready-made examples. You could even draw every one of these designs as a UML class diagram. That notation from a couple chapters back. It's all one story. All right, solid. 5 principles, 1 per letter, and I'm genuinely excited, so bear with me. S is single responsibility. Plain version, a thing should do 1 job. 1. So it has exactly 1 reason to ever change.
1 job. Don't make 1 class do the work of 5.
Exactly. Picture this. You write math as a tree. So 2 times the square root of 25s becomes a little tree of objects, literals, operators, all wired together. Their 1 job is to hold that structure, okay? Now get greedy. Make each node also translate itself to machine code, print itself, evaluate itself. And what happens? Every node balloons.
So how do you slim it back down?
The visitor pattern, and it's beautiful. The tree keeps its 1 job. Each extra job, printing, evaluating, becomes a separate visitor that strolls through the tree without even knowing how the walking works.
Tree stays a tree, chores move out. Okay, what's O?
OCP, open closed. Here's the idea. You add new behavior without ever reopening and editing the old stuff. Not even a ship binary. Open for extension, closed for modification. You pull it off with inheritance and abstractions. You extend by writing brand new derived classes, and the old code never gets touched.
New stuff without cracking open the old stuff. Okay, but what's the catch? There's always a catch.
There's always a catch. It's this. Don't abstract ahead of time. Every abstraction adds weight, okay? So if you build every hook you might someday want, the code just drowns in machinery nobody uses. Add abstractions only when you're actually sure, and when you guessed wrong, and you will, you go back and refactor.
Refactoring, that's a whole chapter later, isn't it?
It is, chapter 10, and that's the punchline. Refactoring is how you earn open-closed after the fact. You reshape the code so the next change is a clean add-on instead of open-heart surgery. The first visitor costs you 1 edit, and then every visitor after it is basically free.
So you pay once, then you coast. I like that trade.
L is Liskov substitution. And get this is the one that makes polymorphism actually mean something. The idea, if something claims to be a kind of X, you should be able to drop it in anywhere. And X is expected. And nothing goes weird. Nothing surprises you.
A stand-in has to actually act like the thing. This is the square versus rectangle one, right?
The classic. Okay, make square a subclass of rectangle. Sounds fine, right? A square is a rectangle. Now a function sets the height to 3, the width to 5, and prints the area. For a rectangle, you get 15. Now run that exact same code on a square. Watch.
Please tell me it's still 15. Please!
25. Because a square has to stay square. So the moment you set the width, it secretly yanks the height along with it. Same code, different answer. The principle just shattered.
So a square's a rectangle in math class, but a liar as an object. What's the actual rule?
Here's the rule, and it's precise. When you override a method, what you demand up front, the preconditions, must be the same or gentler. And what you promise afterward, the postconditions, the same or stronger. Ask for less, deliver at least as much. The square breaks that it silently drops a promise the rectangle made.
Is there any clean way to fix it?
No perfect fix, honestly. The cleanest move is a single set width and height method that throws on bad input. It obeys Liskov, and it pays for it with a narrower interface. There's always a trade.
And this is basically the polymorphism idea from the OOP chapter, yeah?
Exactly. Liskov is what keeps polymorphism honest. And by the way, polymorphism is so central, it gets a whole chapter to itself later on. Liskov is the rule that makes it safe to lean on.
Okay, and
ISP, interface segregation. And this one's pure courtesy, honestly. Don't force people to depend on buttons they never press. You take a fat, do-everything interface and split it into small, focused ones. It gets broken when one class is juggling too many jobs, or when you bolt methods onto a whole family of classes when only one branch actually needs them.
Don't make everyone carry a tool one guy uses. Is there one we just live with?
Yes, and I love that the chapter's honest about it. String. Its real essence is reading and changing text. All that searching machinery could have just been plain functions off to the side. It technically violates interface segregation, but the library is rock solid, stable for years, so we tolerate it. And notice that visitor fix from before? It quietly respects this one too. Narrow interfaces everywhere.
And D, bring us the finale.
DIP, dependency inversion. My favorite, I'll just say it. Plain version. Don't nail your high-level code directly onto the fiddly low-level details. Instead, have both of them lean on a shared abstraction sitting in the middle. Program to interfaces, not to implementations.
And why call it inversion?
Great question, because normally the general thing leans on the specific thing, right? But at build time, you flip the arrow. Now the concrete detail leans on the abstraction.
Hold on. That's a contradiction. You build the abstraction out of the details, but the details depend on the abstraction?
And that tension right there is the whole magic, because there are two different kinds of dependency. Let me make it concrete. Picture printing a report in 3 formats: plain text, HTML, and text. The clumsy way, one giant method full of if it's HTML do this, else if it's TX do that, and every new format means reopening it. DIP slides a format abstraction into the middle with a title method. EML format fills it in, TML format fills it in, and the builder just asks, format.title. And now every single arrow points from concrete toward abstract.
So the boss just says, give me a title, and each format handles its own thing. Way cleaner.
Exactly the trade. And there's an alternative flavor, by the way. Parametric polymorphism, templates, or concepts in newer C++. Best when your objects already live in separate families you can't merge. But same spirit.
Okay, before we lose it, run solid back for me. All 5.
Love it. This is how it sticks. S, single responsibility. One, job. O, open, closed. Extend, don't reopen. L, Liskov, a stand-in behaves itself. I, interface segregation, keep interfaces skinny. D, dependency. Inversion. Lean on abstractions.
SOLID. One job, don't reopen, stand in cleanly, stay skinny, lean on abstractions.
You just earned the t-shirt. That's set 1. Done. Now, set 2. GRASP.
Solid shapes classes. So what's GRASP?
A very human question. Who is responsible for what? It stands for General Responsibility Assignment Software Patterns. A responsibility, formally, is just what an object knows plus what it can do. First one, information expert. Give the job to whoever already holds the information. Split the knowledge from the work, and you invite needless chatter back and forth and messy coupling.
Wait, doesn't that clash with the SDD string thing you just told me?
Sharp catch. And get this, the chapter says exactly that itself. Stud. String breaks interface segregation, but it honors information expert because all the info about the text lives right there inside the string. So here, they let expert win. It's a judgment call. Every single time, a judgment call.
So the principals fight, and you're the referee. Okay, next.
Creator. Common sense in a suit. Whoever already builds, holds, or feeds an object should be the one that creates it. Formally, Class B creates Class A if B contains them, aggregates them, closely uses them, or has the data to initialize them. Lovely example. Abstract factory. A factory with make window and make button, quietly picking the right concrete class for you.
Whoever's already holding the pieces assembles them. Got it.
Now, 2 heavyweights, and I mean heavyweights. High cohesion and low coupling. Cohesion is how well the stuff inside one box actually belongs together. You keep that high. Coupling is how tangled up separate boxes are with each other. You keep that low, and
Hang on. Didn't we already meet cohesion and coupling somewhere?
you did, back in the design chapter. But there they were, just marks of a good design, qualities you admire from a distance. Here, GRASP puts them to work. They become the actual tiebreaker for who gets a given responsibility. Same idea, now with a real job to do.
Tight on the inside, loose on the outside. A good team, not a codependent one.
Ha! Exactly the vibe. Last one here. Controller. A system event comes in. A user clicks, a device fires a signal, and you hand it to a class that stands in for the whole system, a facade controller, or a per-use case one named like order handler or order session. That's the C in MVC and in PAC. And in Qt, by the way, slots play exactly that role, wired per object, so 2 objects of one class can serve 2 different forms. 4 more, quick. But these are gems. Don't tune out. Polymorphism. When behavior changes with the kind of thing, spread it across the kinds, instead of one big switch on a type tag. The classic move is literally called replace conditional with polymorphisms. You turn that switch into a family of classes, 1 per case. And really? It's just DIP wearing a different hat.
Kill the switch. Let each type know its own moves.
Exactly. Next, fabrication, or pure fabrication, and I love this one. Sometimes you invent a class that doesn't exist anywhere in the real-world problem at all, purely to get clean cohesion and loose coupling. It's the secret behind facade, adapter, and the fancier ones like visitor and decorator.
So you're allowed to add a character who's not even in the book if it makes the story cleaner. Kind of like me on group projects.
I'm going to keep teaching. Then indirection, a middleman. Instead of a knot where everyone talks to everyone, in circles, you route it all through one go-between so no 2 parts touch directly. Abstract factory, adapter, bridge, facade, they all lean on this?
A switchboard operator, so nobody needs anybody else's number.
That's it, exactly. And I save the best for last, protected variations. You find the spot in your design most likely to change, and you wall it off behind a stable interface, so when the change comes, it stays trapped in that one spot. The chapter calls it one of the most important principles, period. Because almost every pattern and every refactoring is really just this one idea in a different costume.
So half of these are secretly the same instinct. Wall off the parts that wobble.
You just found the thread running through all of it.
Okay, roll GRS back for me, same as before.
Here we go, one breath. Information expert, creator, high cohesion, low coupling, controller, polymorphism, pure fabrication, indirection, and protected variations. 9 of them. But really? One question. Who does what, and how do we keep it all loose?
Put the work where the facts are. Keep it cohesive. Wall off the wobble. That's set 2.
Exactly. Which leaves set 3, the package principles.
Last set, the big boxes, packages and components.
Now we zoom out. Grouping principles chase cohesion. Separation chases loose coupling. First, REP. Reuse. Release equivalence. If you want people to reuse your stuff, you owe them a published, stable, sealed interface. A reusable chunk is a release chunk, okay? Then, CRP. Common reuse. Classes used together should live together. Should live together. Use one, you'll use them all, like keeping that whole expression. Tree family in one package. And the flip side. Don't force unrelated strangers to be roommates.
Share it. Version it. Don't make strangers share an apartment. What's the third grouping one?
CCP. Common closure. So practical. Keep together the things that change together for the same reason. Those report formatting functions. They're independent, but they all lean on the format specin. So change the format, and a bunch of them shift at once. Group them, and that change stays in one tidy spot. Now, separation.
Don't build your house on the guy who keeps redecorating.
Ha! Perfect! And get this, SDP doubles as a smoke detector for bad design. The facade is the classic trap. Everybody leans on it, so it had better be stable, but it's wrapping unstable classes underneath. You fix it with an abstract interface. Then SAP, stable abstractions. A unit should be as abstract as it is stable. And ADP? Acyclic dependencies, no dependency, loops between packages. A loop sends a change chasing its own tail forever.
I'm guessing there's a famous loop you're about to hit me with.
The best one. MVC itself is a loop. Watch. The controller updates the model tells the view, and the user drives the controller through the view, round and round. And here's the elegant escape. You break the circle with abstraction. The view2 model link goes through the observer pattern, and the view2 controller link goes through event-driven programming.
Event-driven? Is that a big deal later on?
A whole chapter's worth. Event-driven architectures get their own chapter down the line. And breaking this MVC loop is your very first little taste of it.
So even the textbook architecture needs untangling. Okay, bring it home.
In one breath, Solid shapes your classes, deGrasse decides who's responsible, and the package principles group and separate whole components. But remember, Dijkstra. None of these are laws. They overlap. They clash. They're seasoned advice for sniffing out the weak spots before chaos ever moves in.
Fight the chaos before it forms. And the best examples of all of it? Design patterns and refactorings, which is exactly where we're headed next. I'm in. Thanks, folks.
All right, brand new episode, and I'm fired up. Last time we built a whole toolbox of principles for keeping code clean. Today, we cash them in, because software has this maddening habit, okay? The same problems come back at you again and again, but never in the same clothes.
So the same bugs keep haunting me. Comforting.
Ha! The same problems, not always the same bug. Here's the split. When a problem repeats word for word, easy. You pull the code into a function or a library, done. But when it comes back with variations, finished code won't fit anymore. What carries over isn't the code, it's the way of thinking.
So I can't copy-paste the solution, but I can copy-paste the idea.
Beautifully put. You just said the whole chapter in one line, and you know why a library can't be frozen solid. Our old friend, the open-close principle. A good library has to allow extension, and the usual way is polymorphism, straight out of the object orientation chapter. It all connects.
Wait, how similar is similar enough, though? That sounds squishy.
It sounds squishy, but the book makes it razor sharp. You model each problem, build an abstract picture of it, and two problems are similar if you can map one model onto the other. Now, if that mapping runs both ways, bijective, a clean round trip, then the same model describes both problems equally well, and we say they're equivalent with respect to that shared model.
Okay, but couldn't I cheat? Crank the abstraction up till everything looks the same?
You walk straight into the trap, push the abstraction high enough, and any two problems match. Gather your resources, do the computation, print a report. See? That describes a tax program and a video game. Technically true. Completely useless.
So there's a sweet spot in there somewhere.
There's a sweet spot, and it splits equivalence into four kinds by how abstract the shared model is. 1. Repeated problems, almost no abstraction, the same code, reach for a library. 2. Implementation equivalent, low abstraction, the same implementation. We've done that since day one of programming. 3. Trivially equivalent, abstraction cranked to the sky, worthless. That's the gather, your resources thing. And then, in the middle, the gem.
And the middle one's the money, I'm guessing.
The middle one is the money. Conceptually equivalent, moderately high abstraction. Too different to share the code, but similar enough to share the idea. That's the whole target of this chapter. And where does it sit on the map? Right after the principles chapter. Because this is those principles worked out into real, living examples.
So, the shared solution is an idea, not code. Doesn't that feel a little soft?
Soft? It's the opposite of soft. It's leverage. Look, with an equivalent problem, you'll still write fresh code, test it, debug it. But you won't reanalyze every detail from scratch, and you won't reinvent the algorithm. You save the thinking. And the thinking is the expensive part. Now, for an idea to be reusable more than once, the book hands you a checklist.
All right, hit me with the checklist.
6 things. 1. It names which abstract problem it solves. 2. It spells out the preconditions when it works. 3. It's abstract enough to cover a whole bunch of equivalent cases. 4. But concrete enough that you can understand it and implement it. 5. Ideally, it flags the important implementation aspects, the gotchas. And 6. It documents the consequences of using it. 6. Things.
And if a solution checks all 6 boxes, plus nails a big, important family of problems,
then, together with its documentation, it earns something priceless. It earns a name. That's a design pattern. Some people say template. In Serbian, you'll hear uzorak or nahablon.
And every pattern's got a standard anatomy to it?
4 parts, always. The name, a couple of words that capture the problem, solution, and consequences all at once, and it joins your design vocabulary. The problem. When this thing applies. The solution. The elements. What each is responsible for, how they collaborate, deliberately not chained to any one programming language, and the consequences, the trade-offs, so you can weigh it honestly against the alternatives.
Hold on. A single word instead of a whole paragraph. That's the actual trick, isn't it?
That's the superpower! You nailed it! 2 engineers say one word and boom, the conversation jumps up a level of abstraction. And here's the link back. Remember the principles from last chapter? Solid, grasp, the package rules. Patterns are those exact principles worked out into ready-made examples. This chapter is basically the answer, key to the last one.
So where did the whole idea even come from?
Architecture, real buildings, real towns. Then software caught on in the early 1990s, and in 1995, 4 authors published design patterns, elements of reusable object-oriented software, and it just detonates, instantly required reading.
Gang of 4. Even I've heard that one.
The Gang of 4, exactly. And those 4 prove the whole idea with 3 worked examples. 1 creational, 1 structural, 1 behavioral. So let's take them in order.
Okay, show me a real one. Start me easy.
Easiest one there is. Unicat, the singleton. Creational pattern, dead simple, wildly common, and perfect for seeing what a pattern even is. Its whole job, its one job, guarantee a class has at most 1 instance. Ever. Think of a control object, 1 plugin manager in a drawing program, or a registry, a catalog of already parsed scripts you keep around so you don't parse them twice.
So, just make 1 global object and call it a day?
That's the trap. And here's the thing, it fails you 2 ways. Way 1, nothing stops some programmer from making a second one. And the moment they do, your correctness or your performance is shot. Way 2, sneakier. With several of these so-called uniques objects leaning on each other, you can't control the order they get built. Change the compile or link order, and you quietly break everything. Quietly. The worst kind.
Okay, so what does the actual pattern do instead?
It hands the class responsibility for its own single instance. In C++, you write a static method. Call it primerac, the instance. That returns a reference to the one and only object, and you hide every constructor. And inside? The whole magic is 1 local static variable, created the very first time that method runs. Not a moment before.
Ah, so it's born on first use.
Lazy creation, exactly. Born on first use. And get this, since C++11, that first-time initialization is thread-safe for free, the language just handles it. The constructor's private, so nobody builds one from outside, and you explicitly delete the copy constructor and the assignment operator, so nobody clones a sneaky second one behind your back.
Nice and tidy. There's gotta be a catch, though.
Oh, the catch bites you at shutdown. Creation order? Fine. Everything's born on first use. But you do not control the order. Those static objects get destroyed. So one that's still being used can die too early, right out from under you. The fix, allocate it dynamically, with new.
But then it never dies. So, memory leak?
Sharp. Yes, it leaks. So sometimes you leak it on purpose, okay? The thing lives the entire run anyway, and when the program ends, the operating system just reclaims the process memory. But if it's holding global resources, files, network sockets, database connections, or if it's 1 per thread, then no. You genuinely have to clean it up.
So neither pure option is actually great.
Neither one's great, which is why the real answer is a compromise, allocated dynamically, but through a shared pointer. Best of both worlds, it can't get deleted while something's still holding onto it, and with make shared the performance keeps right up with a raw pointer. Clean.
All right, second example. What have you got?
Sastav, the composite, a structural pattern. Picture a little hierarchy of flat shapes. There's a base class, like that shape. Every shape has a position, and one method that really matters, area, then rectangle, circle, and you're gonna love this. A square that inherits from rectangle.
Wait, square from rectangle? That's the crime scene from last chapter.
The Liskov square versus rectangle disaster, back to haunt us. But here, it's totally harmless. Why? Because these shapes get set once in the constructor. Nobody ever resets a width later. So nothing gets a chance to lie. And the area method uses hierarchical polymorphism. Remember, straight from the object orientation chapter, pure virtual in the base class, concrete in each child.
Okay, so where's the actual pattern hiding?
Here it comes. Now you want a compound shape, a bunch of shapes you get to treat as one single shape, and that thing has a double nature, okay? It is a shape, so it lives right in the hierarchy, but it's also a collection of simpler shapes. And by the way, you've seen the shape before. The sum of sub-expressions is itself an expression. Same idea.
So it's a box that's also sitting on the shelf.
Exactly, a box that's also on the shelf. Structurally, it's four things. 1, the composite is a class in the hierarchy. 2, it holds a private collection of objects from that same hierarchy. 3, it owns them. Delete the composite. The parts go with it. 4, it implements all the hierarchy's methods, so Slozen-like keeps a collection of shape pointers and its area is just the sum of the parts' areas.
Honestly, that feels almost too easy.
It is too easy, right up until you try to copy one, because the composite doesn't know what class each element actually is, so it can't copy them directly. But, and this is the elegant part, each element knows its own class, so the composite just turns to each shape and says, make a copy of yourself. A virtual method, copija, and dynamic binding calls the right one every time.
So the object copies itself because only it knows what it really is.
You've got it. And hold on to that trick? Hold on to it. Because the very next pattern runs the exact same move. Meanwhile, compound shapes nest inside compound shapes, all the way down, and they all copy cleanly, like any ordinary value.
You teased it. Same trick. What's this one?
Positalak, the visitor, a behavioral pattern for cleanly running operations all over a big object structure. Trees, graphs, same shapes, same composite. We've already got area, but now the boss wants perimeter too, and a shape count, and more after that. The easy version? Add each one as a virtual method across the whole hierarchy. And it works. It works. But two things start to rot.
All right, give me the 2.
Rot number 1. Every new method on the composite repeats that same walk, the collection loop, over and over. Rot number 2, the real killer. As the classes and methods pile up, one single computation gets smeared across every class. Your area logic is now living in 6 different places, and the day you want to change how you compute it, you're touching all 6.
So you gather each job back into one spot.
Exactly right. You pull one job out into a visitor class, and that class has one method per class in the hierarchy. Visit rectangle, visit circle, and so on. Meanwhile, the walking, and the whole which class am I question, stays inside the shapes in one new method, except visit. And here's the callback that makes it all sing.
The copy trick. The object knows what it is.
Double dispatch. The exact copija move again. The visitor has no idea what class the visited object is, but the object itself knows, so accept. Visit calls the matching visitor method. A leaf just calls its one method. A composite calls its own, then forwards accept visit to every child. Prefix or postfix your call. For area, the composite's own visit is empty. For saving to disk, it wouldn't be.
And now perimeter is just one new class?
One self-contained class, area lives in one place, perimeter in another, and neither one repeats the walk. The price? You've redirected responsibility around, and the recursion costs a little speed. For really deep structures, you can keep a work list instead of recursing.
Come on, there's always a downside. What is it?
2 of them. 1, add a brand new shape class, and now every existing visitor needs a new method bolted on. 2, some computations force the visitor to break the visited class's encapsulation. So here's the rule. You only reach for visitor once you got several different visitors, several genuine reasons to walk that structure.
And this exact pattern. Hang on, didn't you name drop it last chapter?
Constantly. Visitor was our fix for single responsibility on that expression tree, remember? And it's the one that keeps interface segregation happy because it leaves the classes a clean, narrow interface. Last chapter, visitor was a promise. This chapter, it's the actual machine.
3 patterns down, but how do I find the right one when I'm actually stuck?
You reach for a catalog, People collect patterns, name them, classify them, and there's no formal test for what deserves a spot, okay? It depends entirely on the audience. A catalog can be broad and general or narrow and specialized, say just patterns for user interfaces. And every entry gets documented half to death. Name, aliases, classification, intent, motivation, applicability, structure, and that structure's usually a UML class diagram.
UML, that's the diagram chapter.
The very same notation, yes, a class diagram for the structure, a sequence diagram for how the participants collaborate, both straight out of the UML chapter. And then it keeps going. Consequences, implementation notes, known uses, sample code, related patterns.
And these all get grouped somehow?
The famous catalog splits them three ways, by purpose. Creational, the ways of making objects while hiding the concrete types. Structural, organizing objects and classes into bigger wholes. And behavioral, handing out responsibility, wiring up algorithms and messaging, and cutting across all three. Every pattern has a domain too. Class domain leans on inheritance, static, locked in at compile time. Object domain leans on links between objects, and those you can change while it's running.
Wait, and our three examples from before?
One from each group, and that was completely on purpose. Unicat, Sostov, Positilak, creational, structural, behavioral. Singleton makes an object, composite organizes them, visitor distributes behavior, and the catalog runs deep. Factory method, builder, prototype, abstract factory on the creational side, adapter, bridge, proxy, decorator, facade, flyweight and structural, command, iterator, mediator, observer, state, strategy, and more in behavioral.
Okay, that's a lot of names.
It is. So the book is smart. It zooms in on just 5 you'll bump into constantly. Number 1, factory method. A creator class declares an abstract make method and lets its subclasses decide which concrete class gets built. Number 2, strategy. A family of interchangeable algorithms behind one interface, and a context object picks which one, so you rip out all those tangled state checks.
So you swap the algorithm without ever touching the caller.
Without touching the caller. Exactly. Number 3, decorator. Add responsibilities to an object dynamically. Each decorator does the part it knows and forwards the rest. And because the decorator and the decorated thing share one interface, you can stack them up, dodging an explosion of subclasses for every combination. Number 4, observer. One subject, many watchers. The subject keeps a list, and the second anything changes, it notifies them all. One to many, automatic.
Observer. Wait, didn't that untangle the MVC loop last chapter?
You remembered. Last chapter, Observer broke the view model cycle, and the view controller side went off to event-driven development, which, by the way, earns its own whole chapter down the road. And number 5, abstract factory, a hierarchy of factories building a whole family of related objects. Great for portability. One factory per platform, Windows or Linux, all behind one abstract interface.
All right, bring it home for me.
In one breath, problems come back with variations, so you can't always share the code, but you can always share the idea. And a documented idea with a name is a design pattern. Unicat guarantees one instance. Sostov treats a whole tree as one object. Positilak pulls operations out into visitors, and the catalog sorts every last one into creational, structural, and behavioral.
And all of it is really last chapter's principles, made real. So, where to next?
Straight into Part 3, Agile Development and Code Quality, where every one of these ideas comes roaring back as living, day-to-day practice. And if you want the deep cut, read The Gang of 4. Thanks, everybody.
Name the idea, share the thinking. See you next time. Today's word is one everybody throws around and nobody defines. Agile. Make it mean something.
Okay, here's the thing. The whole idea rests on swapping exactly one assumption. Just one. The classic heavyweight methodologies quietly bet that with enough effort up front, you can know exactly what you're building before you build it. Agile says the opposite. Change is inevitable. Change is normal. So instead of fighting it, you build a process that welcomes it every turn. That's the whole chapter. One line.
And where are we sitting on the map? We just did design principles and patterns.
Perfect setup, because chapters 6 and 7 shaped good structure. Solid. Grasp the patterns. This one zooms all the way out to the process around it, okay? A whole family of methods bubbled up in the late 90s. And in 2001, a group calling itself the Agile Alliance wrote the manifesto. That's the moment the word got its flag planted.
And now people slap the word on anything loose, I bet.
Constantly, which is why the chapter spends time on what Agile is not. It's not the absence of structure. It's not anarchy. It's not zero documentation. It's not the easiest method. It's not a cure-all. And this one gets people. It's not the mode for beginners.
Wait, not for beginners? I figured light process meant easy.
Everybody figures that, and it's the trap. The principles read simple, so people go, oh, this is the easy universal one. And it is not easy, and it is not universal. And then there's the real sin. The chapter names, cherry picking. You grab the 3 practices you like, skip the rest. Selective use is not agile. You either commit or you're just cosplaying. So the manifesto is just 4 value pairs. And I love that it's a comparison, not a rejection. People and interactions over processes and tools. Working software over comprehensive documentation. Customer collaboration over contract negotiation, and responding to change over following a plan.
So, the right side's garbage? Docs, contracts, plans, toss them?
No, and this is the line everybody misses. The right side is not thrown away. Docs, plans, contracts still matter. You just value the left more. Software with no docs is a nightmare to maintain. The point isn't 0 docs, it's the right amount at the right moment. Because docs written all up front go stale and get reworked. Same with people over process. A bad process slows great people, but obsess over it, and you bury the people carrying the project.
And collaboration over contract. That's the money one, right?
It is, and it comes from real pain. Estimating big software is brutal. Complexity grows faster than anybody can price it. So the agile move is the contract fixes the relationship, not the full scope. You agree to work together, and the parts get formulated and built gradually, side by side.
And change beats the plan. The headline everyone quotes.
And notice, you still plan. But the moment a change demands a new plan, you replan, without treating the old plan as sacred. So the trick is, don't plan far ahead. Detail only the very next iteration. Keep the rest a rough vision. Which is the whole reason it runs in iterations. An iteration's a few weeks, you plan that one for real. The rest stays a sketch.
You said the manifesto spins off principles. How many am I memorizing here?
12. But relax, they all follow straight from the 4 values. Deliver valuable software early. Welcome changing requirements even late in the game. Ship working software every few weeks. Business people and developers talk every day. Face-to-face is the best conversation there is, and working software is the real measure of progress, not the paperwork. Not the paperwork.
Okay, which ones have a real twist? Point me at the surprising ones.
3. Earn a spotlight. Sustainable development, a pace you could hold forever because overtime wrecks the mood and multiplies your bugs. Self-organizing teams, genuine autonomy, and the catch is they need every specialty on board or they stall. And my favorite, simplicity, which they define as the art of maximizing the work not done.
The work not done? Say more, because that sounds like a dodge.
Sounds like a dodge. It's the opposite. It means you spend 0 minutes on anything that might be needed someday, nothing speculative. And it's a double win. Every line you don't write, you save yourself in development now and in maintenance forever.
The best code is the code you never wrote. Man, I feel seen. So which do I actually pick? XP or Scrum? Those are the 2 famous ones.
Those are the 2 the chapter digs into, pulled from a bigger crowd, by the way. Agile modeling, agile unified process, open unified process, a whole shelf. But XP and Scrum sit at opposite ends of one dial, and the dial is, how much do they prescribe? How much do they tell you exactly what to do?
Okay, so where does each one land on that dial?
Extreme Programming. XP is older and relatively complete. It hands you a lot of specific practices. Scrum is a framework, open, borrowing techniques rather than defining them. And here's the fun part. Line XP. Up against a heavy classic like RUP, and XP looks thin. But line that same XP up against Scrum, and suddenly XP looks rich.
So classic. To XP is a smaller jump than XP to Scrum. Huh, I'd have guessed the other way.
Most people would, and in the real world, teams just combine them. Scrum to organize the flow, XP practices to do the work. And there's a twist the chapter keeps hammering. Very few teams run full. Extreme programming, but tons and tons use its individual practices.
The band broke up, but everybody's still playing the songs.
Ha! Exactly. And then there's scaling. When a project outgrows a single team, and I mean 50 developers, hundreds, often across different cities, you reach for the large-scale frameworks, DAD, LeSS, SAFe. All they really do is coordinate the many teams up top, then hand the work inside each team down to another method. Let's crack open XP the way the chapter does. Structural pieces first, then practices. And the star of the structure is the user story, a rough requirement written by the client. Short, no technical detail, just what they want in plain language.
Hold on. That's just a use case from the UML chapter, isn't it?
Great ear. And no, the difference matters. A use case is precise and analyst-written, a story is quick and client-written, which is why you don't make exact estimates from it. It just has to be clear and verifiable. And a story sits between a business case and a use case. So if you want, you can even sketch it with UML activity or sequence diagrams.
Now the time buckets. Iteration versus release. I always mix those two up.
Lock this in, and you never will again. An iteration is the short cycle, about 2 weeks, and it rarely ships to production. It's internal rhythm. A release is longer, 4 to 6 iterations, so a few months. And that one usually does ship, often on a date the client actually cares about.
So the release is the album, the iteration is the single. And below that,
tasks. The atoms, a few hours each. And woven through all of it, tests. And this is huge. XP made testing routine at every single level. Acceptance tests the client defines, plus unit and integration tests the programmers write. And get this? Before XP, testing everywhere wasn't normal. XP made it the spine. Now the practices, and they come with a mantra. All or nothing. Each practice covers some other practice's weakness, so they only work as a set. Boldest one first, the customer is a full-time member of the team. Not on call, in the room.
A client next to me all day? Heaven or nightmare? I honestly can't tell.
Both at once. On the good side, instant answers and real trust. On the bad side, it can trigger an avalanche of changes. So there's a fix. Near the end of a cycle, you forbid spec changes. You freeze it. And another. Most questions. The team answers better itself, so you leave the client only the ones nobody else can answer.
Okay, so with the client right there, how do you actually plan the work?
The planning game. And don't let game fool you. It means broad involvement and intense, real conversation. The split is beautifully clean. The client decides what gets built and its priority. The team gives the rough cost. So the team sets the size of the time and budget box, and the client fills it up by priority.
And then the client keeps meddling in the middle of the iteration, right? Come on.
Nope. That's the point of freezing it. Once the iteration starts, the client cannot change its stories. The team splits them into tasks and builds in whatever order is technically easiest. Releases get planned the same way, but looser. And those do stay open to change. It's just the running iteration that's...
And how does anyone even see progress in all this?
Plain numbers, out in the open, tasks recognized, in progress, in testing, done. Same board for bugs. And worth flagging. Those are progress tracking measures, okay? Not the design metrics from Chapter 4. Totally different animal. One counts your work, the other judges your structure. Team practices. All production code gets written in pairs at one machine. One types, the other reviews live, right over their shoulder. And the pairs are dynamic, roles swap several times an hour, partners at least once a day. So over time, everybody touches everything.
2 people, 1 keyboard. Isn't that just paying double for the same code?
That's exactly what the critics say, word for word. And the defenders come right back. A pair makes far fewer mistakes, and it spreads knowledge across the whole team. And it pairs with collective ownership. Every line belongs to everybody, so nobody's the lonely owner of one module. No bus factor of one.
But if everyone's editing everything all the time, doesn't that just collide constantly?
It would, which is exactly why continuous integration exists. CI. You push after nearly every passing test, and the code has to compile and pass all the tests before it's allowed in. Tools rebuild the whole thing, every platform, many times a day. Extend that further, and you get continuous delivery and deployment. The whole CI/CD pipeline grows out of this.
And with everyone heads down in these 2-week chunks, who's holding the big picture?
Beautiful question, because there's a practice just for that. The metaphor. An idealized big picture, basically the vision, and it exists to counter the short-sightedness iterations can breed. It's often written as a shared vocabulary of the core concepts, and the rule is every story should trace back to it. It's the North Star.
All right, hit me with the coding side, and please tell me it bans overtime.
It literally bans overtime, sustainable pace, the 40-hour week, with one exception, the last week of a release. Then simple design, build only what this iteration needs on 3 rules, the simplest thing that could possibly work. Assume you won't need the extra, that's the famous you aren't gonna need it. And once, and only once, no duplication.
So the second any code repeats, it's gotta go?
Any repetition gets factored right out. And that's refactoring, which is so big it gets its own chapter. 10. And the subtle bit people get wrong. Simple never means quick and dirty. A truly simple solution is often non-obvious and takes real work. Then, tying it together, test-driven development, you write the failing test first, then the code that satisfies it.
Wait, the test before the code? That's backwards from how anyone learns to program.
Completely flips the usual order, and it's so central, it gets its own chapter 2, 9. So we live in that one soon. And you round it out with coding standards so the team stays consistent. Because Agile changes the code constantly, which means readability matters even more here. Everyone's reading everyone's code every day.
Okay, so XP is the toolkit. What's Scrum then?
The light, flexible framework, early 90s, went public in 95. And the key thing is, it doesn't define techniques, it organizes the flow and borrows techniques, a lot of them straight from XP. It just assumes a capable team that fills the gaps itself.
So who's actually on that team?
10 or fewer, in 3 kinds. 1 Scrum Master who guards the rules and meetings, the referee. 1 Product Owner, responsible for the results. And remember this, only the Product Owner adds work to the backlog. And the developers, all the specialties, doing the building.
And the sprint, that's the famous bit everyone's heard of.
The sprint, 1 iteration, 3 to 4 weeks with a clear sprint goal everything aims at. And a subtle rule, you can change the task list during the sprint, but not in a way that threatens the goal. And if the goal itself goes bad, the sprint can be canceled early. But, again, only the product owner may.
And there's a whole ceremony schedule around it, isn't there? All those meetings.
4 events, all time-boxed. Sprint planning opens it. Up to 8 hours. Answering 3 questions. Why is this sprint valuable? What can we finish and how? Then every day, the daily scrum, 15 minutes, same time and place. At the end, the sprint review with stakeholders, up to 4 hours. And then the retrospective.
The retrospective, is that the team therapy one?
Ha! Team only. Up to 3 hours. Pure self-critique. What worked? What didn't? How do we improve? No outsiders. And 3 artifacts. The product backlog. The product owner keeps. The sprint backlog. The developers keep. And the increment, which may only contain work that met the definition of done. Which, notice, is a cousin of XP's acceptance tests.
Is Scrum actually working out there in the wild? It's everywhere.
It's the most widespread agile method on Earth. But here's the sting. Schwaber himself estimated 3/4 of organizations won't get the benefit they hoped for. Scrum works by exposing every dysfunction you've got so you can fix it. It's a mirror. But instead of fixing what they see, a ton of teams just bend Scrum until it fits around the dysfunction.
So they change the mirror instead of their own face. Rough.
Beautifully put, and the number backs you up. Roughly 43% of teams claim they're doing Scrum, but are doing it wrong. They kept the word and dropped the discipline. Last big idea, and it's a bit of a bombshell. Follow the logic. If change is welcome in every phase, then implementation changes the design, testing changes the design, even maintenance changes the design. So design stops being a separate phase you finish and leave behind. It blends into everything.
Wait, everything? There's no design step at all anymore?
Everything, yeah. And that's the tension. Remember Jack Reeves back in Chapter 4? Programming is design. Better to let the designers write the code than have someone translate their diagrams. Great for small pieces. But push it up to the big components and your architecture arrives late and unstable. And from Chapter 4, architecture is the expensive thing to change. That's why we separated it out.
So which is it? Plan or don't plan? You're pulling me both directions.
And the compromise is clean. You shape the architecture up front, before implementing, and the rest of the design you do during, as you go. And the boundary is the exact same criterion that split architecture from design in Chapter 4, the cost of change. High cost, do it up front. Low cost, defer it. Same ruler all the way through the book.
Okay, give me a concrete picture. I need to see this one.
The chapter builds an interpreter. Watch, one component becomes 3, a parser, a translator, an evaluator, plus a controller driving them, and 2 shared structures pulled into packages, the syntax tree and the compute graph. The payoff, pin that tree down early, and the parser and translator get built in parallel, maybe by different teams, because they agree on the shape in the middle.
Hang on, that's the expression tree visitor thing from Chapter 6, all grown up.
Same lineage. You nailed it. Parse a script into a tree, then walk it. Ties right back to 6 and 7. And there's one more knob, team size, and it lands small. 3 to 5, 5 to 7, around 7, 9 at the very most.
Why keep them so small, though? More hands? More done? No?
You'd think, but no. Big teams drown in communication, individuals get lost, and agreement fractures into subgroups that stop talking. And the chapter's honest about the cracks. Agile leans hard on the people, so a falling out or several members leaving at once hits harder than in a classic method. Why? The documentation is thin, the knowledge was in the people, and the people walked out.
Okay, bring it all home for me.
In one breath, Agile swaps the old bet for a new one. Change is normal. Out of that, 4 values, 12 principles, XP for the concrete practices, Scrum to organize the flow, architecture upfront with design as you go. But hold on to Robert Martin's line from the top. Agile doesn't guarantee you get what you want. What it does is let you steer continuously for the most value at the least cost.
And the plot twist is most teams don't even run a whole method. They just cherry pick their favorite techniques. And next up, we pull on one of those threads all by itself, test-driven development. I'm in. Thanks, folks. Okay, testing. Be honest with me, this is the chore chapter, right? The broccoli of software.
That's the setup, and the chapter detonates it. Here's the thing. Normally testing lives dead last. You design, you write the code, and then, if there's any time left, you check that it works. This chapter takes that whole order and flips it right on its.
Wait, you test before there's code?
Before there's code. But let's earn that, because it sounds insane until you see why. First, what is testing, really? You run the software on some chosen representative cases and you check that it behaves. That's the whole game, okay? And here's the humbling part. A test is never a proof that your code is correct. Never. Run 1,000 tests, all green, and you still haven't proven it works.
Come on, green is green, my tests pass, and I still can't say it works?
You can say it works for exactly the cases you tried. That's it. Proving it for all possible inputs, that's formal verification, a whole different, much harder beast. So what testing gives you is what the book calls informal verification. Good tests slash the odds of a hidden bug. They don't kill it. They lower the probability. They don't drive it to zero.
So green means probably fine, not provably fine. Cute.
Beautifully put. And while we're naming things, 2 words, people constantly blur: verification and validation. Verification asks, did we build the software right? Right against the spec. Validation asks, did we build the right software? The thing the client actually wanted. Different questions entirely.
Right thing versus right way. So which one do most tests actually do?
Verification, almost all of them. And hold on to that, it comes roaring back in a minute. And notice where we're standing on the map. The last chapter was Agile Development, right? This test's first idea is the beating heart of Agile. And refactoring, 2 doors down in Chapter 10, literally builds its whole safety net out of tests. This isn't some island.
Okay, so how many kinds of tests are we even talking about here?
2 rulers to measure them by. First ruler, by goal. And that splits into 3 families. Functional tests. Does it compute the right answer? Does it talk to other software correctly? Non-functional tests. Everything where the correctness of the result isn't even the point. And holistic tests, the whole product, in the user's hands. 3 families: functional, non-functional, holistic.
Non-functional. That's the vague one. Like what?
Great question. Performance fans right out. Efficiency at normal load, load tests, stability under extreme load, endurance over long runs, scalability, hunting for bottlenecks. Then, usability, which includes accessibility and regional fit, language, locale, all of that. Then, security. Then, installation in weird environments. And my favorite, destructive tests. Can I knock this thing over on purpose?
So break it for a living. Okay. And the holistic bunch?
That's the user-facing group. Development tests all through the build, then acceptance tests, then alpha and beta. And get this, alpha and beta aren't even the same job. Alpha is a small techie crowd early on, and they're not hunting code bugs at all. They're hunting bad concepts and clumsy interface. Beta is a wider crowd, close to your real users, and now you do want them finding the actual code.
Wait, who actually writes all these?
Sharp, because it genuinely matters who holds the pen. Unit tests, the programmers, always. But acceptance tests, those the client defines, a technically capable rep of the client. Because those tests are the record of what correct means to the person paying for it. Written just before or during the feature, automated, and rerun on every single build.
Okay, that was all the goal ruler. What's the second one?
By scope, 4 levels, zooming out as you climb. Unit tests, the smallest pieces, a function, a method, a class. Component tests, 1 notch up, checking a whole component's interface. Integration tests, do the components actually snap together? And system tests, the entire product, end to end. And here's the punchline, only system tests ever touch validation.
Because the others just check the spec?
Exactly. Everything below system is pure verification. Did we meet the spec, yes or no? Only the whole system, sitting in front of a real user, can ask the bigger question, did we even build the right thing? Okay, run the map back with me. By goal, functional, non-functional, holistic. By scope, unit, component, integration, system.
3 goals, 4 scopes, and units are the ground floor.
And the ground floor is exactly where we're going to live, because that's where tests first really happens. So, a unit is the smallest thing with an interface you can poke, a function, a method, a class, even a whole package if it's got a clean handle. And for any unit, you check 4 things.
4 things. Go.
1. Functional requirements. Does the postcondition follow from the precondition? Right answer for every kind of input, right change of state. 2. Robustness. Feed it garbage, and does it complain properly? Does it throw the right exception? 3. Integration. Do the little pieces behave when you use them together? And 4. The external subsystem interface. If you're leaning on something outside your code, does that thing actually match the interface
So not just the happy path. Also, what if I'm an idiot?
Ha! Robustness is the what if I'm an idiot probe. And honestly, it's half the value. Now, a couple of rules that ride along. Test code is non-production code. It ships nowhere. It exists only to test, okay? And normally you test the public interface only. Poking at the privates needs special helpers, a friend class, stuff you'd rather not bake into the actual product just to satisfy a test.
And even a giant pile of tests still isn't proof, I'm guessing.
It never lets you forget it. Good tests expose most bugs, never all conditions, and that raises the question that made this whole chapter famous. If tests matter this much, when exactly should you write them?
Before the when, you promised me a tool. What do you actually write these in?
For C++, tons of libraries, but the chapter demo's one called Catch2, and its whole charm fits in one phrase: no registration. The older libraries make you register every single test so the runner even knows it exists. Catch2? You just write the test. Drop in one config line, catch config main, include the header, and it hands you a ready-made main function that finds and runs everything all by.
There's got to be a catch. Pun fully intended.
There is. Version 2 ships as a single header and leans hard on parametric polymorphism, so compiling gets slow. Version 3 moves to a static library to fix exactly that. And hey, parametric polymorphism, remember that from the principles chapter? The templates. Instead of inheritance trick? Same idea, sitting right here in your test framework.
Nice callback. Okay, so how does one actual test look?
You open a test case. You give it a name and some optional tags, and those tags let you run just the subset you care about. Inside, you make assertions, and there are 2 you'll basically live on: require and check. Require, if it fails, stops the test dead right there. Check, if it fails, just notes it and keeps.
Wait, why would I ever want it to keep going?
Because check catches more problems in one single run. You only reach for require when the next line literally depends on this one. No point checking a pointers field after you've confirmed the pointer is null, right? There's also require throws, require, no throw, require throws. As for one specific exception type, plus matchers for strings and collections.
Got it. And what's a section?
Oh, this is the gorgeous feature. Inside a test case, code before the first section is set up, code after the last is teardown. And here's the magic. Both run fresh for every single section. So 2 sections share the same starting vector, but each gets its own clean copy, and whatever you do in one never bleeds into the
same launch pad, separate flights.
Perfect. And there's a ton more it can do. Behavior-driven style, fixtures, template tests, data generators, custom reporters. But the chapter keeps it deliberately elementary, so the spotlight stays on the method, not the gadget.
You said tons of libraries. Name a few, so I sound smart at parties.
Okay, rapid fire. Catch2, CP Unit, CP Unit Lite, Boost, Test, Google Test, Unit Plus, CXX Test, CP Unit. And they mostly differ in one thing: how much registration ceremony they make you do. The classic, historically enormous one is CP Unit. It's the CP Unit. It's the CP Unit.
And X unit means more ceremony?
More ceremony, yeah. With CP unit, you set up the test program yourself, a separate build target, your own main, a test class for each unit. The simplest form, your class inherits from test case, you fill in a run test method, and the assert macros throw an exception the moment a check fails.
And there's a fancier way, I take it.
There's a fancier way. You inherit from test fixture and use a suite. 3 macros do the work. CPU unit test suite to open it, CPU unit test for each method, CPU unit test suite end to close it. And behind the scenes, those build a static suite function that hands the runner a ready-made bundle. Plus setup and teardown, the exact same idea as Catch 2's sections. And its assert family is rich. Plain assert equal, assert doubles, equal with a tolerance, assert throw, and a message-carrying variant of every one of them?
So Catch 2 is really just this same idea with all the paperwork deleted.
That's the one-line summary of a decade of progress. Now, the real payoff, the thing this whole chapter's been circling. When do we write these things? Look at 4 tiny tests for a fraction class. And here's what's wild. With 0 declaration in front of you, nothing. You can just read off that the constructor takes a numerator and a denominator, and exactly how the accessors behave. The test is documentation. It pins down usage as precisely as a spec would.
So the test is basically the spec wearing gym clothes.
Ha ha! Yes! And here's the leap. Since you want the spec before the code anyway, why not write the test first as the spec and then write the code to satisfy them? That gives you 2 principles, and they are strict. 1, tests precede code, always. 2, high systematicity. No function gets built until there's a test failing because it's missing, and no line of code changes until a test demands.
Wait, no code at all without a failing test first? None?
Not one line. And that discipline gives you the famous rhythm, red, green, refactor. Red, you write a test. It fails because there's nothing there yet. Green, you write just enough code to make it pass, no more. Then, refactor, you clean up the design without changing the behavior. And that word, refactor, that's the entire next chapter, chapter 10.
So the R in the cycle is a cliffhanger for chapter 10. Slick.
The book literally points you there. Now, the 4 steps of a single iteration, lock these in. Step 1, analysis and design, plan the new methods, maybe a loose spec. Step 2, write the tests as the formal spec, and often they won't even compile yet. That's fine. Step 3, write a skeleton. Stub methods that just return a constant until it compiles, tests still failing. Step 4, fill in the real code, method by method, until the tests finally go green.
And you add more tests as you go, or is that it?
You add them as you go, because the moment you start really implementing, the concrete code reveals new edge cases, and you write tests for those right then and there, and keep the iterations tiny, a few minutes each, pile up 100 tests and 100 lines of code, and then it breaks? Now you're hunting through the whole haystack. Small loops keep the test just 1 step ahead of the code.
Run the 4 steps back for me.
Design, tests, as spec, skeleton that compiles, then code till green. And there's one more pair to know, the direction you build in. Top down, you use stubs, placeholder pieces that define an interface but just return constants so the thing compiles. Bottom up, you use drivers, throwaway harnesses that wire small pieces together just for...
So stubs fake the stuff below you, drivers fake the stuff above you.
You nailed the whole distinction. And systematic here means ruthless. Every feature, every boundary case, every line, every branch and loop, every polymorphic call tested across its different...
Hold on. Polymorphism, that's a whole chapter later too, right?
Chapter 11, yes. And Liskov, from the Principles chapter, remember Liskov. That's exactly why a subclass has to pass its parents' tests. It all ties together.
Give me the worked example so it's not all theory.
They build a fraction class, totally empty to start. Step 1, a test says the fraction 2/5 should have numerator 2, denominator 5. Run it. It fails, obviously, because there's no constructor yet, so you add the constructor and the accessors, you run it again, and just like that, green.
One test, one green. What's next?
Now a real rule. The denominator can't be 0, and a negative denominator should flip both signs, so -3 over -4 becomes 3 over 4. You write those as sections first. One section expects a domain error thrown on a 0 denominator, the other checks the sign flip. Red. No exception, signs are wrong. You fix the constructor, run it. Green again. The test names the rule before the code ever obeys it.
So the test is always the thing that goes first, even the rules.
Every single time. Step 3, equality. Here's the beautiful gotcha. The naive equals just compares numerators and denominators straight across, right? So 2/5 equals 4/10 comes back false. Wrong. The fix is cross multiplication. 2 times 10 against 5 times 4. And the thing that caught that bug was the failing.
Oh, so the test failing is the feature, not the bug.
That is the entire mindset shift. Right there. Then, reading and writing. They use string streams, write a fraction out, read it back in, and only once they see how reading actually works do they add tests for bad input, a wrong separator that has to leave the stream in a proper failure state, then less than, then reducing by the greatest common divisor, then addition and subtraction. Everyone, test first. 36 assertions in the end, all green. And notice, they tested every public piece, but not the private greatest common divisor helper.
Because private stuff you test through the public face, mostly.
Last beat, and this is the payoff. Tests do way more than just verify. Now, verification itself is only ever partial. Dijkstra's famous line is that testing can show that bugs exist, but never that they're absent. Fine. But there are 4 bonus jobs on top of that. Job 1. Better design. Writing the test forces you to become the very first user of your own code. So a clumsy, awkward interface stings you early while you can still fix it. And here's the kicker. Only high cohesion code tests.
Wait, cohesion, that's the design chapter word.
The same cohesion from chapters 4 and 6. It all connects. Tangled, low cohesion code is a nightmare to test, so tests quietly push you toward it. Job 2, refactoring safety net. Chapter 10 changes your design without changing behavior, and the tests answer the one terrifying question, did I just break something? You rerun them. Job 3, documentation that's always current, because a stale test fails, it can't lie. And job 4, debugging. You catch a bug your tests missed, write a test that fails on it, fix until it passes, and now the test guard that...
And debugging's a whole chapter 2. I'd bet money.
Chapter 12, and that classic gripe. Writing tests just slows me down. Has a flip side nobody mentions, it stops you from rushing, from charging headfirst into a giant pile of code you didn't even need to write. And honestly, today, code without unit tests is considered obsolete.
So the broccoli turned out to be the main course. Tests first, red-green refactor, and the test double as the one form of documentation that never lies.
That's the whole chapter in a breath. And the next stop is that mysterious R, refactoring, chapter 10, where all these tests we just wrote finally get to prove their worth.
Today's word is refactoring, which, full disclosure, sounds exactly like the thing code review keeps asking me to do, that I keep not doing.
Well, this chapter makes you feel seen and then makes you do it anyway, because it turns refactoring from a chore into a discipline. It opens with Robert Martin, and his line is that code is perishable. Perishable. Software that lives a long time has to keep changing, and every single change is a chance to wreck the clean structure you started with.
Wait, hold on. So just adding features, one at a time, quietly rots the whole thing?
It erodes it. One reasonable little edit at a time. And that's the sneaky part, because no single change ever looks like the villain. Refactoring is how you push back. You repair the structure without changing one thing about what the program does on the outside. Same behavior, better bones.
Okay, so give me the real definition, the one I could put on a slide.
Here it is, a series of small transformations that improve the code structure with no externally visible change in behavior. And I want you to hear 3 things hiding in that one sentence, okay? Improve the structure, keep the exact same behavior, and do it through a chain of tiny, tiny steps. Those 3. That's the whole soul of the thing.
It's like tidying the kitchen. The meals still taste the same, but now you can actually move around in there and cook.
Perfect analogy, and I'm stealing it. And by the way, the chapter frames refactoring as a kind of optimization, but not the kind the old school programmers meant. They optimized for runtime, for raw speed. This optimizes for maintenance. Easier to live with, not faster.
And where does this sit in the whole course? Because it feels like it's wired into everything we've already done.
Oh, it's a hub. Remember, solid, grasp, cohesion, coupling, all those principles? Refactoring is how you actually enforce those after the code already exists. Agile called it out as a core practice. And remember TDD, red, green, refactor? That third step, the refactor step, points straight at this chapter. This is where it finally cashes in.
So this is the chapter TDD's been quietly setting me up for the whole time.
Right. Now, before you touch anything, there are 2 preconditions, both mandatory. The first, the code has to already be correct. It behaves right in every situation you know about, and its unit tests pass. Green across the board.
Hold on. Why can't I refactor buggy code? That's exactly when it's at its ugliest.
Right? It feels backwards, and it's a beautiful trap. The whole goal is to not change the behavior. But with a known bug, you don't actually know how the thing behaves. That's what a bug is, okay? Behavior you didn't intend. So you're aiming at a target you can't see. You might accidentally fix it, hide it deeper, or spawn 3 new ones. And here's the kicker. Even accidentally fixing it is bad, because now the behavior changed, and you can't tell what else moved with it. It's a landmine. Every outcome is a landmine.
So the rule is, just don't.
The rule is, blunt, don't refactor incorrect code. One known bug is reason enough to stop, period. There's exactly one exception. Really nasty debugging, where you have to reshape the code just to find where the bug even lives, and that you handle very, very carefully. Now, second precondition. You have to clearly perceive a weakness in the structure. You can actually name what's wrong with it.
And if the code's fine and I honestly can't point to a single flaw?
Then you leave it alone. Aimless refactoring for its own sake is often worse than doing nothing at all. You never make a change without a clearly recognized goal. That's the discipline part.
Okay, so both boxes are checked. What's the actual procedure?
4 beats. First, set the goal. Near, something right in front of you or far, out where you can't even see the whole scope yet. Second, plan the transformations, each one simple, almost trivial. Third, and this is the one people love to skip, prepare your tests. Before each step you ask, could this move change some behavior my tests wouldn't catch? And if the answer is yes, you write new tests first.
Tests before every little move? That's the TDD heartbeat all over again.
Same exact rhythm. And fourth, you apply the step and verify. Compile, run all the tests, and if they pass, the known behavior didn't change, and you're clear to move on. And you just repeat that loop. Transform, test, transform, test, until the thing is well structured.
And when do I actually do all this? Like, is it a once-a-year spring cleaning thing?
Regularly, woven right into the programming. Because programming just is this, you alternate between writing new code and refactoring the code you've already got. Cleanly separated activities, but constantly taking turns, back and forth.
Check the structure before I add, check it again after, so the mess never gets a foothold. Okay, so how do I actually recognize one of these weaknesses in the wild? Is there a checklist I can run down?
No rigid checklist. And that's on purpose. Instead, you learn to recognize candidates. And the rule, honestly, it's gorgeous in how simple it is. If the code stinks, it needs changing. That's it. They're literally called code smells, and the chapter catalogs 22 of them.
Hold on. Code that stinks? So my whole repo is basically a crime scene.
Ha! You and everybody else, okay? And here's the honest part the chapter owns up to. It's subjective. There's a proverb it loves. Once bitten by a snake, you're afraid of a lizard. We overweight the exact flaws that already burned us once. Your nose is trained by your own scars. So, the greatest hits. Number 1, the most common, duplicated code. Same logic in 2 places. You change one copy, forget the other, and boom, you've planted a bug that's murder to find later. The fix is abstraction. Usually,
So, the crime isn't the copy-paste itself. It's forgetting a copy later.
that's exactly the crime. Next, long method. Too long usually means it's quietly doing several different things, it's hard to read, and it's a great hiding spot for a bug. Then, large class, too many fields, too many methods, and the tell is when different parts of the code only ever use different little subsets of it.
And that means what? The class has a split personality?
Multiple responsibilities, and wait, remember, single responsibility. The S in solid, same idea, sniffed out from the other direction. And that's the whole theme of smells. Every smell is some design principle being violated. The smells are the principles turned inside out. Keep that in your pocket. So, divergent changes. One class edited for a bunch of unrelated reasons, pulled in 2 directions at once. Pure single responsibility violation, and you fix it by extracting a class for each axis of change. And in mass.b, wire.
What's the one where a single little change somehow hits everywhere at once?
Oh, that's distributed abstraction. Best nickname in the whole catalog, shotgun surgery. One concept smeared across a dozen classes. So the second you change it, you're forced to edit all 12. Brutal. Then, feature envy. A method that keeps reaching over and using some other class's data more than its own. Like it's jealous of the neighbor. That's high coupling, and the fix is to move the behavior next to the data it keeps mooning over.
Wait, that's information expert from deGrasse, right? Put the behavior where the data lives.
You connected it perfectly. Put the behavior where the information lives. Same principle, different chapter. Okay, now, my personal favorite, the switch statement. Not one switch, the same switch on the same criterion, copy-paste it all over the place, and you've lived this, right? You add one new case, and now you're on a scavenger hunt for every switch in the codebase.
Lived it, hated it. So how do you actually kill it?
You abstract the criterion away with polymorphism, a class hierarchy. Each value in that switch becomes its own class, and each switch becomes one clean polymorphic call. It even has a name, replace conditional, with polymorphism.
Hold on, polymorphism, isn't that literally the next chapter?
The whole next chapter. So this smell is just the setup act for it. All right, one more pair. Speculative generality. You build something general for a case you're sure is coming, except only one case exists today. Dead weight, machinery nobody's using. And remember, the principles chapter, open-closed, warned us. Don't build hooks you might someday want. This smell is the cleanup crew for when you did it anyway. And the last one's going to surprise you. Comments.
Wait, comments are a smell now? I thought those were one of the good guys.
Usually, yes. But a big fat comment can be a mask. It's sitting there covering for code that's a mess underneath. So the move is to ask, is this algorithm really that complicated? And if it isn't, you reshape the code until most of those comments just aren't needed anymore. The code explains itself. Okay, so we take all of this and we systematize it exactly the way we did with design patterns into catalogs. And a catalog, nicely, is 3 things at once: a dictionary, a collection, and a classification. The big reference one holds 72 techniques sorted into 7 groups.
7 groups of what, though? What kind of move goes where?
Composing methods, moving features between objects, organizing your data, simplifying conditionals, simplifying method calls, dealing with generalization, and the big refactorings. 7 families.
72, though. That is a whole lot of tiny little moves.
It is, and that's the point. They're atomic, applied between 2 test runs, one small move at a time, and every technique is written up the same way. Name, summary, classification, motivation, mechanism, and a worked example. A recipe card. So anybody can reuse it. Take the star of the show, extract method. You find a coherent piece inside a big method, or any piece you'd feel the need to explain with a comment and pull it out into its own. That's the standard cure for both long method and comments.
And the trick to it is the naming, I'm guessing?
The naming, yes, you name it for what it does, never for how it does it. And there's this lovely rule of thumb. If you can't come up with a good name for the piece, maybe it isn't a real piece. Don't extract it. Try a different technique first.
Oh, so the name is basically a test of whether that chunk is even a real thing.
Beautifully put. The name is the test, and the mechanics are clean. Any variable set before your piece runs comes in as a parameter, and any variable it computes that still matters afterward becomes the return result. Next one. Move method. Which cures?
Let me guess. Feature envy.
Feature envy? You got it. A method that leans on another class more than its own just packs up and moves to that class, and the coupling drops. And then, one, just for sheer elegance. Separate query from modifier.
Okay, separate what from what now?
A method that both returns a result and changes the object state. You split into 2. One only reads, one only mutates. The classic example is a stacks pop, right? Old school pop does 2 jobs, hands you the top element and removes it. So you split it, top just reads the top, pop just removes it. And now top is a pure query. Safe to call again and again, even on a const object. And everywhere you used to call the old pop, you now call the pair. Top, then pop.
All right, enough theory. Show me all this working on something real.
A quiz program. The scoring, a right answer is 5 points, a wrong one -3, and if you don't know, you type an @ sign, and that's -1. 2 classes to start. Question, which stores the text and the answers, and test, which holds all the questions.
And let me guess, one method in there does absolutely everything.
Everything. Test, ask questions, prints the question, reads your answer, scores it, and prints the report, all in one place. A textbook. Long method, 4 jobs crammed into 1. So 13 small steps take those jobs apart. First, we extract methods, asking a single question, checking a single answer, each into its own. And then comes the insight, both lean almost entirely on the question's own data.
Wait, that's the information expert move. The behavior goes to the data.
You nailed it, and the chapter says it out loud. Question up to now was a data bag. No responsibility except holding stuff, and that's its own smell, the data class. So we move method. Push that behavior onto the question, and in one shot cure the feature envy and honor information expert. 2 birds. Then it keeps going. Extract the report. Remember the raw answers instead of pre-scored results. Split one loop that was secretly doing 2 jobs. Merge 2 loops that were doing 1. And then generalize the report so it takes an output stream, defaulting to standard out.
Oh, and that quietly hands you file output for free, which was the whole point.
For free, and without touching main, not one line. Okay, and now the chapter brings in a villain on purpose. They add a whole new kind of question, one where you order the answers and add it badly, deliberately. Now the scoring code branches on the question type, bolted right in there.
Wait, they made the code worse on purpose?
On purpose. So we get to fix it right. And the fix is the big finale. Replace conditional with polymorphism live. First, you hold the questions by pointer, so dynamic binding kicks in. Then, push the special behavior down into a subclass, so each type of question finally knows its own moves. Then you extract the genuinely abstract base. Question. With pure virtual methods, because a general question, like compute 2 plus 3, doesn't even offer you answers to pick from.
And the stuff every question shares, where does that end up?
You pull it up. The text and the correct answer belong to every question, so pull up, hoist them into the base class, while the specific instructions and the grading stay down in the subclasses. Pull up, push down, pull up, push down, until every class holds only its own behavior. And that's the switch smell from earlier, finally cured. The branching turned into a family of classes. You could draw the whole hierarchy as a UML class diagram, that notation from way back.
But hold on, the final code ends up way bigger than the original. Isn't that a fail?
Great catch. And no, it's not. The chapter flags this directly. Refactoring often increases the sheer amount of code, but longer and clearer beats shorter and cryptic every time, because clearer is what you can actually maintain. The only trick is knowing when to stop. Because honestly, you could keep generalizing this thing forever. Okay, a sober note to balance out all my enthusiasm. A complex refactoring is only ever as hard as its single hardest step. So if one step in your plan is enormous, or it touches a huge swath of the code all at once, that, right there, is your warning sign to stop and rethink.
So when should I just flat out not do it?
A few places. Database schema changes, the ripple is enormous, and migrating all the existing content is delicate and really expensive to get wrong.
Because one slip there, and real data is just gone.
Gone, and you can't get it back. That's why Agile methods delay building the database until they truly need it. Next, a heavily used interface. Changing an implementation is local. Nobody notices. But changing an interface called from 100 places? A nightmare. So you measure the blast radius first, use substitute interface, and if it's used too widely to change safely, keep both versions around for a while. And the real lesson underneath, don't publish a public interface until it's stable.
Anything else on the do not touch list?
A few more. Code that's already too complex, where a new abstraction just piles on more overload. Weaknesses that are all tangled together, where fixing one makes another worse. Incorrect code, like we said. And anywhere near a deadline. You never, ever rush a refactoring.
Right. No refactoring while the building's on fire.
Never in a fire, and sometimes the code is so far gone that rewriting it from scratch beats refactoring it. And the way you avoid ever hitting that point? You refactor regularly. Little and often. It's a problem that only gets worse if you let it sit.
But wait, all this restructuring, adding layers and classes, that has to make it run slower, right?
Often a little, sure. But here's the liberating fact, okay? Only tiny parts of your code actually dominate the performance. Take an image processor. The interaction and output code can be way bulkier than the actual image crunching code, and yet they barely touch the runtime. And guess which parts you're maintaining the most?
The bulky ones. So slowing those down is basically free.
Basically free. And that's the principle. For most code, development costs outweigh runtime costs, so you don't skip refactoring just to protect a little speed. Now, how do you figure out which slice actually needs to be fast? Two strategies. Optimize backward. Build it first. Then tune only the bottlenecks you've measured. Or optimize forward. Chase the fastest version from the start. Backward wins, hands down, because guessing your hotspots up front is unreliable, and tuning early wrecks your design.
Measure first, then tune. Okay, bring it home, press.
In one breath, refactoring is a series of tiny, test-guarded transformations that improve the structure while the behavior stays exactly put. Only on correct code, only with a real weakness in your sights, done regularly. And that's what stops your design from ever decaying past the point of repair.
Tidy as you go, so the mess never wins. And that replace conditional with polymorphism trick you kept teasing? That's exactly where we head next. I'm in. Thanks, folks. New episode. And today's word is a real mouthful. Polymorphism. Sounds like a Pokemon evolution to me.
Ha! Okay, it's Greek, right? Poly, many, morph, forms, many forms. And here's the thing, it's one piece of code that works for many different types, even when the procedure underneath is wildly, wildly different for each one. And why do we care? Because in practice, polymorphism is the beating heart of code reuse. You write it once, it serves everybody.
Lazy in the best possible way. Give me the tiniest example.
One line. The chapter opens with one line, ratio equals shape dot area divided by shape dot perimeter. And that line, okay, it does not care one bit whether the shape's a circle, a square, a hexagon, whatever. Same code, any shape. That's abstraction doing all the heavy lifting for you.
And where does this sit in the course? Feels like we bumped into it before.
We have. Back in the object orientation chapter, remember the 4 pillars of object orientation? Encapsulation, interface, inheritance, and right there, the 4th one, polymorphism. Back then, we named 3 kinds of it and basically said, we'll deal with you later. Well, this is later. This whole chapter is us cashing that check.
And there's a quote up top, right? There's always a quote.
There's always a quote, and it's a cheeky one. Alan Kay, the man who literally coined the phrase object-oriented, he says, and I'm paraphrasing, that he did not have C++ in mind when he did it. Ha! And the chapter takes that as a dare. It goes deep, from the bare concept through C++ templates out to lambdas and concepts. So buckle up. So before the flavors, and there are 4, we'll get there. The chapter dissects polymorphism along a few axes. Number 1, every polymorphic snippet has 2 parts. There's a universal part, the bit that always happens exactly the same way, and a potentially variable part where the individual cases actually differ.
So, in your one-liner, universal is the divide and assign, and variable is however each shape computes its area.
Exactly. And here's the key. That variable part is mandatory. No variation, no polymorphism, okay? If nothing varies, the behavior's just nailed down, ordinary function, done. But, and this is subtle, the universal part can stay abstract too. Sometimes only the algorithm is universal, not one literal operation. The shape of the thing is shared even when no single line is.
Okay. What's axis 2?
Type checking, and all it really means is making sure you never call a method that isn't there. Weakly typed languages punt it to runtime. They find out the hard way while the program's running. Strongly typed ones prove it up front at compile time. And get this, even a line as dumb as A equals B plus C spins up a whole web of conditions the compiler has to sit there and verify.
Wait, that's why compilers feel slow?
A real chunk of it. It's untangling subtypes and implicit conversions for every single operand, one at a time. Okay? Now, axis 3, the big one. Binding. Binding is just picking which concrete implementation actually runs for a given operation, and you can do that early or late. Static binding decides up front. At compile time, dynamic binding waits until the very last second, right before the call.
And I'm guessing static has a wrinkle.
It splits in 2. Shallow static binding just picks one implementation that already exists. Deep static binding generates a brand new version of the code for the specific types, and that one has a nickname, instantiation. And here's why it matters. It's goal for optimization, because every type gets its own tuned code. That thread comes roaring back in the optimization chapter. Meanwhile, Java and C++ sit at opposite extremes. In Java, every method is dynamic unless you mark it final. In C++, only methods you mark virtual are dynamic. Everything else binds statically.
All right, the flavors. Lay them out for me.
4 kinds, okay? Number 1, hierarchical polymorphism. This is the OOP one, the one everybody thinks polymorphism means. Code you wrote for a base class just works on every subclass for free because a subclass is a base class, and it needs dynamic binding to work honestly. It has to figure out the real type at the last second.
That's the inheritance is a thing from the OOP chapter. Square is a rectangle.
That's it. And that's exactly where an earlier chapter comes back to bite us, okay? Because here's the crack. Nothing actually forces a subclass to behave like its parent. You set the width of a square, and the height secretly sneaks along with it. And just like that, the is a relationship quietly breaks.
Isn't that the Liskov thing?
That is exactly the Liskov thing, the Liskov substitution principle. Straight out of the design principles chapter, that's the rule that keeps hierarchical polymorphism honest. A stand-in has to really act like the thing it's standing in for. So polymorphism hands you this enormous power, and Liskov keeps that power from lying to you.
Love a good callback. Kind two?
Parametric polymorphism. And this one has nothing to do with inheritance. Nothing. Here you write your code with type variables, symbolic placeholders, and at each use the compiler swaps in the real types and compiles a fresh copy. There's instantiation again. Fun fact, this was born in 1976 in a functional language called ML. C++ does it with templates, and people also call it generic programming. Same idea, different name.
Type-shaped blanks you fill in later. And 3 and 4?
3 is implicit polymorphism. Here, you don't even name the types at all. The compiler just figures out every type your code could possibly work for. Parametric's looser, bigger, more easygoing cousin. And 4. 4 is ad hoc, plain old overloading. Same function name, different argument types, each version doing essentially the same job for its type. But here's the catch, okay?
There's always a catch.
There's always a catch. You, the programmer, have to keep them conceptually aligned. If two same-name functions do wildly different things, that's not polymorphism, that's just name reuse. That's sloppy. And in C++, overloading always binds statically. Okay, quick recap. Run it back with me. Hierarchical by inheritance, parametric by type variables, implicit by inference, ad hoc by overloading, 4 flavors. And the whole rest of the chapter zooms way in on that second one, parametric. Okay, function templates. The whole move, you take an ordinary function, slap template, angle bracket, type name T on top, and replace every concrete type with that T. Take max2, returns the bigger of 2 ints. Put a T on it, and now it's the bigger of 2. Anything. Well, anything with a greater than defined on it. 2 ints. T becomes int. 2 doubles, T becomes double. The compiler deduces it, and that's implicit instantiation. Or you force it by hand.
But what if I get cute and mix them, an int and a double?
It refuses, flat out. It can't deduce one T from 2 conflicting types. Which one would it pick? So you name it explicitly or give the parameters defaults. And here's the warning the chapter hammers on, okay? Templates compile in 2 separate phases. The first pass only checks basic syntax, because, think about it, the real types aren't known yet. The actual compile only happens later, at instantiation.
Oh, so a bug could just sit there hidden?
It sits there dormant, invisible, until someone instantiates it with one particular type, and boom, it fails. So the lesson, test it on more than one type. That's the testing chapter talking. Unit. Test a template across several genuinely different instances, or it ambushes you later. And one last craft note, write templates with the most general types you can, and take arguments by const reference so big objects don't get needlessly copied on every call. Little touches, real performance.
Okay, functions covered. Can you template a whole class?
Absolutely, class templates for whole polymorphic types. Take a point class with, say, integer coordinates. Add template, class T, swap out the types, and now you've got point of int, point of float, point of whatever. It used to be you had to instantiate those explicitly, but since C++17, the compiler can deduce those too. It's gotten smart.
Oh, I'm sensing a gotcha.
There's a sneaky one. Build a point out of 3 decimal numbers, and the compiler deduces it as point of double, not point of float, double. And if you were expecting float, you've just silently changed the size and memory layout of every one of those objects. No warning at all. Those are the worst bugs, the silent ones.
You also mentioned you can template a plain variable.
Variable templates? Yeah, since C++14, you define pi1 time as template t, and out pops pi of float, pi of double, pi of long double, each at exactly the right precision. Same idea we've been doing all along, just applied to a value instead of a function.
And does one template always do the right thing for every possible type?
No, and here's the classic trap. Run max 2 on 2 pointers, and it happily compares the addresses, the memory locations, not the values they point to. Garbage. So you write an explicit specialization, a hand-tuned version just for that one type. And strings. Strings are the classic trap here.
Because a string literal is secretly a pointer.
It's a const, char pointer, precisely. So you need a version that uses ERSPRM for that exact type, or it just compares the first characters and calls it a day. The rule. The general template is your default. You override the weird cases by hand. Oh, and one more thing. This one's lovely. Parameters can carry defaults, and that's how every standard collection hides its memory strategy. A vector isn't just vector of t. It's vector of t. It's vector of t plus an allocator that defaults to the standard one, so you never once think about it. Good design.
Okay, switch gears on me. What in the world is a functional?
Ooh, beautiful build-up here. I love it. Start dead simple. Counting the odd numbers in an array. Rigid, right? One type, one fixed condition. Hard-coded. And then, step by step, the chapter generalizes everything in sight. Pull the test out into its own function. Pass that function in as an argument. Template the element type. Swap array indexing for iterators. And now, suddenly, it works on any collection at all.
So the counter just stops caring what it's counting, or why?
It stops caring completely, and that condition you're passing in becomes a type parameter we call a predicate, anything that returns a truth value, true or false. And that one template you've built, that's basically CountT from the standard library, you just reinvented it. But then C++ adds a wonderful twist. You can program the call operator.
Wait, a class you call like a function?
That's a functor. Any class with a call operator defined. Its objects get used exactly like functions. And here's the payoff. This is why it beats a plain function. A function is one fixed thing. That's all it ever is. But a class can have many objects, and every one of them carries its own stored state. So each object becomes its own personalized function. Same code, private memory.
Okay, make that concrete for me. What does that actually buy you?
Here's what it buys you. Greater than 5, with the 5s baked in. Works fine as a template. But template values only exist at compile time, okay? They're frozen. You can't spin one up from a runtime variable inside a loop. A functor, though, stores that number as a member and gets built at runtime, so now you can loop and manufacture a fresh comparator on every pass, each with a different number inside. And binding an argument to an existing function? Same exact trick, wrapped in a small template. Okay, here's a slick one. You can use a template parameter to pick the behavior itself at compile time. Watch. Say you wrap a vector so that indexing checks the bounds for you. You pull that check out into a class with a static method. Call it checkIndex, and then make a do-nothing twin, no check index, that just doesn't check. And you pass whichever one you want in as an extra type parameter.
So the same array can be checked while I'm developing and unchecked when I ship.
And bit identical to a raw vector when you ship. That's the magic. With no check index, it compiles down to literally nothing extra. Zero performance cost, not a single nanosecond.
Hold on. So the safety's just free?
Free. When you switch it off, completely free. You get full safety while you're developing, and you pay no tax at all in production. That's the dream, right there.
That's great. Now, what on earth is a recursive templates that call themselves?
That's exactly what it is. The example, building a multi-dimensional matrix as a template on the element type T and a dimension count. And here's the trick. It's gorgeous. A matrix of dimension. N is just an array of matrices, one dimension smaller. So it recurses down and down until it hits the base case. Dimension 1, a plain flat array of elements.
And every recursion needs a floor to stand on.
It does. And you define that floor with explicit specialization. Our old friend, that's the stopping step. And where do the sizes come from? Variadic arguments. A C++11 feature that lets a function take any number of arguments. So set size grabs one dimension, resizes that level, and passes the rest down the chain to the smaller matrices. Elegant as anything.
It does sound elegant. Any catch?
One heads up, yeah? A 10 by 20 by 30 matrix built this way makes a ton of tiny objects, over 200 separate allocations. So look, it's a gorgeous demo of recursion, a teaching gem. But it is not how you'd ship a real matrix. For that, you'd pack all the data into one block of memory and get cleverer with your indexing math. Pretty, but not production.
Functors sound powerful, but honestly kind of wordy. Isn't there a shortcut?
Lambdas, since C++11. A lambda is just an unnamed function you write right there, in place, where it's used. No separate class cluttering your namespace, no jumping around the file to find it. Count the odd numbers, square bracket, parent n, brace, return n mod 2. Done. Inline. Gone. And the name. Lambda. Comes from Alonzo Church's Lambda calculus back in the 1930s. This stuff has deep roots.
And that square bracket out front, what goes in there?
The capture. And the capture is the whole thing, okay? That's what makes a lambda genuinely equal to a functor. It reaches out and grabs variables from the surrounding scope. Square bracket I captures I by value. Add an ampersand, now you're capturing by reference. Square bracket equals grabs everything in sight by value. A little menu of options.
So the capture is basically the stored state, just sneaked in the front door.
It is exactly the functor's member data, in disguise. And flip side, no capture at all, and your lambda is just a plain function, nothing special. Now, when you need to store one of these or return it from a function, the types get hairy, ugly fast. So stydy function wraps anything callable behind its essential signature, something clean like bool of int. And now functions, functors, and lambdas all get handled uniformly the same way. One wrapper to rule them all.
Now, you warned us way back that template errors are brutal. Is there any relief coming?
Concepts from C++20. And these are a game changer. They're a lot like Haskell's type classes. You get to describe the whole set of types a template will accept. You just say it out loud. T must support addition with a requires clause. And the compiler checks that constraint first before it even tries to instantiate.
So instead of a 5-page wall of gibberish,
you get one plain human sentence. This type doesn't meet the concept. That's it. Readable errors at long last. And that is exactly the pain point, the very thing that made templates so intimidating to everybody for so many years. Fixed. Well, improved. Ha!
Now Java and C# have all this too, right? Same deal? Different syntax?
Look similar. Work it completely differently. Java generics are mostly a syntactic convenience, okay? Their real job is to catch your type mistakes at compile time. But under the hood, it's type erasure. Everything compiles as if it were just plain object, one shared translation for every type you ever use. Whereas C++ templates compile a separate, optimized copy for each and every type. Totally different philosophy underneath.
So Java's version is skin deep, and C++ goes all the way down to the bone.
Nicely put. That's it exactly. Now, C# is a bit deeper. Its generics live down in the virtual machine, so it can specialize to a degree, but it's still much closer to Java than to real C++ templates. And Haskell, pure functional. Haskell. Haskell's. Pure functional. Haskell's ++ concepts. Same idea. You describe what a type has to offer and let the compiler check it. Everybody's circling the same good ideas.
All right. Bring it home for us.
One breath. Here we go. Polymorphism lets you raise the level of abstraction. And the more abstract your code, the more concrete cases it quietly covers. So reuse just climbs and climbs. 4 flavors: hierarchical, parametric, implicit, ad hoc. And don't forget, the threads running through the whole course. Liskov, from the Design Principles chapter, keeps the inheritance flavor honest and replace conditional with polymorphism. From the Refactoring chapter is that same idea caught in the act. It's all connected.
One code, many forms, and Liskov making sure none of the forms lie. So where to next?
Debugging, because once your templates get this clever, this shape-shifty, you're going to want to know how to hunt down exactly what went wrong. And that's the very next chapter.
From shape-shifting to bug hunting. I'm in. Thanks, folks. All right, new episode. And today's the topic every programmer secretly dreads: debugging.
And the chapter opens by punching you right in the ego. Kernighan, one of the greats, says debugging is twice as hard as writing the code in the first place. So follow the logic with me. If you wrote that code as cleverly as you possibly could, then by definition, you are not smart enough to
debug it. Oof, thanks for the vote of confidence.
Right? But here's the liberating part, the whole thesis of the chapter. Debugging is not talent. It's not some intuition you're born with. It's systematic. Okay? And training and discipline beat raw cleverness every single time. Every time.
Okay, so it's a skill, not a gift. But back up. What actually counts as a bug?
The definition is wider than you'd think. A bug, the formal word, is a defect, is anything that makes the software behave against its specification. Anything. And here's the trap in the word bug. You hear it, you picture a typo in the code. But a defect can be born in any phase: requirements, planning, design. Not just.
Hold on. A bug in the requirements? Before anyone's even written a line of code?
Before a single line, yeah. A misunderstanding at analysis time is a defect, and it ships right along with everything else. And here's why bugs are so slippery. Software is wildly dynamic, millions of state changes a second, okay? So the bugs are dynamic too. Zeller lays out the path as a 4-phase sequence. 4 words: fault, infection, propagation, failure.
Okay, walk me down that chain.
So it starts with the fault. The bad code the programmer types. You run it, and that fault produces an infection, a wrong program state. That bad state spreads to other parts, and that's propagation. And finally, it breaks the surface as a failure, the crash, the wrong number on the screen. Fault, infection, propagation, failure.
So a bug that spreads fast is the really nasty one, right?
See, that's the intuition. And it's backwards. Fast spread is the good news, okay? A fast one races straight to a failure you notice immediately. It's the ones that creep, hidden for ages, that are the assassins. And a subtle point I love, you never actually know. A program state is correct. You only assume it. And that assumption just means no infection spotted yet.
Loud bugs are your friends. Okay. And what are the different flavors of bug?
5 kinds, sorted by how they show themselves. Interface inconsistencies, unmet expectations, that's just the wrong result. Poor performance, crashes, and data corruption, and security holes. And the scariest? Silent data corruption, because it hides. It hides, it piles up quietly, and by the time you see it, the cost has ballooned.
Great. So the worst one is the one you can't even see coming.
That's the one. Now, Where does this chapter sit on our map? It lands right after refactoring and polymorphism and right before optimization. And managing bugs has two wings, prevention and removal. Most of today is removal, the actual hunt. Then at the end, we circle back to prevention, which, spoiler, is the cheapest wing of all.
All right, removal. Debugging, literally getting the bugs out. Where do you even start?
4 activities, and they're in order. Spotting that a defect exists, analyzing and understanding it, locating it, and fixing it. Spot it, understand it, locate it, fix it.
Spotting sounds like the freebie of the 4.
You'd think, but spotting happens in testing, or worse, out in production. And strictly speaking, spotting isn't even part of debugging, okay? The real first move is understanding. And understanding means one concrete thing. You gather enough to reproduce the bug. That's the bar. Because if you can't reproduce it,
then you don't really understand it yet.
That's exactly it. Understanding connects the visible symptom to what's actually happening inside the machine, and you come out of it holding a set of hypotheses, then locating pins down the fault. The one exact bad line.
And let me guess, fixing is where it all falls apart.
Honestly, usually the easiest part, once you've genuinely found the thing. The exception is nasty. If the bug lives up in the business rules or the requirements themselves, the fix gets so expensive, you end up rewriting whole chunks of the program. But a normal code bug? Find it, and the fix is often a one-liner.
So the real pain is that middle stretch, understanding and locating.
And those two are inseparable. They alternate. You understand a little, locate a little, hit a wall, go back and understand some more. Analysis works the end near the symptom. Locating works the end near the cause. They meet in the middle. And there are 4 ways to go about all this: informal, scientific, heuristic, and strategic, tactical. Let's take them in order.
Start me on the simplest one.
Informal debugging, and it is gloriously simple. 2 steps. Step 1. Try a simple fix. Step 2, repeat until the program works. That's it. That's the entire method.
That's not a method. That's just flailing with extra steps.
Ha! It kinda is. And it only works in a narrow world. Tiny programs, a domain you know cold, bugs you catch while you're still typing, a typo, a bad loop bound, a wrong index. Here's the rule of thumb. Anything that already survived your unit tests almost certainly has no simple cause. So the easy fix is off the table by then?
And what's the danger of just poking at it?
This is the big one. If you don't completely delete your failed fix attempts, you're not fixing bugs, you're breeding them. And the chapter has this perfect joke. 10 little bugs were hiding in the code. You ship your last patch, and now how many are there? 9, obviously.
Wait, 9? 10 minus 1 is? No, hold on. The patch added 1.
The patch added 1. You net out worse than you started. So the discipline is, if a couple of honest tries don't crack it, you escalate. And that's your cue for the scientific method. And I mean literally the scientific method. Natural science reasoning pointed straight at your code.
Actual capital S science? On a bug?
Genuinely, yeah. Watch how it maps. You observe the problem, form a hypothesis about the cause, predict how the system should behave if you're right, run an experiment to check that prediction, and then loop, refining or throwing out the hypothesis until it finally holds up.
That's the exact loop a scientist runs in a lab.
The exact same loop. Observe, hypothesize, predict, experiment, repeat, and one discipline makes or breaks it. Write your hypotheses down explicitly on paper. Because if you reason purely in your head, you get a winding path you can't even explain to a colleague. Write it down, and the reasoning is reliable, and you can hand it to somebody else.
So what's the catch with going full scientist?
The observer effect. And yes, the same idea as in physics. Every probe you add just to watch the system, a code tweak, an external tool, changes its state. And a clumsy observation can mask the bug completely, make it vanish while you're staring at it. So the golden rule is, disturb that natural fault to failure flow as little as you possibly can.
So looking at it can make it disappear. That's genuinely spooky. And does the method have its own weakness?
One big one. It tells you to form a hypothesis, but it never tells you how to form a good one. And that gap, right there, is exactly where heuristics come walking in.
Heuristics? Rules of thumb? Squeezed out of hard experience?
Exactly. And the best set is David Agin's 2006 9 Rules. Let me run all 9 in one breath, then we'll unpack the heavy hitters. Understand the system. Make it fail. Watch before you think. Divide and conquer. Change one thing at a time. Keep an audit trail. Question the obvious. Get another opinion. And if you didn't fix it, it isn't fixed. 9 of them.
Okay, 9. Walk me through the ones that matter most.
Rule 1. Understand the system, the whole environment. Your code, sure, but also the OS, the libraries, the hardware, the network, even the users. When trouble hits, actually read the docs. And lean on diagrams, UML especially, straight out of
The UML chapter, from way back at the start of the course?
that very one. It comes right back as a debugging aid. Rule 2. Make it fail. Find the exact sequence of steps that triggers the bug. Reproducing it does 3 jobs at once. You see the bug from many angles, you watch its cause in action, and later you confirm the fix, because the failure stops happening. 3 jobs, 1 move.
Rule 3 is observe before you think. But honestly, didn't we basically just cover that with the scientific method?
We did. And the point is, don't reason on too little data, or you'll bury yourself in confident, wrong conclusions. But Rule 4 is the real workhorse. Divide and conquer. You take your search space, split it roughly in half, test which half the bug lives in, shrink, and repeat.
Hang on, that's just binary search, only you're hunting a bug instead of a number.
That is precisely binary search, yes. And the classic mistake is starting with a frame that's too narrow, so the real cause sits outside your search from the very first step. Always work from the failure backward toward the cause, because, think about it, there are always fewer symptoms than possible causes.
Nice. Rule 5, one change at a time.
Never a whole batch. One change, then check the consequences. And this next bit is huge. Do not mix refactoring and debugging. They're opposites, okay? Refactoring improves structure without changing behavior. Debugging deliberately changes behavior, the broken part. So refactoring must not change your test results, while debugging is literally trying to. And refactoring, by the way, got its own whole chapter. The one right before this.
Right, that was last time. So how do you keep the two from bleeding together?
You separate them in time. If you need a big cleanup just to see the bug, refactor first. Tests, green the whole way, and only then go fix. Never blend the two into one mush, because then you can't tell which change did what.
Rule 6, the audit trail.
Keep traces. 2 kinds. Automatic ones, where the code writes its own log, and manual ones, a logbook you keep by hand while you're testing. And the keyword is while. You write it live, not afterward, from memory.
Because by after, you've already forgotten the one step that actually mattered.
Exactly that. The whole goal is linking the symptom to the cause, and since you don't know either one up front, a trace can never really be too detailed.
All right, 7 and 8.
7. Question the obvious. Is the oven actually on? Does the car have gas? Did you even run the right build? The obvious is precisely the thing we all skip. And 8. Get another opinion. And here's why that works. You wrote the bug. So why on earth would you be the best person to spot it?
Right, you're too close to it. You can't see your own blind spots.
You carry silent assumptions a fresh pair of eyes doesn't have. And there's a rule inside the rule. When you bring someone in, tell them the symptoms only. Never your assumptions. Give them information, not your conclusions.
And 9 you already gave us. If you didn't fix it, it isn't fixed.
And that one is not filler, okay? A bug that mysteriously vanishes after some change nobody made on purpose? That is terrifying, because maybe it didn't leave. Maybe it just changed its disguise. Replacing a blown fuse doesn't fix whatever kept blowing the fuse.
All right, tools, what's actually in the kit?
2 families. External tools you use every day across projects, and internal stuff you build into the program purely to hunt bugs. Start external with the compiler itself. Here's the wrinkle. The compiler optimizes. It reorders code, inlines functions, hoists things out of loops. Great for speed, but it wrecks your ability to follow along line by line. So you get 3 build modes.
Give me the 3.
Debug. Optimization's off. Full mapping from the machine code back to your source. Dead easy to trace, but a lot slower. Release. Everything optimized. No debug info at all. That's what ships. And release. With debug. Optimized, but still mapped. The middle path. So you get source-level debugging at nearly full speed.
So debug mode is the slow but honest one, and release is the fast liar.
Ha! Slow and honest. That's the trade. Then the real star, the debugger. GDB, or the one baked into your IDE. Breakpoints. Conditional breakpoints. Data breakpoints, which fire the instant a memory location gets written, stepping line by line, watching variables change. And my favorite, the call stack, showing who called the current function and who called that, all the way up to main. That's how you trace a bad value back to where it was born.
That's a serious amount of X-ray vision packed into one tool.
And there's more. The profiler, it watches resource use. Its real home is optimization, literally the next chapter. But since slow performance is itself a kind of bug, it earns a seat at this table too.
Optimization. That's the very next thing we're doing, isn't it?
Right after this one. Then dynamic analysis. Valgrind runs your program inside a sandbox and catches bad memory access and leaks. Static analysis, like CPU check, reads your code without ever running it. Coverage tools like gcov find the lines that never execute. And sanitizers. Those dash-off sanitized flags. Compile the check straight into the binary. Address, leak, undefined behavior, and thread, which catches race conditions.
Race conditions. That already sounds like a whole scary topic on its own.
Oh, it is. Concurrency gets its own chapter down the line. Now flip to the internal side. Code you write for yourself. Assertions first. An assert checks a condition that must be true, and if it isn't, the program dies loudly, right there. And keep each one simple. 2 separate checks. None is non-negative, and under 100, so when one blows, you know which. In production, the ndebug macro compiles them out, and static assert checks at compile time, for free.
So the code basically polices itself.
It does. Then, execution traces. Macros that log where you are, stamped with time and place. Little snippets you inject to print some complicated state in readable text. And unit tests, which, and this is the beautiful part, pull double duty as—
Wait, tests? Isn't that the whole TDD chapter?
Chapter 9. Exactly. And this is the link I love. Tests catch regressions. You change some code. The tests tell you whether the behavior shifted, and the specific test that failed points you straight at the case that broke. So locating the cause gets dramatically easier. That's exactly why tests are pure gold while you're refactoring.
So, is there a short official list of prevention techniques?
There is 4 of them: assertions, traces, commenting, and unit tests. And on top of that, Metzger adds a strategic layer: debugging strategies lifted from search algorithms. Binary search, greedy search, breadth first and depth first across the suspect functions, plus deductive and inductive analysis. And the neat detail: breadth first adds a function's own calls to the end of the list, depth first to the front.
All right, prevention. The cheap wing you keep teasing.
The cheapest bug is the one that's never born. And 2 big enemies feed the bug count. 1, not enough skill. 2. Needless, chronic stress. And here's the nuance. A short burst of stress can actually lift your performance. But long-term stress, it grinds down even your very best people and makes them error-prone day after day after day.
So the classic Death March deadline is basically a bug factory.
It manufactures them wholesale. And the fixes are refreshingly human. Good relationships on the team, constant learning, working conditions relaxed enough that people can actually think, good communication with the client, and systematic quality assurance. None of that is about being a genius. It's about being sane.
And when bugs slip through anyway, because they always do,
then you set yourself up to locate them fast. Number 1 move, keep every previous version of the code, GIT, SVN, whatever you use. Because comparing the last version that worked against the first one that broke is one of the easiest ways there is to corner a cause.
Version control. I'm betting that gets its own chapter 2 later on.
Later in the course. Yeah, a big one. 2 more prevention habits. Never ignore your compiler warnings. Clean that code until there isn't a single warning left, not one. And write readable code from the start, because readable code just has fewer places for a bug to hide.
Which lands us right on comments.
It does, and the rule for comments is sharp. They should explain the motivation, the reasons, the why, not the what. Doxygen can even generate your documentation straight out of them. But good comments are surgical, okay? The bad ones narrate the obvious. Increment the counter by 1, thank you. Or worse, they dress up bad code to look respectable.
Wait, so a comment can actually be a red flag?
Fowler nails it. He says comments are often used as deodorant to cover up a smell in the code. So before you reach for a comment, try refactoring instead and let the code speak for itself. The balance is to comment only where it genuinely earns its keep.
Okay, bring it all home for me.
In one breath, a bug is any failure against the spec, born in any phase, not just coding. You remove them systematically, never by luck. You understand. You locate. You fix, leaning on both the toolbox and your teammates. But the real victory, the cheapest of all, is prevention. Killing the bug before it's ever born.
Loud bugs are your friends. The silent ones are assassins, and staring too hard can make them hide. And next time, we make all of this actually run fast, without breaking any of it. Optimization. Catch you then. All right, new episode. Making software fast. That's just writing better loops, right?
Ha! If only! And here's the thing. It starts long before you touch a loop, with a question that sounds dumb but really isn't. What does fast even mean? The chapter opens with Dijkstra wagging his finger at us, okay? His whole point, clever tricks, are the last resort, not the first move. You reach for them when you've run out of everything else, not 1 second before.
Okay, so what does fast actually mean, technically?
Performance. And formally, performance is a ratio, the work a program does, divided by the resources it burns to do it. And notice, I'm going to keep saying performances, plural, on purpose.
Plural? Come on. Fast is fast.
You'd think. But no, because there are many kinds of work. Cases handled, bytes of text, seconds of video, transactions, and many resources getting spent. Processor time, memory, cache, the disk, the bus, the network, even electrical power, even the heat coming off the thing.
Wait, heat counts? So my laptop cooking my legs is technically a performance stat.
It literally is a performance stat. But here's the move that makes this manageable. You don't watch all of them at once. You hunt for the one resource carrying the heaviest load. And that one has a name, the bottleneck.
And I'm guessing it's always the processor?
Usually, but not always, and that's the fun part. cache a bunch of intermediate results, and boom, you shove the load off the processor and onto memory. Which is the whole secret here, okay? Optimization is not some magic delete the works button. Most of the time, you're just shuffling the load from one resource onto another.
Hold on. So I'm not actually removing work. I'm just moving it somewhere else?
Often. Exactly that. And once you see it that way, everything reframes. Oh, by the way, where are we in the course right now? Right after debugging, right before concurrency. And that little sandwich is no accident, as you'll hear by the end. So Malkoff lines up three cousins, and it's worth keeping them straight. Debugging, the chapter we just wrapped, there you change what the program does to make it correct. Optimization is a different animal. You're not allowed to change the result at all, not one bit. The only thing you get to lower is the cost of computing it.
So, same answer, just cheaper to get to. And the third cousin?
Refactoring. From Chapter 10, it also keeps the result identical, but its goal is a prettier program, where optimization's goal is a faster one. And here's the sad little truth. Those two goals fight. They fight constantly. Efficient code and clean code pull in opposite directions, and that tension runs underneath this entire chapter.
Okay, and there's this phrase in here, optimal versus optimized. That's just the same word twice, right?
Great catch, and it is crucial. Optimal means provably the best possible. Mathematically, you cannot do any better, and optimization almost never aims for that. It aims for good enough, close enough to the ideal that the job is actually usable.
Wait, why not just chase the best? Why settle?
Because proving true optimality takes heavy math, okay? And even just finding a faster solution costs you real work, analysis, experiments, implementation, testing, and in a real project, finishing matters more than perfect. So you write down this could be faster as a task for later, and you move on with your life.
So where do you actually reach in and optimize?
Layers. By level of abstraction. Up top, you've got high-level optimization, everything above the code, and it splits in two, the project, which really means the architecture, and the algorithm. Then down below, low-level optimization. That's the code itself, and how you build the program out of it.
Give me the architecture one first.
Decomposition by resources. You look for the features all elbowing each other over the same bottleneck and split them into separate components so they can run on different machines now or down the road. Modularity, basically, buys you flexibility for when the load spikes.
And the algorithm level is just pick a faster algorithm?
Pick a lower complexity, one. But carefully, okay? Because here's the catch. Nobody warns you about. A lower complexity algorithm often has a pricier single step, so it only actually wins once the input gets big. And high-level work in general is expensive, because it usually means rewriting stuff you already went and wrote.
Which, nobody ever wants to hear.
Nobody wants to hear it. So you do this stuff early, up front, before there's a whole mountain of it to rewrite. Now, the low level. This one splits into 5 sub-levels. And honestly, I love rattling these off. So here we go. Source code, compilation, building, machine code, and execution.
Okay, walk me down them.
Source code. You reshape the code itself, or trade a nice general concept for a language specific, one that happens to be faster. Compilation. You pick the compiler version and tune its flags. Building. Static versus dynamic linking, or a lighter library. Machine code, now your handwriting assembly. The only level where you use every single thing the system's got. But you pay for it, because it changed your code to one class of processor. And execution, adapting to the processor at runtime, out-of-order execution, delayed branching, and just-in-time
Source, compile, build, machine, run, and, real talk, assembly sounds terrifying.
and barely needed anymore. Honestly, modern compilers optimize so well, they'll happily reorder your instructions for you. You handwrite assembly only in that one rare, sensitive spot where it truly matters and almost nowhere else. All right, strategy. 3 questions decide the whole game. When, what, and how much. The moment you do it, the target you aim at, and the amount you're willing to spend on it.
Let's start with when.
2 options, and they're night and day. Forward optimization. You care about speed the entire way through, planning, coding, testing, continuously. Backward optimization. You shove it all to the very end, build the thing correct and well-structured first, and only once it actually works do you turn around and ask, okay, now is it fast?
And the second one's the winner. I can hear it in your voice.
Ha! It usually is, and it rests on 2 assumptions. 1, the code changes a lot during development. 2, almost all your performance rides on a tiny sliver of the software. If both hold, and they usually do, then you optimize as little as possible, as late as possible.
Because once code's optimized, it's a nightmare to change.
That, and something deeper, you can only truly measure performance at the very end, once every feature actually exists. Before that, it's all guesswork, okay? And this is exactly where Knuth drops the most famous line in the whole field: premature optimization is the root of all evil.
Wait, that's a real quote? I genuinely thought that was just a t-shirt.
It's real, chapter and verse. What he actually says, ignore the small efficiencies about 97% of the time, but do not miss the critical 3%. The exact numbers aren't the point. The point is, find the part that matters before you go touching anything. And localizing that hot part? Same detective work as localizing a bug back in the debugging chapter.
Oh, nice. Same detective work, brand new crime scene.
Same detective, new crime. Now, how much? That comes from 2 criteria: the minimal performance you absolutely have to hit, and the planned performance you're aiming for. And for interactive software, there are these 3 gorgeous human thresholds.
Human thresholds? Like what, exactly?
So beautiful. 1/10 of a second feels instant, instinctive reaction territory, like a key press landing. 1 second is a natural pause, the beat it takes to answer an easy question. And 10 seconds is the ceiling for staying interactive at all. And anything past 1 second, you'd better show the user something's happening. Slower than 10 seconds, just run it in the background and let them walk away.
So the little spinner isn't decoration, it's psychology.
It's a contract, is what it is. And modern practice ties the whole thing together with 4 ideas. Estimate performance, be lazy about optimizing, localize it, and experiment. And lazy optimization is really just the agile. You aren't going to need it. Teams literally reserve somewhere between 5 and 35% of the schedule for
5 to 35%? That's not a range, that's a canyon.
Ha! Because it depends on everything. The problem, the language, the tools, the team. And here's the honest part. Every optimization is only ever an attempt. You keep it only if measurement proves it helped, and the speed was worth the uglier code. If not, you revert it. But you write down that you tried, so nobody wastes an afternoon trying the same thing again.
Okay, finally, the actual tricks. What's the single biggest one?
Cache locality, the heavyweight champ, up to 100 times faster. Here's what you have to know. The cache loves exactly 2 things: reusing the same data quickly and using data that sits right next to its neighbors in memory. Feed it those 2 things and it screams.
Give me the textbook example.
Summing a big matrix. If you walk it column by column, 2 consecutive elements are, what, 40,000 bytes apart. The cache can't possibly hold both, so it's a miss every single time. Now flip the loops, walk it row by row, so neighbors are actually neighbors in memory. And the exact same sum runs up to 100 times faster.
100 times? Just from swapping I and J around? That's genuinely absurd.
It's the magic that isn't magic. Same math, same result, nothing deleted. Okay, next big one, cutting jumps and branches. A jump wrecks the processor's pipeline. It's already racing ahead, working on the next instructions before you even asked. And a jump comes along and throws all that started work in the trash.
So every single if is a little tax.
A little tax, and one you can sometimes skip entirely by just doing the work for every case instead of checking a condition first. Then there's a whole family of general tricks, okay? Inlining, you paste a tiny function's body right where it gets called, so you skip the entire call machinery. A little swap runs 10 to 15 times faster because for something that small, the call itself costs more than the work. Hoisting invariance, anything the loop recomputes identically every pass, you yank it out and compute it once before the loop. Pulling a vector size out can be more than 3 times faster. And lookup tables, you pre-compute the answers into a...
That's a lot of free speed. Is there a catch hiding in there anywhere?
There's always a catch. Loop unrolling. Sounds great, fewer jumps, right? But smaller code is not always faster. Unroll too far, and the loop body spills past the cache and slows right back down. Or the compiler was already doing it better than you were. Because the processor's a collection of resources, okay, it's not just an instruction counter. Some instructions cost way more than others, and jumps cost most of all.
So what about C++? Specifically, anything special there?
Quick tour, use the standard library. It's brutally, obsessively optimized. Pass big objects by const reference instead of copying the whole thing around. And swap dynamic binding for static wherever you can. Oh, remember polymorphism? Chapter 11? A virtual method binds at runtime. But if no subclass ever overrides it, make it non-virtual. Now it can inline, and the processor predicts it better.
So the flashy polymorphism quietly comes with a speed price tag.
A small one, but real for the simple methods. And under all of it, the golden rule, okay? Never optimize on a hunch. Never. Try it, then measure. No gain? Revert it. You do not wreck a clean design for maybe faster.
But how do you actually find that critical 3%? Eyeballing loops seems rough.
You don't eyeball. You bring the single most important tool in this whole chapter, a profiler. It watches resource use while the program's running and points a big finger straight at the bottleneck. And there are 3 flavors, sorted by how they collect the data.
3. Okay, hit me.
Event-based first. It just listens to events, the OS or the runtime already reports, cache misses, page faults, that kind of thing. Linux perf is the classic. Second, instrumentation. It plants a counter at the entry and exit of every single function. Dead accurate counts, but the program runs way, way slower with all that machinery, so the actual timings can drift on you.
Right. The observer effect. Watching it changes it. Very physics.
Ha, exactly, observer effect. And the third, sampling. It interrupts the processor at regular intervals, anywhere from 100 to 10,000 times a second, and just notes where it is right then. Your call counts get a little fuzzy, sure, but the relative timing is actually more accurate, and it barely slows the program down at all.
Okay, so what does one of these actually tell you when you run it?
Let me walk the gprof example because it's honestly gorgeous. You've got a program that fills a 10,000 by 10,000 matrix and sums it. First profile, total run, 1.47 seconds. And one function, sumline, is eating 1.28 of that. 87%, one function.
Found our guy. So what's wrong with him?
Cache locality. Sumline is summing, column by column instead of row by row. Classic. So you flip it. And sumline drops from 1.28 seconds to about 0.03 of a second. Call it 42 times less. Total run falls to 0.23. The whole program's suddenly about 82% faster.
From one line? Okay, I'm officially a believer now.
And here's the beautiful part. The profiler immediately repoints. Now the biggest cost is in it. So you go strip a pointless check out of it, and total lands around 0.12 of a second, roughly 92% faster than where we started. Measure, fix the worst thing, measure again. That's the loop.
It's a loop. Find the worst, fix it, remeasure.
That is the entire rhythm, and this ties straight to metrics, chapter 16. Remember, DeMarco? What you can't measure, you can't control. Same gospel, different pew. Oh, and one deadly trap. Okay, write this one down. Never, ever profile the debug build.
Why not? A build's a build.
Nope, because debug builds turn the optimizations off and pile on tracking. They run far slower, and get this, they can even have a completely different bottleneck than the real thing. So you'd sit there optimizing the wrong function entirely. Measure in real production conditions, or you're just guessing with extra steps.
All right, bring it home. Give me the one thing to tattoo on my arm.
Correctness always beats speed. Always. A slow program is at least still usable on small inputs, but a wrong program is dangerous every single time you run it. So you never, ever trade correctness for speed. Full stop.
Got it. And what about the magic? The guy who tweaks one line and the whole thing takes off.
There is no magic, okay? It's an exact discipline, start to finish. And the so-called magics is just somebody who understands the machine better than you do. Which is exactly why Malkoff says, don't skip the line, you learn good design first, then debugging, then the tools, and only then, at the very end, optimization.
Design, debug, tools, optimize. We literally walked that entire staircase this season.
We walked every step. And that very last technique we brushed against? Parallelization? Splitting the work across cores and machines? That gets its whole own chapter next. Concurrency? Breaking one big job across a bunch of workers is your first real taste of it.
From one slow loop to 100 cores. Measure first, though, always. Thanks, folks.
Okay. Every single chapter up to now, we've been quietly leaning on one assumption, and we never once said it out loud. Your program runs on one thread, one instruction, then the next, in exactly the order you wrote them, okay? It's a nice, calm little world. And the second you take that comfort away,
everything falls apart?
Ha! A whole new layer of problems appears, problems that just don't exist in the sequential world. Now you've got two jobs sharing the same clock, the same data, the same machine, all at once. That's Chapter 14, Concurrent Programming. Less, a shiny new feature. More, a brand new collection of ways for everything to go sideways.
Okay, but where does this even sit? We just walked out of the optimization chapter.
Right on the map. A lovely handoff, by the way. Parallelizing your software is one way to make it faster, so concurrency is kin to optimization. But the chapter's honest about the catch. Immediately, the best speed up you can ever hope for is linear in the number of cores. Double the cores. At most, double the speed. And in practice, you never even get that, because you burn real time on communication and synchronization between the jobs. More cores, more speed, but never, ever free.
Never free. So more isn't automatically better.
Never automatically better. Now, Rob Pike opens this whole area with one line. Everybody quotes, and almost everybody gets wrong. Concurrency is not parallelism. And the chapter pulls those three words apart very, very carefully because...
And in my head, they're the exact same thing.
Right, in most people's heads. Concurrent is the widest idea. Jobs run in overlapping windows, interleaved, a bit of this one, a bit of that. No guarantee which gets the processor when. Parallel is stricter, an actual stretch of time where two jobs run at the very same instant. And that you cannot fake. It takes more than one core. So parallel is just concurrent plus one promise, genuinely simultaneous. That's the narrower, stronger word. And distributed goes further still, completely different address spaces, separate memory worlds that never touch.
Concurrent, parallel, distributed. Widest to most separate.
That's the trio, and hold on to it, because the whole chapter hangs off those three.
So what actually runs these jobs, like physically?
Two kinds of execution unit, processes and threads. And the whole difference comes down to one question: what's shared and what's private? A process is a program in execution. It hauls around the code, plus the full state. Is it ready? Running? Waiting? The instruction counter, the saved registers, and a whole pile of resource bookkeeping on top. Memory tables, file descriptors, every resource it's holding.
That is a lot of luggage.
It's a lot of luggage. And hold that thought, the luggage is the whole point. Now a thread. A thread is just a piece of a process that runs sequentially, and one process can hold many, each starting from a single main thread. But a thread carries almost nothing of its own. A tiny private kit, its own state, counter, registers. That's it. Everything heavy. The code, all that resource info, stays shared at the process level. Stays shared at the process level.
Wait, so why even bother with threads if we've already got processes?
Ah, that's the killer question. And the answer is, one phrase, the cost of a context switch. That's the processor putting down one job to pick up another. It writes the whole old state out to memory, then loads the new state in. And that's expensive, okay? The state is bulky, and while you're at it, you almost always blow the cache clean away. So it hurts.
And threads somehow dodge all that?
They do, because a thread's private part is featherlight, remember, and the heavy shared part never moves. So, switching between two threads of the same process is cheap. Cheap. But, and I want to lean on this, only of the same process. The moment you jump to a thread of a different process, that shared part is different and you pay the full context. Switch price all over again.
Okay. Any other big split between the two?
One huge one. Only processes can run distributed because all the threads of a process are trapped together in the same address space. And that shapes how each one talks, by the way. Processes don't share memory, so they have to communicate through special interprocess channels. Signals, sockets, pipes, shared memory. Threads are the mirror image. They already share everything, so they just talk straight through the shared data.
Which is basically coupling, right? Straight out of the design chapter.
Exactly the word. Coupling. Back then it was just a design smell, a thing you frowned at from across the room. Here it's two threads literally reaching into the same memory at the same instant. Same idea. Now with teeth. And taming that? That is the entire rest of the chapter.
All right, so how do I actually make a thread?
Two flavors in the book, the C++ standard library and Qt. First, stydy thread, since C++11. You hand its constructor a function, maybe some arguments, and here's what trips everybody up. Building the thread starts it. No separate starts call, no launch button. Then you call join to wait for it to finish. Qt flips it. You subclass QThread, write a run method, and just creating that object does not make an operating system thread. That waits until you call start.
So in one, it's automatic. In the other, you pull the trigger yourself. Got it.
You got it. And now a genuine landmine, okay? If a stydy thread is still joinable when it gets destroyed, meaning you never joined it and never detached it, the program just calls.
Yikes. So you have to join it or detach it.
It calls terminate, and your program dies right there on the spot. So, detach is the other choice. It lets the thread run free in the background on its own. And C++20 added a nicer option, JThread, which just auto-joins in its own destructor. Footgun. Gone.
Nice. Is there like a menu of things I'm even allowed to do to a thread?
5 basic operations, and they frame the whole comparison, so they're worth naming. 1, create, which, remember, usually starts it. 2, finish, when its main function ends, though cleanup may not be automatic. 3, suspend and resume. Pause now, wake later, and only some operating systems support that. 4, interrupt, one thread, quote, one thread, killing another. And 5, wait, one thread waiting on another, the most basic form of synchronization there is.
Hold on. One thread can just kill another one?
It can try. And that's the dangerous one. So dangerous, the standard library flatly refuses to let one thread forcibly kill another. Qt offers terminate. But get this, it doesn't even guarantee the thread dies. And it's worse. It stops the thread at some arbitrary spot so a mutex it was holding stays locked. Shared data it was writing is left half-finished. It's a mess. That's why you follow it with a wait for any reliability. And why terminate is a break glass, an emergency move, never routine.
So what's the civilized version of ending a thread?
It came in C++20. JThread's cooperative cancellation through a stop token. You force nothing. You request a stop, and the target thread checks that flag on its own schedule and bows out gracefully. You ask it to leave. You don't shoot it. Suspend and resume follow the same restraint. The standard library won't let one thread pause another. A thread can only tell itself to sleep. Sleep for a while, sleep for a moment, or yield, a nudge to the scheduler. Qt doesn't offer suspend at all.
Okay, you keep hinting at some mess. What are we actually fighting here?
The entire back half of this chapter exists to solve 3 problems. Only 3. I want you to hold that number. Sharing resources between execution units, communication between them, and synchronization of them. And synchronization just means coordinating their work. And what truly has to be coordinated at the end of the day is access to the shared resources.
Or else what? What actually goes wrong?
Or else you get the classic data race anomalies, and the chapter names 4 of them: lost updates, reading uncommitted changes, non-repeatable reads, and phantom data.
Wait, those are straight out of databases.
Same family of demons! You've met these ghosts before. And the first tool that tames them is the mutex. It works by a lock. You lock it once, and if it's already locked, the next thread that tries has to wait for the unlock. And the locking and unlocking are atomic operations, handled way down in the operating system. So far sounds airtight.
So it physically locks the data down. Nobody else can touch it.
No, and this is the trap. This is the thing to really sit with. A mutex guards nothing by itself. Nothing. It's a convention, not a physical lock on any door. It only works if every thread politely agrees to protect the same data with the same mutex. And who's enforcing that? Nobody. So the moment one single thread reaches in and touches that data without locking, the entire protection is void. For everybody. For everybody.
So it's an honor system with a token. Everybody has to agree to grab the token, or it means nothing.
That is a beautiful way to put it. Now, the real practical problem, you lock the mutex, and before you ever reach the unlock, an exception fires and blows you clean out of there. And now, the mutex is locked forever. Dead. The fix has a name worth memorizing.
So the second the scope ends, even if an exception throws you out, the destructor runs and unlocks it.
Every single time. Guaranteed. In the standard library, that wrapper is LockGuard. There's also Scoped Lock for grabbing several mutexes at once without deadlocking yourself, and Unique Lock for when you want to lock and unlock explicitly. Qt gives you Q Mutex Locker for the exact same idea. One catch? These have to be plain local objects on the stack, never heap allocated, or the whole guarantee just evaporates.
And you keep saying mutexes and locks like they're 2 different things.
Because they are. A lock is the more general idea. A mutex is just one kind. A plain mutex only knows exclusive. One owner, everybody else waits. Full stop. But a read-write lock is smarter. If a thread only wants to read, it happily lets other readers in alongside it. Many readers at once, no problem, but the instant somebody needs to write, everyone else is locked out, and I mean everyone, readers included.
Many readers, one writer.
That's the whole song. The standard library does it with shared mutex, a shared level for the readers, exclusive for the writer, and Qt does it with QReadWriteLock, plus its own array AI helpers, QReadLocker and QWriteLocker.
Is a semaphore Just a fancier mutex?
A cousin, related, but a different soul. A semaphore keeps a counter you can raise, lower, and check, and that number means the count of free resources. Want one? Lower the counter to grab it. And if it's already at 0? Nothing free? You wait until somebody releases one back into the pool.
So a mutex is really just a semaphore that only ever counts to 1.
You just derived it. That's a binary semaphore, exactly, a counter that's only ever 0 or 1. And funny enough, in C++, semaphores only showed up in C++20, both counting and binary. Acquire lowers the count and blocks you at 0. Release raises it and wakes a waiter. Qt, meanwhile, has had Q semaphore forever. You just set the starting count in the constructor.
All right, is there anything in here that's less manual? Because this is a lot of handwork.
Oh, I was saving the elegant part. Instead of you wrestling threads by hand, the standard library hides the whole thread behind one idea, a future result. You call stydy async on your function. It runs asynchronously and hands you back a future, an object that will eventually hold the return value, a claim ticket for a result that isn't ready yet.
A claim ticket. Okay, I like that.
And you steer it with a policy. Launch async spins up a real new thread. Launch deferred is lazy. It runs the work in the same thread only when you finally asked for the result. Then the future lets you wait and call get, which hands you the value. One gotcha, okay? You cache that ticket exactly once, call get twice and you're in trouble, and there's a valid check for whether it's still good. The beauty of async plus future. Juggling threads is the library's job now, not yours.
And where does promise fit? That word keeps turning up right next to future.
They're a matched pair. A future, by itself, only pulls out a function's one final return value. But if you need to wait on intermediate results, values produced along the way, you reach for a promise. The producer thread holds the promise and sets values into it, or even an exception. The consumer thread holds the matching future and pulls those values back out.
So if I'm the one writing a function, how do I know it actually survives all this chaos?
The chapter grades your code on a 3-rung ladder. Bottom rung, a single call function. Must not run in 2 threads at once, usually because it's leaning on global data unsafely. Middle rung, a reentrant function. Can run in several threads, but only if they're not chewing on the same data. Top rung, a thread. Safe function. Runs in any threads you like. No strings, no conditions.
And the same ladder works for whole classes.
Same exact ladder through the class's methods. A thread-safe class has every method, thread-safe, and lets nobody poke at its data directly. And here's the thing. The 2 most common mistakes both come from ignoring this ladder. Either you overlook the sharing problem while writing the code, or you overlook that some class you're using was never built for concurrency, and you treat a single call class as if it were thread-safe.
So half these bugs are really just wrong assumptions.
Wrong assumptions in a lab code, yes, but it's not all peril. There are proven ways to write safe code. A pure functional style, everything by value, no globals, no side effects, local and thread, local data nobody else can even see. Good old mutual exclusion, your mutexes and locks, and atomic operations. Those are your tools.
That's a ton of discipline, though. Is any of it free?
Never free. There's that phrase again. Passing everything by value costs you. Locking costs you. Atomics are expensive. Safety almost always costs you performance. Which is why the chapter puts its foot down on 2 things. Hard. First, when do you start worrying about concurrency? From the very first moment you design the class, not later. Because bolting concurrency on afterward usually means tearing the whole thing down and rewriting it.
And how tight do you make the locks? Big regions? Tiny regions?
That's a genuine balancing act and never, ever done by gut. Lock the smallest region you possibly can because one wide locked stretch murders your parallelism. Everybody just stands around waiting on it. But don't overcorrect into a swarm of 1,000 tiny locks either, because the act of locking has its own cost. So you hunt for the balance in the middle. You just never place them by eyeball.
Okay, threads share and synchronize, fine. But processes, how do they talk at all if they share no memory?
Only through operating system or network channels, signals, sockets, pipes, named pipes, shared memory, message queues, memory-mapped files, and the whole distinction boils down to one line: threads share resources, so they can talk right through them, but they must synchronize. Processes share nothing, so they need these channels.
So where does all of this flow into next?
Straight into the next chapter. Event-driven architectures. And it's set up beautifully, watch. Remember the signals a queue thread emits? Finished? Started? That's a producer just announcing, hey, something happened, and letting whoever cares react. You first met slots way back as controllers in the design principles chapter? And next chapter, that dynamic decoupled signal and slot wiring stops being a detail and becomes the entire architecture.
From locking threads down to letting them shout events across the room.
Beautifully put. Concurrency taught us to share safely. Event-driven will teach us to depend loosely. But the through line of this whole chapter is 3 words, okay? Sharing. Communication. Synchronization. Get those 3 right and the mess never even forms.
Concurrency is not parallelism, and now I finally know why. Thanks, folks. New episode. Last time you had me juggling threads and mutexes. Please tell me today is calmer.
Oh, you'll love this one. It's the chapter right after concurrency, and it's built from one radical little sentence. Here's the sentence. Take whatever triggers an operation and completely divorce it from the code that actually carries that operation out.
Divorce? We just met the operation.
Ha! An amicable one, I promise. Look, normally an object reaches out and calls another object's method directly, right? So right there in the code, it knows exactly who that other guy is. His type, what he does, all of it. Event-driven flips that. The object just announces that something happened, okay? And it lets anyone who cares react. It doesn't know who's listening, doesn't care. And here's the beautiful part. The dependency between the objects moves out of the code. The dependency between the objects moves out of the code and into configuration. It gets wired up when the program runs, not when it compiles.
Okay, contrasted for me. What does the old way look like?
Explicit communication. The textbook example, picture a program stuck in a loop, constantly checking, is the key pressed. Now? How about now? That's called polling, active waiting. And the poller has to know in advance exactly who it's checking and how, so the connection gets woven tight, right into the...
That's my toddler. Are we there yet? Are we there yet?
Ha, exactly. And event-driven flips precisely that. The key press, done the new way. The program tells the operating system, look, I'm interested whenever a key gets pressed. And then it goes off and does other things. The OS notices the event, fires off a message. The program reacts. Nobody spins a loop over that keyboard, okay? The source of the event took the initiative. And that flip has a name. A great one. Inversion of control. The caller doesn't call the service when it needs it. The framework, the source.
So, why go through all this trouble? What do I actually get out of it?
The prize is lower coupling between your objects, and less coupling means less total complexity. Remember our coupling scale, way back in the design chapter. Every single dial turns the good way here. The level of coupling drops down to data or to messages, the friendliest end of that scale. The way it's wired goes dynamic, set up at runtime. And the overall intensity comes, Wait,
this is that thing you flagged chapters ago.
You've got a memory on you. Yes, when we ranked static versus dynamic coupling, event-driven, signals and slots, that was named the textbook example of the dynamic kind. So this whole chapter really is that one bullet point finally getting cashed out. But here's the thing, nothing is free, okay? Less global complexity, sure, but more local complexity. Each individual complexity, each individual component gets simpler, it just emits, or it just handles. That's its whole life. The cost is, now nobody can read one file and see who reacts to what. That map is hidden away in the
So one file stops telling the whole story.
Right. Reading the code locally stops revealing the flow of control. And that's the classic bargain of dynamic coupling. You buy flexibility and you pay for it, and how easy the execution is to follow.
Now, you keep saying event and then notification. Aren't those just the same word?
Subtle, but it really matters. An event is a fact. Something happened. A key got pressed. A value changed. A notification is the message about that fact, traveling out to whoever's interested. The event is the thing itself. The notification is the news of it. And get this, the event happens exactly once, but there can be many notifications. As many receivers as care about it, that's how many notifications go.
Goal scored once and the whole stadium hears it.
That's the picture exactly. One single fact, and a whole crowd of notifications fanning out from it. Now let's trace the whole journey, from a condition arising to a reaction actually firing, and it runs through 4 layers. 1. The event generator. The object that recognizes some defined condition just happened. 2. The event channel. The pipe that carries events from the generator over to the processor. 3. The processing engine, where the event gets recognized and the right action fires. And 4. The series of event-driven activities, where the whole thing actually plays.
4 whole layers just to press a key?
Ha! And that is exactly why the channel earns that spot in the middle, because the generator and the processor never know each other directly, okay? A channel always sits between them. So when you add a new handler, you don't touch the generator at all. The handler just tosses its event into the channel, not caring one bit who's on the other end. Nobody has anybody's phone number. The channel is the switchboard. And here's a lovely connection. This exact middleman is the same mechanism 2 patterns already handed us: publish, subscribe, and observer, from the design patterns chapter. All 3 slide a broker between the
Observer, that's the one where the watchers get told when the thing changes, right?
The very one. And hold that thought, because we're going to show that event-driven is basically observer, leveled all the way up. But first, let's go see it in real code. The most widespread real implementation of all of this in the whole C++ world is Qt signals and slots. And to play, a class has to do 2 little things: inherit from QObject and drop the QObject macro right at the top of its definition. That's the entry fee.
Okay, paid up. Then what do I actually work with?
2 concepts and a way to wire them. Signals are methods that produce events. Slots are methods that handle events. And connect is what ties a signal to a slot. Let's take signals first, because they're the weird ones. 3 strict rules. A signal always returns void. Always. It has no body that you write. Qt generates the body for you through a tool called the Meta Object Compiler, mock for short, and you fire it off with the statement emit. So your counter notices its own value changed, and it says emit value changed, and off it.
Wait, what even is emit? Is that a keyword?
Sneaky detail, and I love it. Emit is a macro that, for standard C++, is defined as absolutely nothing. It's empty. You could delete every emit in your code and it would run exactly the same. But you never do, for 2 reasons: compatibility and documentation. The reader's eye hits that word emit and instantly knows, a signal's going out right here. It's a comment that happens to compile. Now, slots, the mirror image, methods that handle events. And unlike signals, you write them as perfectly ordinary functions. 1 rule binds a slot to its signal, same time.
The plug has to fit the socket. So how do I actually plug them together?
With a static method, QObject, connect, and it takes 4 arguments. A pointer to the object doing the emitting, the signal itself, a pointer to the object doing the catching, and the slot. Now, the old style names the signal and the slot using two macros, literally called signal and slot.
You said old style like there's a trap coming.
Because there is, and it's a nasty one. With those macros, the signatures only get checked at runtime, so you mismatch your types and the compiler says nothing. The build passes clean, totally green. Then connect quietly returns false. The connection silently never forms. The program runs along happily, and the reaction you were expecting just never happens. It's the worst kind of bug, a silent one, which is exactly why newer Qt recommends the pointer to member syntax instead. You pass pointers to the actual functions, and now the type matching gets checked at compile time right where it belongs. That same mistake.
And this connect, it runs at startup? It's not baked into the classes themselves?
That is the key property, and honestly, it's gorgeous. The binding is dynamic and per object, not per class. Two different objects of the very same class can be wired up completely differently, so a single type can serve as the controller for two different forms at once. Something static coupling would have forced you to split into separate
Controller. Hang on, that's the Grasp job, isn't it?
good memory. Again! In Grasp, the controller was the class that catches a system event, and we said right then that Qt slots play that exact role. Well, this whole chapter is just the machinery humming underneath that one sentence. Let's close this out with our quality yardsticks. Event-driven architecture almost always does something kind to coupling. It lowers the intensity and with no loss of functionality at all. Two payoffs here. First one, if some signal stops mattering to you, you just stop listening. You don't touch the emitter. You don't disturb anybody. And second, say you want two things to react now instead of one. You just add new slots. That's the whole move. You don't change the emitter. You don't disturb the handlers already sitting there. Removing a reaction and multiplying reactions are both purely local edits that
Okay, and you promised me Observer a while back. Pay up.
with pleasure. Because event-driven is a generalization and an upgrade of Observer. In plain old Observer, the watched object itself holds the list of its watchers, and it notifies them whenever it changes. Here, both the source and the handler depend on an abstract connection mechanism, not on each other, and the channel, the framework, holds that list. So even the subject gets to put down that burden. It comes out lighter and freer. And remember, that tangle from the principles chapter, the MVC loop? Controller updates the model tells the view drives the controller, round and round, a change chasing its own.
Hail, the circular dependency you outlawed for whole packages.
That very one. And we broke that circle with abstraction. The View2 model link goes through Observer, and the View2 controller link goes through event-driven development. Back then, I told you that second one would get its own whole chapter someday. Well, you're standing in it. That was the first little taste. This, right here, is the meal.
A promise from 10 chapters ago, finally landing. All right, bring it home.
One breath. You stop calling directly, and you start announcing. An event is a fact. A notification is the news of it. It flows through 4 layers, with the channel keeping the generator and the processor total strangers. Qt makes it all real with signals and slots wired by connect at runtime. You lose a little local readability, and you win loose, dynamic, ripple-free coupling. Observer, all grown up.
Loose on the outside, flexes at runtime. So where do we go next?
The perfect segue, actually, because all chapter, we've been saying lower coupling, less complexity, all of it in words. Next chapter is software metrics, where we finally put actual numbers on those words, because what you can't measure, you can't control.
From vibes to numbers. I love it. Thanks, everybody. And don't call us, we'll call you. Today's word is metrics, which to me is the part of the meeting where someone puts a number on a slide and everyone nods.
And that nod is the whole danger of this chapter. It opens with a line from Tom DeMarco, which you can't measure, you can't control. Gorgeous, right? And then the chapter spends the rest walking that line back, because you can judge quality two ways, okay? Qualitatively. You describe it, compare it by feel. Or quantitatively, you turn those traits into numbers. And software metrics is the art of the second.
And numbers are objective, so numbers win. Easy.
That's the trap. The whole chapter is built to spring it, because you only ever measure what happens to be measurable, and that's almost never what matters most. Quality almost never measures exactly, so the number you get is just not the answer.
So then what is it, if it's not the answer?
It's a pointer, a trend, an order of magnitude, a spot to compare against, and nothing more. And the book's line is razor sharp. Taking a raw number as your quality score is exactly as dangerous as ignoring it completely. Exactly as dangerous.
So the dashboard worshiper and the guy who never looks are both wrong.
Both wrong. You use a metric in context, okay? Movement over time, one solution versus another, an alarm bell when you cross a threshold. What you never do is read a grade straight off it like a thermometer.
And where does this sit in the course? Feels like a tools chapter.
It's where everything we judge by gut finally gets numbers. Remember cohesion, remember coupling, those quality words from the design chapters. This is where they turn into coefficients. Metrics is the measuring tape laid across the whole subject. So first question, what kind of value can a measurement even hold? 5 types, sorted by scale. Absolute, you measure it directly, like lines of code. Derived, computed from other measures, a ratio. Interval, given as a range. Nominal, just words, like yes, no, blue. And ordinal, and ordering, like greater than. 5 of them, okay?
Why do I care if it's a word or a number? A measure's A.
Because the type decides what math you're even allowed to do. Absolute and derived survive arithmetic. You add them, divide them, average them. But averaging nominal or ordinal values? That's nonsense.
Right. The average of blue and yes isn't a thing.
It is not a thing. On those you only compare and sort. Now, the big split, and this is the one to hold on to. Every metric falls into one of 2 families. Development tracking metrics, how well the project follows the plan, the process, the resources, time, cost, effort. And design metrics, measurable traits of the software itself.
So one watches the work, the other watches the product.
Perfectly said. Put that pair in your pocket. We're circling back to both. Process lives in the schedule. Design lives in the code. Same border you drew judging quality. How's the job going? Versus how good is the thing you made?
All right. First family, how do you actually measure how the work is going?
Constantly and out loud, you post these values where the whole team can see them, okay? Progress, that's jobs done against time. Completion is the mirror image, jobs remaining. Effort, planned hours versus actual. Cost, number of problems, bugs opened and closed, plus requirement stability and size stability. That's your dashboard.
That's a lot of curves. Is there a headline one?
Progress. Progress is the clearest picture of where you actually stand. Cumulative jobs up the side, time along the bottom, and you plot 4 curves stacked on each other. The top one is recognized jobs, all the work that exists. Below it, started. Below that, in testing. And the bottom one, finished.
And the gaps between the lines are...
The gaps are how much work sits in each phase right now. And the elegant part, all 4 only ever rise, they're cumulative and nested one inside the next. Recognized is always at least started, at least in testing, at least done. They can't cross, so you read it by position. Top's the total, bottom's done, and when the done curve climbs toward recognized, you're closing in on the finish.
Feels like the burn down from the Agile chapter, honestly.
Same spirit, exactly. Completion is basically that burn down chart. Agile teams live and breathe these. And get this, the very next chapter, task tracking, is where you wire them up. But there's one condition, and if you break it, the whole beautiful picture just falls apart.
Uh-oh. What breaks it?
Uneven jobs. Think about it. If one job is a tiny one-line tweak and the next is a whole component, then counting finished jobs tells you nothing. The curve can look gorgeous while the project's quietly running late. So the jobs have to be roughly the same size for that count to tell you the truth. Okay, second family, design metrics, measuring the software itself. Number of code units, files, classes, packages, lines of code, LOC, the sheer amount written. Functional elements, classes per package, methods per class. And then cohesion, coupling, stability, and abstractness.
Hold on. Cohesion and coupling are on the list.
That's the whole thrill of it. Back in Chapter 4, those were fuzzy design virtues, right? Things you felt in your gut. Here, they turn into measurable quantities. That's the classic textbook move. You take a quality of structure and squeeze it down into a single number.
Okay, but poke the obvious one for me. More lines means more work got done, no?
And that is exactly the wrong instinct. Okay, LOC is an absolute measure of quantity, not of value. A shorter, clearer solution is usually the better one. So more lines is neither better nor worse, it's just more lines.
So a big LOC number tells me nothing?
It tells you something in context, a growth trend, a way to compare two variants, a way to normalize other measures per thousand lines. That's fair game. But the second you use it as a productivity score, more lines equals more output. You've rewarded the wrong behavior. People pad. They will always pad.
Pay a writer by the word and watch the adjectives multiply.
Every single time. Now, two absolute classics, both chasing the same thing. How hard is this code to understand and maintain? One through control structure, the other through the density of the expressions. Take the first, cyclomatic complexity. You draw your code as a graph. G. Nodes are the start and end points, the branch points, the merge points, and you count the independent paths through it.
Independent paths, as in the distinct ways the code can flow?
Exactly that. And the formula is clean. V of G equals E minus N plus 2P. E is edges, N is nodes. P is the number of connected components, usually just the number of subprograms. And if you tie every exit back to its entry, it collapses to E minus N plus P.
And is there a number I'm supposed to stay under?
10. Keep V of G at 10 or below, okay? Go above, and there's so much branching, it's genuinely hard to understand and hard to test. And the gorgeous part, that same path count is also the lower bound on how many test cases you need to cover it fully. It literally hands testing its homework.
Oh, so the complexity number and the testing effort are the same number.
The same number, and it's the same reason refactoring exists. You split a monster function precisely to drag that number down. This one's from Thomas McCabe, 1976, a paper called A Complexity Measure.
And the second one, the density thing?
Halstead complexity. And this isn't one measure, it's a whole family, all built on expression density. You count 4 things. Total operators. Heads up, operators include the types and brackets. Distinct operators. Total operands. Distinct operands. 4 little counts.
4 little counts. And out of those you get?
A whole cascade. Vocabulary is distinct operators plus distinct operands. Length is the totals added together. From those you derive volume, difficulty, effort, estimated writing time, and get this, even an estimated number of bugs you'll ship.
Wait, it predicts your bug count? That's witchcraft.
Very rough witchcraft. And the book's honest about that, okay? It doesn't hand you a true count of hours or bugs, it gives it crudely. The real value is the link it proves. More varied operators and operands genuinely means heavier code. That's Maurice Halstead, 1977.
Quick, this isn't the complexity from the optimization chapter, right?
Sharp. No, totally different beast. Optimization was about algorithmic complexity, how your resource use scales, raw speed. This is structural complexity, how tangled the code is to read. But same discipline, notice, measure first, judge second. Optimization opens the exact same way. Profile before you touch anything.
Last stop, You said packages. We're zooming out to the big boxes?
The big boxes. Metrics for the relationships between packages. Really, numbers on exactly what the design principles were preaching, that your dependencies point the right way. Start with stability. A package's tendency not to change. Except we don't measure that head-on. We measure its complement, instability, I.
How do you even put a number on not changing?
Like this. Instability I is CE over the quantity, CA plus CE, between 0 and 1. CE is outgoing dependencies, classes in here that lean on others. CA is incoming, classes out there that lean on you. Big CA, lots depending on you, means you don't dare change. You're stable. Big CE, leaning outward, means everyone else can drag you into their changes.
Wait, this is the stable dependencies principle, just with arithmetic bolted on.
The very same principle, now with a formula under it. It told you to run dependencies from unstable toward stable, because a change in a stable package avalanches down through everything below it. Instability I is how you measure which way your arrows actually point.
So not every package can be stable, or nothing could ever change.
Right, you'd have a frozen system. So here's the second axis, abstractness, A equals NA over NC, abstract classes over total. And that's your safe anchor lever, okay? An abstract base doesn't change when the implementations underneath do, so a package full of abstractions can carry a whole crowd of dependents.
So stable and abstract kind of belong together.
That's the stable abstractions principle. A unit should be as abstract as it is stable. So you plot instability on X, abstractness on Y, and the ideal is this line, A plus I equals 1. From stable and abstract in one corner to unstable and concrete in the other. That diagonal is the main sequence.
And quality is your distance from that line?
Exactly. D equals the absolute value of A plus I minus 1 over the square root of 2. Small d, you're hugging the good diagonal. And the far corners, those are pathological, where you really do not want to live.
And I'm guessing they've got names.
2 dead zones, great names, concrete and stable. Everyone depends on it and it cannot move. That's the zone of pain. An abstract and unstable, an abstraction nobody depends on. That's the zone of uselessness.
And cohesion. Did that one get a number 2?
It closes the whole circle. Relational cohesion, H equals R plus 1 over N. R is the dependencies among a package's own classes, N the total. High H means they're densely wired together, so the package is genuinely one thing, not a random pile of files. And you can refine it. Weigh each dependency by how many methods realize it instead of counting 0 or 1.
So run it all the way home. What did all this measuring actually buy us?
In one breath. Cohesion and coupling, those gut feel virtues from the design chapters, walk out of here as real coefficients. You gain a comparison and a threshold. You lose the illusion that any number decides anything. The metric shows you where to look. The designer still delivers the verdict. Right back to DeMarco, where we started.
Measure so you know where to look, then actually go look. I can live with that. Next up, task tracking, where those progress curves finally come alive. Thanks, folks. Today's chapter opens with a quote, "Software isn't written once, it's written over and over, and somebody has to remember what changed, when, and why."
And honestly, that one sentence is the chapter. 2 tools so fused into everyday development, we barely question them, okay? One remembers every change you make to your code, version control. The other remembers what's left to do and what's broken, task and bug tracking. The memory and the to-do list, really, 2 halves of one thing.
One remembers the how, one remembers the what. So what does version control actually buy me?
4 things, and they're worth memorizing. It records the changes to a whole set of files over time, and that one idea hands you 4 superpowers, okay?
Hit me with the 4.
Roll back to any earlier state, any state at all. Compare 2 versions side by side, see who changed what and when, and work in parallel with a whole team without stepping on each other. Roll back, Compare, blame, collaborate. That's the entire pitch.
But how did anybody survive before this? Asking for a friend who names his folders final, final, to, and final, actually final.
Ha! And who among us hasn't? That's the old way. Copy the folder, slap a date on it, pray. And it works. Right up until a second person joins. Then two people edit two copies and somebody's changes quietly vanish. It's chaos. It's chaos. And it gets worse with every person you add. Version control fixes that systematically. The spine of every collaboration.
And where does this land us in the course? We just came off the metrics chapter, right?
Chapter 16, Measuring Software. Exactly. And this one is the plumbing every project runs on. Two names to hold on to because the whole chapter pivots on them. Subversion, SVN for short, the centralized one, and Git, the distributed one. Centralized versus distributed. That split drives everything we're about to say. So, two architectures. Centralized is plain old client-server, okay? The clients are the people, and one server holds the repository. The single place where every version lives. Everybody checks out from it. Everybody sends changes back to it. That's SVN in a nutshell.
One vault, everybody shares it. So what's the distributed twist?
Here's the twist, and it sounds almost wasteful at first. Everybody carries a full copy of the entire repository, the whole history, every version on your own machine. There's still one repo. Everyone agrees is the main one, but that's an agreement, a convention, not a technical requirement.
Wait, everyone has the whole thing? Why copy all of it?
Because then you don't need the network. Committing, browsing history, making branches, all local, instant, offline. You only reach for the server when you want to trade changes with someone. So on a train, no Wi-Fi. You're still fully working, whole history in your pocket.
That's genuinely great. Okay, the actual commands, do those differ too?
They do, and the names have settled over the years. Grabbing a working copy, checkout in SVN, clone in Git, refreshing to the latest, update or pull, sending changes in. Commit. Then diff to see what changed, log for history, and branch, merge, tag for the bigger moves.
Hold on, a second ago you said push. Now you're saying commit. Which one actually sends my code?
And that's the single most important difference, okay? In centralized SVN, commit goes straight to the server immediately. Everyone sees it. But in Git, there's a middle step. Your commit saves locally, just for you, like a private checkpoint. And only later does push send it up to the shared repository.
Oh, so that's the split. In Git, commit is save my draft, push is now publish it.
Exactly. And even the version numbers differ, by the way. SVN gives the whole project one revision number that just ticks up. 1, 2, 3. Git names each commit with a hash, a fingerprint of that exact snapshot.
You keep saying repository, like I know what's inside it. Break it open for me.
Fair. It stores all the versions of the project, full history, usually backed by a database. But Git and SVN store it completely differently. Git keeps an object database in a hidden .git folder, saving a whole snapshot at every commit. And to save space, it just shares the bits that didn't change. SVN? Different animal. It keeps everything centrally on the server, and instead of snapshots, it works with deltas, just the differences from one revision to the next.
Snapshots versus differences. So, a photo album versus a running list of edits.
Oh, that's a gorgeous way to put it. I'm keeping that. Now, to actually work, you need a working copy, your own local copy of one version, and it changes as you type. You update it to pull in the latest, make your edits, send them back.
Edit, send back. So are we done? That's the whole loop?
Almost. But Git sneaks in one extra layer, and people trip on it constantly. Between your working copy and the repository sits the staging area, also called the index. You first add changes into it, and that lets you pick exactly which ones go into the next commit.
Why would I not just commit everything I changed at once?
Because one clean commit shouldn't have to. Classic case. You fixed a bug, but while you were in there, you also tweaked some formatting. Two different things, right? Staging lets you commit just the bug fix now, clean, and leave the formatting for later. It's a filter you run before you save.
That's actually smart. Okay, run me the whole chain, start to finish.
3 steps, and Git adds a 4th. Working copy, where you edit. Staging, where add picks what counts. The repository, where commit remembers it forever. And then, in Git, push, publishes it to everybody. Now, the genuinely fun part, branching. A branch is a version of the project developed independently of the main line, usually one per new feature, worked by its own little team. So one team's half-finished, broken-in-the-middle work doesn't wreck things for everybody else.
A parallel universe where I'm allowed to make a mess safely.
That's exactly it. And when your universe is ready, you merge the branch back into the line you split off from. In Git, a branch is dirt cheap. And I mean dirt cheap, because it's nothing but a light, movable pointer to a commit. You make them constantly.
And in SVN, it costs more?
Heavier. By convention, it's a whole copy in a branches folder, so the culture flips. In Git, you branch without thinking. In SVN, you think twice first.
So, merging? That's the moment two people's edits smash into each other?
Where they combine, and the relief is, most of it is automatic. Anywhere the two sets of changes don't overlap, the merge just goes through. Git even gives you 2 flavors, fast forward and 3-way.
2 flavors? Okay, give me the fast one first.
Fast forward. Your branch hasn't diverged. Nothing new happened on the main side while you were away, so merging is just sliding the pointer forward. No merge commit, nothing fancy. And if both sides moved on, then a 3-way merge. It compares both versions against their common ancestor, the last point they agreed on, and builds a fresh merge commit.
Okay, now people online seem to fistfight about rebase. What even is that?
Ha! It's a whole holy war. Rebase is the alternative to a merge commit. Instead of merging, you replay your branch's commits one at a time on top of the other branch's tip, and you get a clean, perfectly linear history.
Linear sounds lovely, but there's a catch, isn't there? There's always a catch.
There's always a catch, my friend. Rebase rewrites history. It literally changes the identity of your commits. So the iron rule, never rebase a branch you've already published because it shatters every copy everyone else is holding. Don't edit the past once other people have it.
Got it. And when a merge genuinely can't sort itself out?
That's a conflict. The same file changed by 2 people against the same starting version. 2 branches touching the same lines. And I love how the chapter frames it, because a conflict isn't necessarily an.
Wait, hold on. A conflict isn't an error?
It's a signal. It just means the system can't decide which edit to keep on its own, so it stops and asks a human. Git wraps the disputed lines in markers. The less than signs, the equals, the greater. Thens. And you go in by hand, pick one or blend them, then confirm. Sometimes you want to mark one specific version so it's easy to point at later. That's a tag. An immutable, human-readable pointer to one exact state. Something like v1.2.0 that names a release.
Like planting a flag in the ground. This one, right here, this is the release.
Plant the flag, exactly. In Git, there are 2 kinds. A lightweight tag, just a bare pointer to a commit, and an annotated tag, storing author, date, a message. And get this, it can even be digitally signed, so you can prove who stamped it. In SVN, a tag isn't even its own concept. By convention, a cheap copy in a tags folder.
And the number itself, 1.2.A0, is there a real system behind that?
There absolutely is. Read left to right by significance. Major, then minor, then patch. sometimes a revision on the end. Major bumps on big changes, minor when it's more than a fix, but not huge, and patch when all you did was fix a bug or two.
So who sees which part? The public or the team?
Great instinct, major and minor are public-facing, while patch and revision stay inside the team. And the formalized version of this whole scheme has a name, semantic versioning. SEM. Ver. Major.minor.patch.
And what makes each of those tick up?
Precise rules, okay? Major goes up on an incompatible API change, something that'll break your code. Minor on new features that stay backward compatible. Patch on backward. Compatible bug fixes. So, if you upgrade and your code breaks, the major number should have warned you.
So the version number is basically a promise.
It's a promise. You could even tack on pre-release labels like 1000-alpha and build metadata that doesn't affect how versions compare. But the one iron rule under all of it, once a version is published, you never change it. Published is forever.
Okay, tool number 2, version control handled how the code changes. This one's about what's still left to do?
Exactly the handoff. Issue tracking systems manage the record and the communication around your development tasks. And bug trackers? Those are just a special case, aimed at defects. Same machine, narrower job.
And the basic unit, what am I actually holding?
A card. One recorded task or bug, carrying a state, a category, a priority, and a description. That's your atom, and everything else is built out of it.
Ticket, basically. Does the chapter pick an actual tool for this?
Redmine, one of the most widely used, free, open source, runs in your browser, handles many projects at once. 3 pieces to know: trackers, roles, and workflow.
Start me with trackers.
Trackers are the kinds of card. By default, bug, feature, and support. Roles are how permissions get handed out. And the workflow is the tunable rule for who's allowed to move a card where. Hold on to that third one. It's the clever bit.
Okay, so what states does a card move through?
The defaults are new, in progress, resolved, feedback, closed, and rejected. And everyone belongs to a bigger bucket, either open or closed. The state tells you what's expected next, you finish that, and push the card along to the next state.
So can anybody just drag a card anywhere they feel like?
No, that's exactly what the workflow is for. It's defined per combination of role and tracker, controlling who can go from which state to which. A tester might open a card, but only a certain role may close it. Underneath, it's a finite state machine. States as nodes, allowed moves as transitions, gated by your role.
A state machine. We literally just described the workflow as one.
Same idea, exactly. And here's where the whole chapter clicks together. Remember Agile, way back in Chapter 8? The backlog, the user stories. Those are, at heart, just cards. Their states become the columns on a Kanban or Scrum board, and a task travels across it, left to right, from open all the way to closed.
Wait, so the ticket and the actual code, they talk to each other?
They do, and that's the payoff of the whole chapter. You reference the card number right in your commit message, and just like that, your code history and your task history fuse into one searchable whole. The card says what needs doing and what state it's in. The commit carries the change that moves that state forward.
So version control remembers the how, tracking remembers the what, and together they're the project's entire memory. Bring it home for us.
In one breath, version control is a time machine over your files. Branches to work in parallel, mergers to bring it back, tags and semver name the releases, and issue tracking in a tool like Redmine hands out the work and follows it to done. Next chapter, documentation. So future, you remembers what any of this meant. I'm in. Thanks, folks.
All right, last one. And it's the chapter everybody quietly skips. Documentation, the thing we all swear we'll write later.
And never do, right? The chapter opens with a little jab that's stuck with me. Code gets written once, okay? But it gets read many, many times by many different people. That asymmetry is the whole reason this chapter exists.
See, in my head, docs are the shrink wrap, the pretty manual on the finish box that nobody opens.
And that's exactly the trap the whole chapter is fighting. It's not decoration on a finished product. It's communication. It's a channel. How to use the software flows from the builders out to the users, and how the thing is structured gets traded between the builders themselves. So it's a phone line, okay? Not wrapping paper.
Okay, and you keep dangling one big idea. Out with it.
Here's the sentence the whole chapter drives toward. Documentation is not a goal, it's a means. It's a means. Lose sight of that, and it stops being useful and turns into a cost. A cost that goes stale faster than you can even write it down.
Stale faster than you write it? That's bleak.
It's the central tension. Now, what even counts as documentation? Everything alongside the code, the text, the diagrams, the illustrations. Sometimes the code itself. It's not one manual bolted on at the end, it's the whole trail. From the first idea, through every stage, to the finished software, and then past it, into the use and maintenance guides. The specs, the designs, the interface definitions, all of it.
So the last chapter is secretly about all the other chapters.
You just put your finger on it. This is the final stop in the course, and it quietly ties the whole map together. The specs and interfaces from chapters 4 and 6, that was documentation. The UML diagrams from chapter 5, documentation. It's the connective tissue under everything we've done.
Huh, and who's it all for?
Here's a key point. No single document serves everyone. 5 kinds of reader, okay, each one needing something completely different. The client who ordered the work needs to know what they bought. The managers need the requirements and the progress. The designers write down how they picture it. The implementers need what to build and how. And the users, they just need to know what it does and how to run it.
Client, boss, architect, coder, user. 5 people, 5 totally different needs, and no one document can hug all 5. Got it. Okay, so writing all this stuff sounds expensive.
It is expensive. So the chapter splits the reasons into good ones and wasteful ones. Start with the good. 4 justified motives. 1. Formalizing the spec. 2. Supporting remote teams. 3. Spreading knowledge across the team. And 4. My favorite. The writing itself forces you to actually think it through.
Hold on. Writing it makes you think. Like a rubber duck?
Exactly a rubber duck. You sit down to write it, and it forces you to check your assumptions, and some of them are just flat wrong. So sometimes you're not even writing for a reader, okay? You're writing to catch yourself.
That I like. And the wasteful reasons?
3 of those. Out of pure inertia. The client's used to it, or you're blindly following some process. As a cover your back, so there's a paper trail. And to hand goals to another team, but bloated and needlessly detailed.
So the honest reasons must line up with real jobs the docs actually do.
They do. 3 roles. As a requirement specification, it pins down the interface and the behavior. As communication, it bridges you to remote teammates, gold for open source and outsourcing. And as a tool for resolving doubts, it makes you test the shaky assumptions.
But you keep flinching every time you say expensive. There's a catch coming.
Ha! There's always a catch. Over-documentation is its own trap. Write everything, just in case. Sounds so responsible, right? And what do you get? A document nobody reads and everybody dreads maintaining. More is not better. More is not better. Better is exactly as much as you need. Just enough. Not the encyclopedia nobody opens.
Weird lesson to hear out loud, but okay. Just enough. So how do you actually carve documentation up?
By who it's for, 2 big kinds. There's user documentation for the person actually running the software, and there's technical documentation, system documentation for everyone building and maintaining it.
What's in the user pile?
Oh, a whole stack. A description of the whole system. an install guide, a beginner's guide, a reference manual with every single feature, release notes, a quick reference cheat sheet, and an admin guide for the fancy tuning.
Basically, all the stuff I ignore until something's on fire. And the technical pile?
That one follows the system from the inside, okay? The vision, the requirements spec agreed between the stakeholders, the design of how it splits into pieces, the implementation description with the key algorithms, the test plan, the acceptance test plan, and a data dictionary.
Wait, that's the whole project's life story, cradle to grave.
That's the punchline. Technical documentation is really project documentation. It trails the project the whole way, from the vision down to the test plan, because all that knowledge is for the builders and the maintainers, not the end user.
So, the user side gets the manual, and the dev side gets the blueprint of the whole build. Now, this is where Agile has opinions. That quote right at the top of the chapter.
Straight from the Agile Manifesto. Remember, back in Chapter 8, working software over comprehensive documentation.
So, what's the actual reasoning behind snubbing the docs?
It's sober reasoning, honestly. A big pile of docs often does more harm than good, because development docs go stale so easily. And here's the sharp part. Stale information isn't just useless. It's misinformation.
Ooh, so a wrong doc is actually worse than no doc at all.
That's the heartbeat of it. But careful now. Over docs does not mean no docs. That's the misread everybody makes. Software with no proper documentation is a disaster for the users, the owners, and the maintainers alike. So it is not throw the docs away.
Then what's the real message?
Two things, really. The right amount and the right moment. Write it too early and it isn't stable because you're describing something about to change under you. And then the headline everybody quotes. In Agile, the best documentation is good code.
The code documents itself. Bold flex. So the other kinds just get benched?
Used sparingly, okay? Comments in the code can auto-generate docs that stay up to date. Hold that thought. We're coming back to it. Specs stay shallow as user stories. Models are useful, but they go stale. And full documents are pricey to maintain, so they're rarely made.
And the price of traveling that light?
You write on demand, so what you get is partial and scattered. And that's the classic complaint about Agile. No systematically organized documentation. You gain freshness, you lose the tidy shelf. The main split for documenting the code itself. It's all about where the documentation lives. External docs are kept apart from the code. Standalone documents, manuals, wiki pages. Internal docs are generated straight from the source, plus some specially shaped comments.
And the difference that actually matters is what?
Freshness. Again, it always comes back to freshness. External docs sit off to the side, so the moment the code changes, they go stale. Internal docs live with the code. They change on the very same edit. Much, much harder to rot.
So if you're going to write docs at all, grow them out of the code so they can't drift.
That's probably the best way to keep them current. And the extreme version of best docs, or good code, is self-documenting code. The names, the structure, the flow, all so clear that any extra explanation would just be redundant.
Clear names, small functions, clean flow. But hold on, does that mean I stop writing comments entirely?
No. The comment carries only what the code can't say for itself, and we saw this back in the debugging chapter. A good comment explains the why, not the.
The what?
The what? A comment that just parrots the line right below it is redundant, and worse, it's dangerous. Because when the code changes, that comment stays behind, and it starts to lie to you.
A lying comment. So a bad comment is genuinely worse than no comment. It actively fools you.
It deceives the reader flat out. A good comment records the intent, the reason behind a decision, an assumption you made, a trap you can't see from the code alone.
And the read me? That's the front door to the whole thing?
The most common entry point to the external docs. A short little file sitting right next to the source that tells you in minutes what the project's for and how to build it, run it, use it. The perfect model of just enough And because it lives right there by the code, it's easy to keep current.
Okay, step back. Who is all of this ultimately serving?
The phase software spends the most of its life in maintenance. Whoever changes your code years from now leans entirely on what's true right now. The code, the comments, the docs you derive from it. And a single scrap of accurate internal documentation beats a whole shelf of stale documents.
Freshness beats volume. Accuracy over thickness. Got it. So, who actually does this auto-generating? Is there a tool?
The tool, Doxygen. It reads your source and those special comments and builds the docs for you. Born back in 1997, it basically became the unofficial standard for automatic program documentation.
And what does it spit out?
Detailed docs in a whole bunch of formats: HTML, LaTeX, RTF, PDF. And get this, it also draws dependency graphs, inheritance diagrams, collaboration diagrams straight out of your code.
Wait, inheritance diagrams? That's the UML class stuff from Chapter 5, generated for free?
For free, right out of the source. Same notation you'd sketch by hand back in Chapter 5, except now the tool keeps it in sync with the actual code, a diagram that literally cannot go stale.
That is the dream. The picture updates itself. So what do these magic comments actually look like?
A few styles. There's the C++ style, a comment of at least 2 lines, each one starting with 3 slashes sitting right above the function. And there's the JavaDoc style, /star. Star, with special tags inside it.
It's like what?
@brief for the one-line summary. @param for each argument. @return for the result. @throws for the exceptions. So for little add 2 numbers function, @brief says adds 2 integers. @param describes A and B. @return describes the sum. That's the whole thing.
And those same tags work on the members of a class?
Same tags. A shopping cart item, a total price method, and @throws for a bad discount value. And here's the beautiful part, because the comment is glued right onto the thing it describes.
Edited in the very same stroke, you edit the code.
And the tool rebuilds fresh docs every single time. That's the loop closing. Okay? From the agile idea that the best documentation is good code down to a concrete tool that makes it real.
And this isn't just the end of the chapter, it's the end of the whole course.
It is. And look at the arc. From the problems of software development, through objects, UML, design principles and patterns, agile, testing, refactoring, debugging, optimization, concurrency, event-driven architectures, metrics, version control. Why?
And we land here on documentation, which is really just communication, the thread running under all of it.
The thread under all of it. So here's the whole course in one breath. Write less, keep it true, and let the code do the talking.
From day 1 to the last page, it was all one conversation. Best doc is good code. That's a wrap. Thanks, folks. So this one's an appendix, the bonus track, the stuff we skip if we're...
The stuff the whole course secretly stands on. Here's the thing. Every earlier chapter waved its hands. You know pointers, you know constructors, you know templates, and moved right along. And we all nodded, okay? We all nodded. This appendix is where we finally look under the hood.
So the footnote is the foundation.
The footnote is the foundation, and it runs on 2 threads that keep coming back. Thread 1, how objects live and die in memory. Pointers, references, new, delete, constructors, destructors. Thread 2, how code becomes reusable, and that's really one word, polymorphism, in 2 flavors.
2 flavors of one word?
2 flavors, hierarchical, through inheritance and the virtual keyword, and parametric, through templates. Same split that opens the whole polymorphism chapter later, by the way. And look, the point isn't to teach you C++ from scratch. It's a clean mental model of what's underneath, because nearly every pattern, every principle in this book, push on it hard enough, cashes out to exactly these mechanisms.
Memory and reuse. 2 rails. Let's ride.
Rail 1, memory, a pointer. Strip away the mystique is just a variable that holds the address of another object. That's it. And here's what gets people. The very first trap has nothing to do with memory. It's the declaration syntax. The syntax bites you before the concept even shows up.
Of course it does. Go on.
Watch this. You write int star p1 p20. 1 star, 2 names. Quick, how many pointers did you just make?
2. 2 pointers. Easy.
1. Just P1. The star binds to the name, not the type. So P2 is a plain old int sitting there, innocent. You'd need a star in front of each name to get 2, okay? So the rule writes itself. 1 pointer per line. Declare them one at a time, and the trap just evaporates.
That's genuinely evil. What else can a pointer do to ruin my day?
Ha! Here's the flip side, and it's beautiful. Right through a pointer, and you change the thing it points at, not the pointer itself. So A equals 1, then B points at A. Now, twice in a row, you run star equals A plus 1. After all that, what does it print?
2. It's 2 both times. It has to be.
3, because star B is a tree. Writing through B, write straight into A. First line, A becomes 2. Second line, A plus 1. So now A is 3.
Wait. You never wrote to A. You wrote to B.
But that's the whole point of a pointer, my friend. B doesn't hold a value. B holds A's address. So star means go to that address and set it, and that address is A. You never touch B's contents. You reach through B and rearrange A. Same expression twice, different answer. The pointer moved the goalposts underneath you. The pointer moved the goalposts underneath you.
My brain hurts, and I love it. Okay, and a reference?
The stricter cousin. A reference is a permanent alias for an object that already exists. You can't re-aim it, and it never points at nothing. No, ever. And pocket this, because it pays off twice before we're done. Destroying a reference does not destroy the thing it names. Same for a pointer. Kill the pointer. The target's still standing there. Quick detour into arrays, okay? Because C-strings hide a byte from you, and it matters. 2 char arrays, same 3 characters. The first I build from the literal, quote, C++, quote. The second I spell out by hand as a list, C++. Same length?
3 and 3. I'm not falling for it this time.
4 and 3. And I know. Where does a 4th character come from, right? The terminating null. Initialize from a string literal, and the compiler quietly staples a 0 byte onto the end, for free, without telling you. The hand-spelled list gets exactly your 3 characters, not one more. No terminator.
So, the invisible one? That's the difference between the two?
The whole difference, and it's not cosmetic. Here's why it bites. A C string isn't even a type. It's a handshake, a convention, a char array that, by agreement, ends in a null byte. And every standard function bets on that convention. So hand Sterling, or Coot, the version with no terminator, and it doesn't stop where your data stops. It keeps reading, marching through memory until it trips over some random 0 downstream.
So it just wanders off into other people's memory?
It wanders off into whatever's next. And that, right there, is the kind of bug that works fine on Tuesday and crashes on Friday. 1 missing byte. Now, sometimes you don't wait for the compiler to hand you memory. You grab it yourself at runtime. That's new. It carves out space on the heap and hands you back a pointer, and that pointer's type has to line up exactly. And of course, there's a trap in the syntax.
There's always a trap in the syntax.
3 honest lines and 1 liar. Line 1, new shorts. 1, uninitialized. Short, fine. Line 2, new short, bracket, 900s, that's an array of 900 shorts. Line 3, new short, parent, 900s. And this is the sneaky one. That's 1 short, initialized to the value 900. The parentheses are an initializer, not a size.
Hang on. So brackets and parens aren't interchangeable at all?
Not even close. Brackets say how many, parens say what value. Bracket 900 is 900 of them. Paren, 900 is 1, holding 900. Now, the liar? You declare P as short star, a pointer to a pointer, and assign it new short bracket 900. But array new gives back a plain short star. You're jamming a short star into a short star. Types don't match. So what happens?
It blows up when you run it?
It never runs. It's dead at compile time. 1 star short, literally. The compiler catches it before the program ever draws breath.
Okay, so who cleans all this up? Wait, does it clean itself up?
It does. And honestly, one of the loveliest ideas in the language. So let me build it up. First, making an object is always 2 steps. 2, allocation, which reserves the space, and initialization, which runs the constructor. And a subtle one, you write lista L2 equals lista, open parent, close parent. That looks like it builds a temporary lista and copies it into L2, right? Looks wasteful.
Yeah, why would you ever write it that way?
Because no temporary ever gets made. The compiler just erases the copy. That's copy elision, mandatory since C++17. So L2 gets built directly in place with a default constructor. No waste. Okay, now the trap. Everybody hits with destruction. Objects don't get destroyed in the order you declared them. They get destroyed in the order of their lifetime. Different thing entirely.
Give me the lineup.
All right, a global int a, then inside main a pointer n from new int, then a local int k, then explicitly delete n. The destruction order? N, then k, then a. N first because you said delete right there on the spot. K, next. A local automatic lifetime. It dies the moment main ends. And A.
The global just hangs around till the end.
Till the very end. Static lifetime. It lives until the program stops. And that same model tells you exactly how many times a destructor fires, which is where it gets fun. So, objects A and B, both real. A reference C that aliases A. A pointer P from new A. And a pointer Q holding B's address. 4 names that smell like objects? How many destructors actually fire?
4. 1 for each. It has to be 4.
Twice! Only A and B, the 2 real objects. C is just an alias. When it vanishes, it calls nothing. It was never a thing, just a nickname. Q is a pointer aimed at B, and killing a pointer never touches its target. Remember, we pocketed that. And P is the sad one. A heap object, made with new, no delete anywhere. So its destructor never runs, and that memory just sits there.
Hold on, the destructor never fires? It just leaks?
Leaks. Forever till the process dies. Burn in the rule for every new, exactly 1 delete, or it's gone for good. And get this exact problem comes back to bite the singleton, way over in the patterns chapter. The singleton, remember, is the object there's only ever one of.
Right? There can only be one thing.
That one. Make it a static object, and you hit a wall. You can't control the order. Statics get torn down at shutdown, so a singleton, still in use, can die too early. So you say, fine, I'll make it with new instead. And now you've got a heap object with no delete. The exact leak we just met. Same knot, tied the other way. And the way they finally untie it is a thing called RAIE.
Which is, in plain English,
resource acquisition. Is initialization. Clunky name, gorgeous idea. Here's the engine. An automatic object's destructor fires deterministically, right when you leave the scope. Guaranteed, not whenever some garbage collector feels like it. So you tie a resource to an object's lifetime, memory, a file, a lock, a database connection. Constructor grabs it, destructor reliably frees it, and the kicker. Even if an exception blows up halfway through, the destructor still fires on the way out. The object cleans up after itself.
So it's its own janitor, and this loops right back to the OLP chapter, doesn't it? Objects having a lifetime?
Straight back to it. The object chapter told you every object has a lifetime. It comes into being, exists for a while, passes away. This is that same story told from the machine side of the table in constructors and destructors. Okay, jump the tracks to rail 2, reusability, and the headline tool is polymorphism. Now, the book splits polymorphism 4 ways: hierarchical, parametric, implicit, and ad hoc. But for reuse, honestly, it's the first 2 that carry the weight. This section is the hierarchical one, the inheritance-based one, and it runs on a single keyword: virtual. Virtual.
Okay, so what does virtual actually buy you?
A virtual function is a method a derived class is allowed to override, and that override is what enables dynamic binding. Meaning, the call picks its version at runtime from the real object sitting there, not from what the code thought it was holding. But, and here's where people get burned, it doesn't just happen automatically. You need 2 things to line up.
2? I thought virtual was the magic word.
Necessary, but not sufficient. Necessary, the method's declared virtual. Sufficient, you call it through a reference or a pointer. Do both, and dispatch lands on the real type. But call that same method on the bare object itself, by value, and it binds statically, right there at compile time, no matter how virtual you declared it.
So the reference is what actually wakes the whole thing up.
That's it, exactly. And now that note we pocketed pays off, see? References and pointers don't own the object, they just aim at it. So they can aim at any derived type and let dispatch land on whatever's really there. Okay, push further. A virtual method can go all the way to pure virtual. No body at all. You literally write equals zeros where the code would go.
All promise, no delivery.
Ha! Exactly! Think of a shape class with area equals 0. A circle knows its area, a square knows its area. But shape in the abstract, no idea. It can't. So it declares the promise and leaves delivery to the kids. And the rule, a class with at least 1 pure virtual method is abstract. You cannot instantiate it. But careful, this trips people. Just having virtual methods doesn't make you abstract. It takes 1 pure virtual. 1.
1 pure virtual, or you can still build it.
That's the line, exactly. You can't make an object of an abstract class, but you can still declare pointers and references to it, which matters. And any concrete child has to implement every pure virtual before you're allowed to instantiate it. So the abstract class becomes a shared interface, a contract that the whole family has to honor.
So this is the polymorphism the whole course keeps leaning on.
This is the engine room. Contract plus dynamic dispatch through a pointer or reference. That's what lets one piece of code work with a dozen derived types without knowing or caring which one it's got. And it's why Liskov, back in the design chapter, means anything. A stand-in only truly substitutes if dispatch lands on it. Polymorphism gets its own entire chapter later. But the mechanism, the actual gears, they live right here.
And the second flavor, that was parametric?
Parametric? Yeah, also called generic programming. And here's the clean way to hold the two apart. Virtual abstracts over behavior through a hierarchy. Templates abstract over types. So take a maximum function. You write template, type name T, and it returns the bigger of 2 T's. Write it once, and it works for any type that knows how to compare itself.
One recipe, any ingredient. So how does it know which type to use?
That's instantiation, swapping the symbolic T for a real concrete type, and it happens 2 ways. Implicit, where the compiler deduces it, you call maximum of 2 and 3. It goes, T's int, done. And explicit for when the arguments are ambiguous. Like maximum of a 4 and a 9.8. One's an int, one's a double. Now the compiler's stuck. It can't tell whether T should be int or double.
So you just tell it? Spell it out?
You spell it out. Maximum, angle brackets, double. Put it in the brackets and the ambiguity's gone. And it's not only types, by the way. You can parameterize a constant too, like a template taking a type T and an int k and multiplying by k. And there are whole class templates, parameterizing the types of the members or of the key methods. Same idea, bigger scope.
Any catch with the class ones?
Oh, a nasty one. Class templates compile in passes. First pass, the compiler only checks the definition syntax, just does it parse. Then, at instantiation, the structure gets compiled, but each individual method, it doesn't get compiled until you actually call it.
Wait, the methods aren't checked up front?
Not until each one's used. A method you never call is never compiled, so a bug sitting inside it stays invisible. And think what that means. A template can ship, go into wide use, get relied on all over a code base, and the error just hides until the one day somebody finally calls that one broken method.
A landmine buried under works on my machine.
Exactly a landmine. And now, zoom out. This is the second big lever the polymorphism chapter is built on. And it's the very same parametric polymorphism, the design principles chapter, offered up as the alternative to dependency inversion. Remember that? When you can't give things a common base class to share, you reach for templates instead of an abstraction in the middle. Two roads to reuse, and this one appendix paves both. Last concept, straddling two worlds, performance and organization, inline functions. You mark a function inline, and the compiler may unroll it. Splice the body straight into the call site, so there's no separate call, no extra stack frame. A little like a C macro if you remember those, but type. Safe.
So, inline definitely makes it faster. It splices it in. Done.
It means maybe. That's the thing. Inline is a suggestion, not a command. The compiler decides on its own, and it's free to ignore you. And here's the twist. In modern C++, inline is barely about speed anymore. It's mostly about the one definition rule. Inline lets the same function be defined in several translation units, like write in a header, without those definitions colliding at link time.
So the speed became the side effect, and the header thing became the actual point.
That's the modern reading, exactly. Same deal for methods, same maybes on the splicing. And memorize this last one, a freebie you'll use constantly. A method defined right inside the class body is automatically inline. You don't type the keyword. It's just implied.
All right, land the plane. What did this whole foundation actually give us?
2 rails, that's the whole map. Rail 1, memory and lifetime, a pointer holds an address, a reference is a permanent alias, new and delete pair up or you leak, and because destructors fire deterministically, you get RayAII for free. Rail 2, reusability, hierarchical polymorphism through virtual functions and abstract classes, and parametric polymorphism through templates.
And every one of those hooks into a real chapter.
Every single one. Lifetime and destructors, the singleton shutdown headache, and the whole reason RAA exists. Virtual dispatch is what makes Liskov mean something, and what the entire polymorphism chapter runs on. And templates are the parametric road the dependency inversion talk was pointing at all along. Push on nearly any pattern, any principle in this book, hard enough, and it bottoms out right here, in this appendix.
The footnote was the foundation all along. Pointers, destructors, and the machinery under every pattern. Thanks, folks.